So it seems that we're ready to go. Okay, so let me start saying many thanks to all of you for attending this meeting. On behalf of the scientific and organizing committees, I would like to welcome all of you to this 3 days event, which we have organized to celebrate the 16th birthday of Enrique Zuazua, who I am seeing him among the participants. Hi, Enrique, morning, how are you? Or good afternoon for you. It is morning for us, but afternoon for you. Enrique is a very close friend for more than 35 years. We are very proud of him and of his career, throughout which he has enriched mathematics with all what this such a statement can mean. So you can easily imagine how happy we are to celebrate his birthday from the Chilean community of applied mathematicians, where he is considered a member of our family. So very welcome, Enrique, and everybody. The meeting is organized around nonlinear theory and control theory. Nonlinear analysis and control theory, which subjects in which Enrique has contributed with seminal ideas and with extremely fruitful collaborations with colleagues all over the world. For this opportunity, we have invited 21 worldwide prominent speakers on these issues. Each of one will give a 35-minute conference, after which we will have 15 minutes for discussions, comments, and questions. But to begin with, we would like to carry out a tribute to Enrique's career, which will be in charge of four high academic authorities in different universities from Spain, France, and Chile. To begin, we will invite Professor Maria Jose Guibert, President of the Deusto University, Basque Country, which has pre-recorded a video introducing the contribution of Enrique to Deusto University. So let us start watching this video.
It is a pleasure for me as rector of the University of Deusto to open this event entitled Workshop on Nonlinear Analysis and Control Theory in honor of Professor Enrique Zuazua on the occasion of his 60th birthday. Our good friend Enrique Zuazua began his collaboration with Deusto in the chair of computational mathematics in 2016, precisely because his area of expertise is closely linked to this field. His work in the interface between control systems theory and numerical analysis and scientific computing has led to some fruitful collaboration with different industrial sectors, such as the optimal shape design in aeronautics and the management of electrical and water distribution networks. The main project that currently links him to Deusto Foundation is the DICON project. DICON project and ERC, the European Research Council project, his second project of this kind. In this case, in the advanced category. It will last until 2022. Since 2016, the DICON project members have been working to make a breakthrough contribution in the broad area of control of partial differential equations and the numerical approximation methods by addressing key unsolved issues appearing systematically in real-life applications. To achieve this, they have been focused on three objectives. One, contributing with new key theoretical methods and results. Second, developing the corresponding numerical tools. And third, building up new computational software, the DICON computational platform, DICON blog, bridging the gap to applications. His scientific career in the field of research and applied mathematics has achieved great international renown and a major impact, both scientifically and socially. Last but not least, and particularly noteworthy, he has never lost his roots, his pride and his Basque origins. Born in Eibar, Basque-speaking and a member of a Basque Academy of Science Jakiunde, he has managed to combine this local and global dimension in a very balanced way. Ohore handi bat da guretzat. We are very proud of him. Thanks to this collaborative networking, he has built relationships with international researchers and students, particularly with Latin American and international students, always available to participate in different meetings, to establish collaborations and to welcome students and visitors. Throughout the life of DICON, this has been one of the cornerstones of the chair. In particular, its cooperation with the University of Chile, host of this event, is a good example of this. I wish you all a fruitful event full of sharing and learning. Eskerrik asko. Thank you very much.
Thank you very much, Professor Guibert. And now we have Professor Amaya Mendicoechea, President of the Autonomous University of Madrid, who will say some words.
Well, thank you very much, Professor Conca, for giving me the floor. I want to take this opportunity to thank the organizers of this workshop on nonlinear analysis and control theory in honor of Professor Enrique Zuazua for his 60th birthday, to give me the opportunity to welcome you all to this workshop. I cannot comment on the content of the workshop, but I'm sure it's going to be really interesting for all of you. I don't think Professor Zuazua needs much of an introduction, because you all know the prizes and awards he has received, the positions he has held at different universities and that he currently holds at different universities. We've already heard the rector of the University of Deusto. By the way, that's where I did my BA degree, because like Professor Zuazua, I'm a Basque in Madrid as well. So I'm proud to say that along with these other positions, Professor Enrique Zuazua is chair of applied mathematics in the Department of Mathematics in the Faculty of Science at Universidad Autónoma de Madrid. And he's involved in several projects at this university, European projects and national projects. And there are two aspects I'd like to mention, because my acquaintance with Enrique is quite short. It's just a few months ago we met when I was running for rector at the university, but there are two aspects of his CV that I find particularly impressive, along with all the prizes and awards that he has received and all the honors that he has received and all the recognition that he's already got. One is the fact that he's supervised 24 doctoral theses, if the data on the webpage is correct. I think that's a lot of theses to supervise, and it just gives an idea that he's really concerned with the training of future researchers. And the other one is partly the one you're celebrating here, which is the collaboration, the intensive collaboration, international collaboration with departments and researchers all over the world. So Latin America particularly, but also many countries in Europe, the northern Mediterranean countries, in Africa, as well as Asia, such as China and Iran. I think a good example of that is the variety of speakers that you're going to have in this workshop from Italy, France, Romania, Germany, the USA, and Latin American countries such as Mexico, Brazil, and Chile. It seems to me that the speakers in this conference are not just colleagues, as we understand them, but also friends. And this is really remarkable because, well, you're all mathematicians. As far as I know, mathematicians do not work in labs, and they do not require like big groups to do research, unlike other areas of scientific endeavor. So what this tells us is something about Professor Zuazua as a researcher, but mostly as a person. So I'm very happy that he's receiving this tribute. I hope you have a very fruitful exchange in the next few days. And I really hope that Enrique also enjoys it. Thank you very much.
Many thanks, Amaya. And now it is the turn to address some few words to the Vice President of our university, University of Chile, Professor Alejandro Jofre, who in its turn, he's also an applied mathematician, an optimizer. So please, Alejandro, go ahead.
Thank you, Carlos. It is more than a pleasure to be here celebrating his Enrique 60 years. Hi, Enrique. I remember very well when he visited Chile many times, 3 or 4 times at least, remember. And it was very easy to know that Enrique was visiting us, because I was very active, moving, talking with different colleagues in many areas, not only mathematics, because sometimes we were discussing about the development of the country, economics, about social science, and I know very well his interest also in this connection between mathematics and other areas like art, and it was we had very interesting discussion when he was pushing ahead his radio program in Onda Vasca. I remember that many years ago, and always talking about, of course, PDEs and control and optimal shape problems and numerical analysis, but always thinking very deep on the connection between mathematics and some specific problem coming from the engineering, sometimes societal problems. So I was very impressed by his impact of different results that he has been developing in his career. And we see clearly a fact of a collection of prizes and awards in different countries. and not only Spain. And Enrique is a mathematician, which is very good to talk with him and to interact. And we see that the papers and contribution with many co-authors of different latitudes, and we were very happy to have Enrique in Chile so many times, and from him we met other colleagues around PDEs and control, and I see here today some of them, and I say hello to good friends that are in this. There are more than almost 90 people connected now, and that is a good example that Enrique not only productivity but also this friendship with many colleagues from different countries. So congratulations, Enrique. The 60 years is a good age, and I know that you are very, very active, still very active, and we hope that you will continue to be active and to have you here in Chile soon.
Many thanks, Alejandro, for these very friendly words. We appreciate them. So to start concluding this first tribute to Enrique, we have the privilege to receive Professor Alain Arnaud from the Université Pierre and Marie Curie, Sorbonne University. Alain was Enrique's PhD advisor at the middle of the 80s when we met Enrique for the first time, so more than 35 years ago. So if Alain, are you there? Okay, yes, I see you here. Okay, so please send some words to Enrique.
Okay, so Enrique, you see already 88. I hope it will overpass 100 participants. First of all, I would like to thank the organizers for this meeting, which promises to be very interesting, and to welcome all the colleagues who accepted the invitation to talk here. Age 60 is an important step in a career. I remember my own birthday party in Tunis 12 years ago. It gave a new impulse to my research to see all these friends from very different origins starting to interact, just because I changed my status from mature researcher to elderly man who deserves some consideration. I even remember that on this occasion, Felipe Alvarez, a very bright young Chilean mathematician, wished me another 60 years of mathematical research. He left us so much too early, and I want to recall here how important his achievements have been for several French mathematicians, including myself. What can I say about Enrique in 10 or 15 minutes that you do not know yet? You all know that Enrique started his career at Laboratoire Jacques-Louis Lyons. At that time, it was called Laboratoires d'Analyse Numérique de Paris 6 in Paris, by preparing a PhD degree under my supervision. He was introduced to me by Maria Esteban in 1985, and my first impression was that of a modest and somewhat shy young man. Then I understood rather quickly that, as intelligent people usually do, he always observed his interlocutor some time before revealing his true personality. In our first meeting, I asked Enrique a simple-looking open question which seemed logically solvable in finite time. The question was about the existence of zeros in a space-time cylinder 0t cross the domain for the solution of a clamped plate equation. Such results were previously known for abstract equations of the form u double prime plus a of u equals 0 when A is a positive self-adjoint operator with compact inverse on L2. assuming that the first eigenvalue of A is realized on some positive eigenfunction. For the case of B-Laplacian with clamped boundary condition, it is known that such eigenfunctions can fail to be of one side. For instance, if the domain is an annulus. But of course, in such a case, all solutions with initial state made of multiples of that eigenfunction do change sign in any cylinder, so that it's hard to believe that the sign changes of the first eigenfunction really make the situation worse. When I asked the question to Enrique, he almost immediately asked whether it could be useful to find a positive supersolution for the eigenvalue problem. Then maybe the next day, he told me that a variational principle of Guido's Tampacchia that we recently learned from Brezis seminar course should allow to do that. 1 week after, my question was solved. Finally, a few weeks later, we concluded that when the first eigenfunction is not of one sign, the global oscillation time becomes even smaller than the optimal oscillation time when the first eigenfunction has a constant sign, which is pi over square root of lambda 1, with lambda 1 the first eigenvalue of the bi-Laplacian. So the problem was entirely solved in an optimal way. A few months later, I started to ask him some rather technical questions directly connected with my personal main field of research, something that I almost never did with my students. The results were excellent and even helped my own research in the field. Chance sometimes plays a role, not only for our results, but to guide our careers. In 1986, Jacques-Louis Lyons, who was delivering his regular course at Collège de France, asked me whether I could help to write down the corresponding lecture notes. Unfortunately, or maybe fortunately, I had a long sojourn already planned in Tokyo, which made it impossible for me to follow most of his lectures in the fall of 1986. At that time, there was no Zoom facility. A few weeks ago, I discussed with Jesus Hernandez, who warned me that already as a high school student, Enrique had a reputation of exhausting all his math teachers, and told me that I should be very strong to control his incredible energy. And actually, I remember that during the years from 1985 to 1987, each morning, when arriving in the lab, after making 2 steps in the corridor, I saw at a distance Enrique saying, "As a matter of fact, it turns out that," or something of this type, referring to our previous conversation that I partly forgot, since I had the strange habit of sleeping at night. I decided to do something very unusual at that time. Now it's usual to have several advisors. At that time, you had one, and that was all. So on the pretext of the lecture notes, I decided to share the direction of research of Enrique Zuazua with Jacques-Louis Lyons. The plan worked perfectly. Although initially Lyons was a bit disturbed by the small southeast accent of Enrique, very soon he understood that Enrique never had enough work for his capabilities. The lecture notes were written, they were published, and as expectable, Enrique immediately got some sharp results in the field. To improve the plan, I did one more thing. I introduced Enrique to another talented young mathematician of Hungarian origin, namely Vilmos Komornik, who was following regularly and very actively Jacques-Louis Lyons' course, with whom he immediately started to collaborate on some fundamental open questions raised by Lyons, following a well-established tradition that which attracted a large audience. Their joint achievements were quite remarkable and have been highly appreciated at the international level. One afternoon, after his recognition by Jacques-Louis Lyons, but probably before the defense of the PhD that was promising to approach the level of habilitation, I remember asking Enrique, near the metro station of Jussieu, whether he was planning to look for a position in France or go back to Spain. He immediately answered that his parents were getting old, and consequently, he preferred to go back to Spain to remain none too far from them. By chance, sometime later, I happened to talk with Yves Meyer, who just started to interact with Jacques-Louis Lyons on some aspects of control theory. Yves Meyer had a very strong influence on Spanish mathematicians, and with a 3-line firm recommendation letter from Lyons, Enrique obtained very quickly a full professor position in Madrid. The sequel of his career has been more complicated and less comfortable than the beginning, since he did not satisfy himself with doing such mainstream research. He wanted to fight to see his ideas produce concrete results. From the very beginning of the 90s, I stopped trying to control or even follow Enrique's activity, since I remembered the warning of Jesus Hernandez. From time to time, I had to review some of his papers, and very soon the situation was reversed, and my student had to review mine. As you know, it is the normal ambition of all fathers that their children become brighter than them. Fortunately, in my case, that goal was not difficult to achieve. I recently explained to Carlos Conca that partly because of the COVID pandemic, I realized part of my bucket list by starting to work on physics, not the physics of the mathematician, but the real one, having to do with the real world. Some of you might imagine that I wish to avoid competition with my British students, but it is not at all the point. How can a father even think of competing with his children? We are not really living in the same world as our children, and we should be aware of that reality every day if we really want any progress for our fragile human species. I wish you an excellent meeting and extend once more my thanks to all of you in this very special period where Enrique will start his next 60 years of research. Thank you.
Thank you very much, Alain, for such an interesting introduction to the initial stage of Enrique's career. Many thanks. His relationship with Laboratoire Jacques-Louis Lyons, with Professor Jacques-Louis Lyons, and with all the staff there. So now I think that Enrique, he would like to say something, or can we open him the microphone, please?
Yeah, I think I can talk now, right?
Yes.
So thank you, Carlos, Sebastian, Rodrigo, all the friends in Chile for taking the care of organizing this. It would have been great if we have had the opportunity to do that together, but I mean, it's great that we can do it in Zoom. This is fantastically organized, and well, so thank you for all that joined, and in particular to the 4 speakers we had that represent, many things, of course, for me. So chronologically, I think Alain is first. I mean, he was my PhD advisor, and he represents probably this golden age of the Laboratoire Jacques-Louis Lyons, where there were so many people, right? Some of them were already very well established professors. So I had the privilege of attending the lectures person of Bresis that Alain mentioned, but also Sierlet, Rabiar, Glovansky, Pironneau, Nedelec. I mean, that was, I still can, I still live on what I learned in this first academic year in Paris, right? And then there was people like you also, Carlos, right? At that time, you were essentially like a postdoc. I mean, just a beginner, a researcher in the CNRS, but that were playing this fundamental role of investing. I remember how many things you explained me in your office, in your blackboard, about all kind of weak limits, homogenization, functional analysis, compactness. I mean, these are things that are impossible to be understood if someone like you, in that case, a consolidated expert was not telling you in person, right? And together with you, there were others that I remember talking very often, like Hervé Ledré or Thierry Casenave and many others. So I think then Alain and all this generation of, say, the French family of mathematics that, provided me the opportunity to do all the rest. So for the others, I mean, later I have been a professor in Complutense, in Autónoma. I really thank Amaya Mendicoechea, the new rector of Autónoma that was here with us. I owe so much to Autónoma, right? So this is a fantastic campus, a fantastic university, full of opportunities. And I'm sure there are still many interesting things to be done in the mathematical sciences in the Autónoma campus. And then later to José María Guibert, the rector of Universidad de Deusto, that was kind enough to open his house so to, collaborate with Autónoma on the development of the DICON ERC advanced grant. So I really thank, right? But then, despite one is mainly working in one place or another, there are other places to whom one belongs, right? And in that sense, the Universidad de Chile, not only because very, individuals like you or Jaime Ortega or Sebastián, Rodrigo are working there, but institutionally, I feel very attached in the sense that it has been a model, not only for me, but I think for the whole community of applied mathematics in Latin America is the Universidad de Chile. And I really thank that Alejandro also took the time to be with us. Yeah. So thank you all. I hope you will enjoy this workshop. Certainly the talks are extremely interesting. And I suppose that not all of us could be, will be in conditions to be there all the time, but hopefully this will leave a trace, as Alain said, in order to continue in the near future with our collaboration. As you know, I am now a professor at Friedrich Alexander Universität in Erlangen, Nuremberg, the university where Felix Klein, was working in the turn of the 20th century. It was Felix Klein who already indicated, right, that mathematics should be driven by schools, not only by individuals, and therefore that education and research should come together. I think Gunther Leugering is among the speakers. I owe Gunther also, as I do to many others in this audience, really a lot. He gave the generous opportunity for me and my family to join FAU. That is much more than a university, right? It's a universe of opportunities. And, together with the Humboldt Foundation, the conditions are so good, I mean, that it was simply impossible to, not to accept the offer of joining there. And so our new home is there in Erlangen, and you are all welcome to come anytime. I hope that we will be able to develop there the activity that we have developed, in Madrid, in Bilbao, in Benasque, in Chile, in many other places. Well, now you have a new home for all of you, and this is in Erlangen. Thank you. Thank you again. Gracias, Carlos.
Thank you to you, Enrique. So we still have some 15 minutes before starting our real meeting. And if someone of you among the people participants would like to say something about, for example, this period in Paris 6 during the last 2 decades of the last century, which were real golden years for all of us, maybe you can do it. Huh? So the microphones can be opened to all of those who want to say something now. I see here Eve Meyer.
Hola.
Hi, Eve. How are you?
Fine. Estoy bien. Estoy perfecto.
Thank you very much for speaking Spanish.
No, but tendré que hablar en inglés por mi charla. No la daré en castellano.
Okay. So in case nobody wants to add something, we can start with our, okay, Gunther. Gunther,
Well,
you want to say something?
Yes,
Okay.
I want to say something because I realized that unfortunately our university leadership wasn't able to come today because Wednesday is the day for all the meetings. So I take the opportunity, you know, as retired vice president for research to say a few words. So at FAU, we are extremely proud to have received Enrique in 2019 for the prestigious Humboldt professorship, which is the highest award in Germany that you can possibly have. Also, previously, we had him as a Humboldt awardee, so the Humboldt Science Award is also a prestigious award. And before that, even in 2015, just when I became vice president for internationalization at that time, he became FAU ambassador. And so he is taking the logo and the contents, as he mentioned this in a few sentences, into the world, and we are extremely proud to have him. And I personally, I know him also since '87. I think Enrique, we met in this fantastic and legendary conference that Alfredo Bermudez at that time organized in Santiago de Compostela. And it was an orgy, right? I mean, the dinner we all remember well, I think, and also it was, of course, scientifically a great, very great impact that we both, I think, experienced there. So thank you, Carlos, for taking this fantastic opportunity to receive Enrique for his 60th birthday. We did a little bit at FAU, but not in this, of course, in this framework. And thank you to all of you to attain this.
Thanks to you, Gunther. So we have two people here that have raised their hands. First, Jaime Ortega.
Yes, hello, Carlos. Thanks for your hard work. It's great to be here. I want to say only thanks, Enrique, for this years of friendship, for this year of mathematics together. I'm one of the most old students from the group of estimados. I'm one of the estimados group, the old student of PhD in Complutense. And I have only good remembers of this time in Madrid and in Bilbao, in several places. And I hope to see you soon personally. And this will be a very beautiful party for all. And thanks for being part of this party only. And regards, Enrique. You are a good friend. Thanks.
Thanks to
Gracias,
you, Jaime.
Jaime. Gracias.
We also have here Rajesh Mahavedan, who would like to say something to Enrique.
First of all, I hope you hear me. You?
Yes, perfectly.
Yeah. First of all, very happy birthday to Enrique's happy 60th and many more happy years to come, and active research especially, and good times with your family. So there were many happy moments I passed in the company of Enrique, especially in the conferences which Enrique organized in Benasque. It was a moment to meet people and exchange ideas. And so actually, it's these conferences also some sense reflect Enrique's personality, because I mean, he's a powerhouse of like energy and meaning ideas. And so these kind of contagious and spreads to other people. And I wish I had energy like him. I mean, so it's the only aspiration I can have. And so again, so also, I mean, I enjoyed very much the football matches I played with him. And so, okay, so all the best.
Many thanks, Rajat.
Yeah.
So I see also that Mahatmadi has raised his hand. So
yes, yeah, thank you very much. I want to say a few words about, if you know everyone in the world, you have two homes. Enrique, the first home is Spain, and his second home is Puerto Rico, where his wife is from Puerto Rico. I get the opportunity to meet Enrique in Puerto Rico, and since then, we've become very good friends, good collaborators. And before that, I did my PhD in semi-group theory, and while evolution equation, I didn't know anything about control theory. And since 10 years, every year Enrique came to Puerto Rico, Enrique said, okay, he introduced me to control theory. And the last 10 years, all my papers are based on control theory. And only because of Enrique. I'm really thankful also you, Carlos Conca, and that knows that even if I may be the last one who knows Enrique, we are now best friends and best collaborator. And every year, since 7, 8 years, every year I meet Enrique, he travels to Puerto Rico or I go to Spain. We are really good. And thanks Enrique for putting me in control theory. That helped me a lot to survive in the United States. Thanks, Enrique.
Thanks to you, Mahatmadi. Very emotional words. So I think that we can now start with our conferences. And the first speaker, we have the privilege to receive Professor Jean-Michel Coron, University of Pierre-Marie Curie. Jean-Michel was a former student of Hein Precis. At the beginning of his career, he started doing research in nonlinear functional analysis, but sometime after that, he started working on control theory, where he is today one of the most prominent experts in the world. And the title of his talk, his conference, will be Abstraction to a Small-Time Local Controllability on a KDV Control System. So, Jean-Michel, please go ahead.
Thanks, Carlos, for the introduction. First, I want to say that it's a great pleasure and great honor for me to have been invited to give this talk in honor of Enrique. Enrique has made numerous pioneer contributions which has strongly influenced the works of many people, and in particular me, as we are going to see. In fact, it's already thanks to him that I moved to control theory. I listened to some of his talks, and I was very impressed by the subject. So, as mentioned by Carlos, the subject of this talk is about obstruction to small-time local controllability of a KDV control system. So the outline is here. First, I will present our results. It's a joint work with Armand Koenig and Ohamin Nguyen. And then I will present some prior obstruction to small-time local controllability. And finally, I will give some insight about the proof of the obstruction to small time local controllability. So let us start with the statement of the obstruction. So the starting point is a pioneer work by Enrique Zuazua about the null controllability of some semi-linear equation, very general, in fact, semi-linearity equation. In this paper, the two Enrique considers semi-linearity equation given by 1 with the usual notation, and you have a part of the domain which is called small omega, on which you have the control. And about the nonlinearity f of y, they assume that they have this sticky rate at infinity. And there are remarkable points in these works. They prove the global null controllability in small time. Global, which means that the result is for any initial data. So this is remarkable. And the other point is that you get the null controllability in arbitrary time. So this is also very impressive. And finally, I want to mention that with the type of nonlinearity which are considered in this very important paper, you may have blow up in finite time if you don't have any control. That is, if you take u equals 0, there are many initial data for some f satisfying 2, such that you have blow up in finite time. So this is a pioneer work for which you can avoid the blow up thanks to the control. And this is really a masterpiece. So maybe I will give some insight on the proof, which has been very influential. For simplicity, let us assume that f of 0 is equal to 0 and define g of y is equal to f of y divided by y. So you start from some initial data which is given, y0, and you want to construct a control such that you can move to 0 at time capital T. And they construct the control by showing the existence of a fixed point to the map y gives z, where z is a solution of the linear equation 3, where g of y is a potential, and the control is u. So it is known that this linear PDE is controllable in arbitrary small time. So you fix the time, and there is a u such that if you start at y0 for z, then you arrive at time capital T at 0. And they choose for you the best u, that is the u which is minimizing the L2 cost, for example. It's not mandatory. You can find some other property. And in order to prove the existence of a fixed point, they give a very important estimate on the cost of the null controllability of the linear equation 3, where you have this potential g of y, which depends on x and time. So this is really a very important work. So, of course, it's difficult to compete with this this remarkable result. So we move in some other direction. Instead of positive result, we look for obstruction to controllability. We are also dealing only with a local result. And we are interested in the case where the linearized system is not controllable. And also in the case where the nonlinear term is going to give some new phenomena. So we start with the control system that we want to study. It's a system which has been introduced by Lionel Rosé in 1997. This is a KDV control system. So you have the equation for the first one is the KDV equation, yt plus yx plus y triple x plus yx is equal to 0. X is between 0 and L, and the time is between 0 and t. We have the boundary conditions, so you must have 3 boundary conditions. The first 2 are the Dirichlet boundary condition. And then for the last condition, you have the control. Yx of TL is equal to u of t. U of t is a control, and the state is the function y at time t, which belongs to L2 of 0L. And you want to study the controllability of this equation. So we start with a local result, and then the idea is to linearize the system. This is what it was doing Lionel in 1997. He considers a linearized equation, so you forget the term yx, and you get the equation 5. And he proves that this equation is controllable, this linear equation is controllable for any t, if and only if L is not critical, in the sense that L does not belong to the set N, which is defined in 6. And moreover, he proves that in the case where the linearized system is not controllable, the part that you cannot control with the linearized system is a linear space, of course, but that we are going to call M. But this linear space is of finite dimension. So this is very interesting result. And from that, he succeeds to get the small time local controllability. That is the local controllability for any time t. What does that mean? It means that you have this 0, and the local controllability means that for any ball of reduced epsilon, this is for the state space. Of course, the norm is very important. There is another ball, a smaller one, such that if you have two states in the smaller ball, the blue one, then you can move from the first state y0 to the second state by using a control which is less than epsilon for some suitable norm. So this is a problem of local controllability in time t. And Lionel Rosier, using his result on the linearized system, get by some inverse mapping theorem that the KTV control system is locally controllable for any positive time. So this is a small time local controllability. Everything is small. The time, the state, and the control are small for suitable norms. And the notion of smallness depends a lot on the order. So what happened now if the length is critical? So I proved with Emmanuel Crépeau in 2004 that if the dimension of M is equal to 1, M is the linear space which is not controllable by the linearized control system, then our system is again small time locally controllable. And there are cases where the dimension is equal to 1, for example, L equal to pi. So it remains open the case where the dimension is larger than 1, and that was done by Eduardo Serpa and Emmanuel Crépeau later on. They prove that if the time is large enough, then you have the local controllability of the nonlinear control system, thanks to the nonlinear term. The linear system is not controllable, but the nonlinear terms give you the controllability. And the proof relies on some power expansion. So you look to the order 1, you get the linearized control system. Then you have the order 2, you do some expansion, you have the order 2, the order 3, and so on. And roughly speaking, the idea is that, for example, if for the order 2, you have the controllability, then the nonlinear system is indeed locally controllable. And the fact that this is for the dimension M is equal to 1, you have to go to the order 3. This is the order 3 which gives something, the order 2 gives nothing. This is from this is because the order is odd that you can get the small time local controllability. When the order is 2, it was not clear if it is small time locally controllable. We know it's locally controllable if the time is large enough. But what about small time local controllability? This is the question. If you assume that the dimension of M is larger than 1, is it true that for every positive time, the control system, the nonlinear control system, is locally controllable in time t? And we give a negative answer recently with Armand Koenig and Waymin Nguyen under some extra assumption. We assume that the length is critical, so it's given by 8, but you have some other assumption. You assume that 2k plus L is not a multiple of 3. So it implies that the dimension is larger than, dimension of M is larger than 1, but it's not equivalent. It's a more restrictive assumption. Then we prove that this then the control system is not small time locally controllable for some norms for the control and the data. For the control, this is the H1 norm, and for the data, the initial datum, this is H3 norm. That is, you cannot move if you have, even if a state is very small, you cannot move if the time is too small, you cannot move to 0, for example. It's not null controllable in small time. So some problems are still open. You see, we have some stronger norm in our result. So for example, the control is in H1, and in the result by Lionel, the control is only in L2, and the state also is in H3, while for the Lionel result, the state is in L2. So what happened for this natural space, that is the state is in L2 and the control is in L2, we do not know. There is also the problem of our assumption, 2 times k plus l is not a multiple of 3. This is a stronger assumption that the dimension of m is larger than 1. So the natural question is the condition dimension of m larger than 1, is it a sufficient condition to get an obstruction to the small time local controllability? And the next open problem, we know that for some value of k and l, the control system is not controllable in small time. What is the minimal time for local controllability? This is the last open problem that I would like to mention. Some other example. This is the water tank control system. It's a system which has been introduced by Dubois, Petit, and Rouchon in 1999. The modelization is through the Saint-Venant equation. And you assume that the control is the force that you apply to the water tank. So there is a natural question, which is here. You start the water tank, it has some position. The level of the water is horizontal. The speed, every speed is equal to 0. The speed of the water and the speed of the tank are 0. And you want to arrive, this is the initial state, and the target, the situation where you want to arrive, it's almost the same, except that the water tank has moved a little bit. Is it possible to make this motion? For the linearized control system, it will prove by Dubois, Petit, and Rouchon that if the time t is larger than square root of L times HE G, G is the gravity constant, L is the length of the tank, and HE is the height of the water at the equilibrium. This condition is sufficient to imply that you can do this previous motion, steady state motion, for any time which satisfies this property 10. So you may ask for the linear system. You may ask, is it working also for the non-linear system? And the answer is no, as we proved recently with Armand Koenig, Wymin, and Guyel. We need more time to do this motion. So this is an example where you have a motion that you can do for the linear system, but you cannot do it for the non-linear system, at least if the time is too small. You can make it for large time. That was what I proved in 2002. But you see a difference between the linear situation, where you can do some motion in some fixed time, and you cannot do the same motion in the same amount of time for the non-linear system. So there was some prior obstruction to small time local controllability for partial differential equations that I would like to present now. The first one is, again, suggested by Pierre Rouchon. This is a quantum particle, which is in a moving box. So you have the wave function psi. It satisfies the Schrödinger equation. And this is the state. Now the state space is not L2, but you have to, it's a sphere. The norm of psi in L2 is equal to 1. So we are working on a sphere. And an equilibrium is the first eigenvalue. It's not exactly equilibrium because you have to multiply if the eigenvalue is lambda 1. The trajectory is phi 1 exponential minus I lambda 1t. And the natural question for local null controllability, we start with something which is close to this function. Is it possible to move to this phi 1 exactly? And there is the same problem as for the water tank. You start with a box which is at some place, and the initial data is phi 1, and you want to arrive to exponential minus I lambda 1t, phi 1, but with a box which has moved a little bit. And again, for the linearized, and there is also some global result. You can move for the first eigenvalue to the second one, for example. And what is interesting is again that the small time local controllability, the small time steady state motion is possible for the case of the linear system, but it's not possible for the nonlinear system. We need more time to do that. There are also some results about global and local controllability in large time, in particular by Karine Bochard and Nersessian. But I want to present you the obstruction to small time local controllability around phi 1. So I introduce some notation. X is between -1 and 1. D is the position of the box. Psi is a wave function. And you assume that the control is small, because we are studying small time locally controllable, which means that everything is small. The time is small, the control is small, and the state is close to phi1 exponential I lambda 1t, which is psi1. And then you have the control system, which is given by the equation 12. The u of t is the control. And you have the position of the box, which is given by d. The speed of the box is s. And so we have this equation. There is a part which is a PD equation, but there is a part which is ordinary differential equations. They are coupled. And you want to prove that you have some obstruction to small time local controllability. So we define theta in 17, which is here. And then you define this V of t. So we do some computation. And the point is that V of t, you can show it's given also by 18, where V0 of tau is given later on. And then there is a sign. That is, if you look to, you see you have S of t, V0 of tau, but V0 of tau is like S of tau. So you have something like, which is like S of tau square, which means that you have a sign for V. And in fact, you can prove that if the time is too small, the real part of V has to be positive. And in fact, it is strictly positive if you move a little bit. If you move a little bit, the V is going to be strictly positive, which prevents you to get the local controllability. You have a sign. Something is moving in the bad direction. So it is something which is very classical for control system in finite dimension. In order to prove that the system is not controllable, you prove that you can move in some direction, but not in the opposite. You are living in a half space. So there is also some nice result due to Frédéric Marbach in 2018 for a control system introduced by Sergio Guerrero. It's a Burger's control system, and the control is U of t, which does not depend on x. And Frédéric Marbach proved in 2018 that this system is not small time locally controllable. There is an interesting problem: is it large time locally controllable? We really don't know for the moment. And the proof by Marbach relies on very interesting tools, scaling, power series expansion as the positive result for local controllability of the KdV equation, and new quadratic estimate which give you that, again, there is some quantity such that if you move, it's going to be positive. And the fact that it is positive implies that it's not small time locally controllable. It's not locally controllable. There are some other examples, the Schrödinger equation with bilinear control by Karine Bochard and Morgan Morancé, and some nonlinear parabolic equation by Karine Bochard and Frédéric Marbach. And in all of these results, in order to prove that you do not have small time local controllability, you prove that if the time is too small, then the state is going to be in a half space. Of course, you have, so that is something is going to be positive. So, of course, the difficulty is to find these things. This is a general strategy, but to do it for a specific situation can be very complicated. Of course, when you give a talk, you have to explain why your result is more difficult to get than the previous one. So this is a slide on this. The first point is that we are dealing with boundary controls. And boundary control usually is more complicated for the obstruction to small time local controllability, because, for example, in finite dimension, there are many results which gives you some obstruction to small time local controllability, which relies on iterated Lie bracket. But we know that iterated Lie bracket, when you have boundary control, it's difficult to understand what it is. And when you understand what it is, in fact, you can prove usually that they are not in the state space. The direction given by the Lie bracket are not in the state space. There are some distributions that are not in L2, for example, in the case we are considering. And also, you cannot perform the change of time scale introduced by Frédéric Marbach, because this change of time scale is going to introduce a boundary layer. And the boundary layers in the case of the Burger's control system can be handled by using the maximum principle. And in the case of the KdV equations, there is no maximum principle, so you cannot use this method. Moreover, it's better to not use this method if you can make it, because usually it gives some better estimate about the obstruction of about the time for the obstruction of small time local controllability. And the next point is that if you look to the linear system, forget the control, then the operator is neither self-adjoint nor adjoint, and the eigenvalue are complicated, and also the eigenfunctions. So what are the main steps of the proof to small-time local controllability of our result? I would like to present the idea on a very simple example. You consider a system in finite dimension. This is system 22. We have the state y1, y2, y3 is in R3, and the control is a scalar control. It's U. And the dynamics is given by y1 dot is equal to U, y2 dot is equal to y3, y3 dot is equal to minus y2 plus 2 times y1 U. So the state is of dimension 3, the control is of dimension 1. You want to study the local controllability of this system. So when you want to study the local controllability, you start with a linearization. It's like when you have a map from RP to RP, you want to see if it is locally surjective, you just linearize. So we do the same. We linearize and we get y1 dot is equal to U, y2 dot is equal to y3, and concerning y3 dot, the term, the quadratic term just disappears. So you get y3 dot is equal to minus y2. So this control system, the linearized control system, is clearly not controllable. It's not controllable because the control has no effect on the dynamics of y2 and y3. For example, if y2 and y3 at the beginning are not 0, they will not be equal to 0 for all time, in fact, whatever we do with the control U. You can prove that this system, the nonlinear system 22, and I will go back later on about the time, is controllable in large time. But what about small time local controllability? For this system, the answer is easy to get because you can use Duhamel's formula and you can more or less explicitly compute the solution. So you get 24, y2 of t is equal to the integral from 0 to capital T, cosine capital T minus t, y1 square dt. And you can get also equation 25. So, and the first equation gives you that y2 dot, y2 of capital T is larger than 0, is non-negative if the time, if you go back to the expression, if the time is between 0 and pi divided by 2. And the other equation about y3 gives you that if y1 of t is equal to 0, then y3 of capital T is less or equal than 0 if the time is between 0 and pi. You see, if you go back to 25, you easily get that. So you see that the system is not small time locally controllable. And in fact, equation 26 shows you that you cannot locally control the system if the time is between 0 and pi divided by 2. And 27 gives you that you cannot control the system if the time is between 0 and pi, even locally. And also, in fact, you may wonder what happens if you have perturbation of this control system. So let me go back to the system. You see, y1 and u, they have the same size. y2 and y3 have the same size, but y2, which is also like y3, it's a quadratic term because it looks like y1 u, and u is like y1. So in some sense, if you do a perturbation of the first equation, y1 dot is equal to u plus y1 square. y1 square is smaller, much smaller than u, okay? So it's going to work again. For the second equation, for example, y2 dot equal to y3, you do the perturbation by y2 dot is equal to y3 plus, let's say, y1 to the cube. It's again a perturbation compared to y3. And you can get also the fact that it's not small time locally controllable. And this, and so on. So this, you can do that by showing the following inequality. For example, the one which is the most interesting one, 29. For any capital T between 0 and pi, there exists delta such that y1 of t is equal to 0, implies that y3 of t not only is less or equal than 0, but you have some estimate in terms of u. And this is really what we are going to do for the KDB equation. We are going to try to get some estimate like 29. So the first step for 29 is to understand what are the controls which allows you for the linearized system to go from 0 to 0. Of course, I should have also mentioned that for this toy model, which is a finite dimensional control system, there are tools in finite dimension which allows you to prove very simply that this system is not small time locally controllable just by computing iterated Lie bracket. There is a necessary condition due to Sussman for small time local controllability, which relies on iterated Lie bracket. You can check that this condition, this necessary condition, is not satisfied. And there is some more general obstruction which has been obtained recently by Karin Bochard and Frédéric Marbach, which are very interesting. But again, iterated Lie bracket, we do not know how to make it work for boundary control, for PDE. So we are looking for something different. So we are looking for the KdV equation to the analogous of 29. So the first step is to understand what are the controls which allows you to move from the linearized system from 0 to 0. And then to do some power series expansion. So let me explain the power series expansion first, maybe. So we have, you expand U in terms of some parameter epsilon. So U is epsilon U1 plus epsilon square U2, and you do the same for Y. So for example, YYX is epsilon square Y1, Y1X, and so on. So if you do the expansion to the order 2, you get two coupled systems, 33 and 34. And roughly speaking, if you can prove that this coupled system is controllable, then you can expect to prove that the nonlinear system, the true nonlinear system, the starting one, the KdV equation with only one control, is in fact small time locally controllable. And that was what was used by Eduardo Serpa, Emmanuel Crépeau, and myself. But the argument was by contradiction. To prove the controllability of 33 and 34, it was more an argument by contradiction. You try to find control such that Y1 is going from 0 to 0 and Y2 is moving in the direction, in some direction of M. But for that, we use some argument by contradiction. And in our work with Armand Koenig and Noël Nguyen, we use another method. We try to really understand in which direction we can move. So we first characterize all the controls U1, such that for the linearized control system, you go from 0 to 0 at time capital T. And this is done by applying the Palais-Wiener's theorem and the Fourier transform with respect to time of the solution Y1. And this is the statement that I'm going to present. So we define Q and P, where the lambda I are the roots of the polynomial given in 35. And with this, you have the result. That is, L is fixed, doesn't need to be critical. T is fixed, and you are looking for U in L2 of minus infinity plus infinity, with support included in 0T, which steers the linearized constant system from 0 at time 0 to 0 at time capital T. And the necessary and sufficient condition is given by this Palais-Wiener condition. Yes, 38 and 39. That is, if you have a U dot, if U is such that you can go from 0 to 0, for example, you have, this is the part that we are going, you have 38 and 39. Now, of course, this is not the end of the story because we want to have this coercivity. We want to have this sign for some quantity, and this is a difficult part in fact. So we assume that we introduce some notation. We assume that the length is given by 40, so the length is critical. You define eta 1, eta 2, and eta 3. P and capital E is a complex number. You define this function phi of x, this function psi of t and x. This function psi of t and x is real. And the key points are here. First, E is not equal to 0 if and only if 2 times k plus L is not a multiple of 3. This is a place where our assumption 2k plus L is not a multiple of 3 is appearing. In particular, if 2 times k plus L is not a multiple of 3, you can prove that psi of 0, psi at time 0, is not 0. Then you can show that psi is a solution of the linearized KdV equation. And it satisfies this strange boundary conditions. That is, there are now 4 boundary conditions, which is a little strange. Psi T0 is equal to psi TL is equal to psi x T0 is equal to psi x TL. So we have 4 boundary conditions instead of 3. But this is the fact that we have these 4 boundary conditions, which tells you that the linearized control system cannot be controllable, because if you have a solution to the linearized control system, if you multiply this solution by psi, integrate from 0 to L, you have a quantity which does not depend on time. And now we are going to see what happened for the order 2. And the estimate that I presented before, the coercivity, is just given by 50. You have this quantity, the left-hand side is more than C times the norm of U, h minus 2/3 to the square. And this is the main step of the proof. Because this quantity, you can see it's a linear quantity with respect to y2. If you do the expansion, we go back to the expansion, you have this equation, the linearized system, which is 33, the expansion to 0 to 2, which is 44. And then you translate the equation, the inequalities I presented before. This is just 55. But 55, the left-hand side of 55 is a linear expression in terms of y2. The left-hand side of 55 is just the left-hand side of 57. So this is now you get the obstruction to small time local controllability for the order 2. But we have also some inequality, and this is very important to have the inequality. So obstruction to the small time local controllability of the order 2, just you take, you want to have y2 t star is equal to 0. So the first term is 0. And then you have a condition which must be satisfied. You have a sign. You have a sign for the initial data. And you see this is linear with respect to y2. And you use the fact that psi 0 of x is not identically equal to 0 to get the obstruction to small time local controllability of the order 2. But the fact that you have some inequality, not only because if you have, for example, for 57, if you have only that the quantity is more or equal than 0, you cannot conclude. You cannot conclude because the order 3 will give something. The order 3 will give something. But the fact that it's larger than c times the norm of u square, h minus 2 divided by 3, prevents you to get the small time local controllability thanks to the order 3. You will get an obstruction to small time local controllability thanks to this inequality 57. And of course, this is not an easy task, but you can do some computation. And this is a place where we need to have some more regularity about the control, in fact. So you get the obstruction to small time local controllability for the KdV equation when 2 times k plus L is not a multiple of 3 for critical length. So in order to conclude, happy birthday, Enrique. And I'm going to stop here. And thank you very much for your attention.
Okay, thank you very much, Jean-Michel, for such a nice talk. So now microphones and the written chat is open for discussion, comments, and of course, questions.
Carlos, can I comment something?
Okay.
Well, let me say hi. Hi, Enrique.
Eduardo.
Well, I'm very happy to see this result, Jean-Michel. This is very impressive. And more than a question, I have a comment, especially directed to young researchers here in the audience, because I remember that we were working on this. We were looking for this result in 2008 with Emmanuel Crepeau under your direction, trying to build these trajectories to get in this space M. It was a happy ending for us. because it was very, very hard. But at that time, I remember that with that contraction that we made of particular solutions, we knew that if we were able to arrive to a good direction in the space M, we can do the whole space, and we always arrive to the bad one. So it was so it's in this kind of conference and life for the researchers, you always see the stories with happy ending, and this is one for you and Armand and Hao-Ming, but it took 12 years. So that's an important signal for all, especially young researchers. So I would like to emphasize that.
Thank you very much, Eduardo. So maybe I could comment a little bit. You see, Eduardo with Emmanuel Crépeau, for example, let's assume that the dimension of M is equal to 2. You can prove by arguing by contradiction that it's possible to enter in M. And then Eduardo Serpa and Emmanuel Crépeau, they just wait a little bit. And then this direction, it moves around the origin. So you can cover all the space. But in order to have this rotation, you need some time. This is why there is some time for small time local contractility. But for example, for the conjecture about what is the best time, maybe the time which is given in general, that is for the case NEK and NEL by Edouard Serpa and Emmanuel Crépeau, maybe it's too long, but it's quite possible that the one that was obtained by Eduardo in the first paper, when the dimension of M is equal to 2, it's reasonable to expect that maybe the time that was obtained for the local controllability by Eduardo, maybe it's the best time, quite possible.
Okay. Is there any other question, comment?
May I ask a question?
Or Professor Chang?
Not Professor, but hello, Jean-Michel. Thank you for your fantastic talk. This is the result that I really appreciate, and I would hope that I would have the chance to get. Sadly, I didn't. So, okay, the question is like, you proved the small time local controllability, and this is a very incredible, but do you have some idea about, can we prove some small time local controllability by use very large control term? So which means,
yeah, that is very, of course, this is very interesting because it's quite possible. You see, in the definition that I gave for small time local controllability, everything is small with a different scale, in fact, but the time is small, the control is small, and the state is small. It does not prevent the problem which is raised by Sheng-Yuan, which is the case where, in fact, maybe you still remain, the state still remain in a small ball, but the control maybe is large. And this is a very interesting problem. Yes, for sure, it's very interesting. I don't know what is the answer, but if we go back to my result, our result, we prove that there exists time t0, there exists some delta, such that but there is this problem of the control which is less than delta. If we do not assume that there is this problem on the size of the control, it's open for the KDB. For some Schrödinger equation with Aubert Tasman and Carrie Bochard, I get some obstruction to small time controllability for any control. But that was very special for KDV. And also, I think that it's not exactly your question because the state is not small. But there is no constraint on the control. And we prove that we do not have the global null controllability, the analogous of the global null controllability in small time, even if it is true for large time. And in this case, there is no constraint, there is no bound on the control in the statement. But this is very special, and for the KDB equation, I don't know what is the answer.
okay, thank you a lot. It's very nice.
Okay, if there is any other question, you can raise your hands.
Can I ask something?
Yes, of course. Enrique, please go.
Merci, Jean-Michel. Merci, Carlos. So Jean-Michel, in those cases where there is a minimal time, then is the system controllable at the minimal time, or so the condition is, or not?
No, probably not. I say minimal time, but it's infimum, in fact. For example, if you look to the toy model, the minimal time is pi, but pi is not working. You have to take pi plus delta.
So pi might not be working.
Yeah.
And are there examples where at the critical time it might work, or?
In finite dimension, I don't know.
Okay.
Probably not. Probably I would say not, because if you can make it maybe for the, I think this is more or less open. That is, if you move a little bit, and it's going to remain. It's not. Of course, I should have mentioned, of course, that the problem of the time for PDE is already important for a linear system, but in the case of finite speed of propagation, here we are looking, for example, where the finite speed of propagation is infinite. But you are right. For example, for just the transport equation, if you look to the null controllability for yx plus yt plus yx at some interval, and you put u of t is the control, you're right. At the time capital T equal L, it's controllable. But I would say for the nonlinear system, the situation might be different. The examples that I know, it's not working for the limiting time.
Okay, so yeah, I mean, I was thinking on, you see these problems we looked with Emmanuel and Loeak. It was a heat equation with non-negative controls. Then when you push the time to be minimum, you get Dirac delta controls, right? So I mean, you achieve the controllability in the minimal time, but at the price of making the control more singular. I mean, it's unbounded.
Yes, you're right. I think if you allow Dirac masses, maybe you're working at the time capital T equal to pi. Yeah.
This will happen. Yeah. Okay. Thank you. Anyhow, very interesting talk indeed. Very much. So yeah, I mean, so what Eduardo said is that it took 12 years to prove this result, right? So this is very encouraging. This is very encouraging for young people, right? So that, I mean, they can never give up before the first 12 years, right? Yeah.
Thank you.
Okay, many thanks, Jean-Michel. So we can congratulate you once again. So thank you very much.
Thank you for the invitation.
Okay, so it's a great pleasure for me to introduce our second speaker today. He is Grégoire Allais, professor at the École Polytechnique of Paris, but he has a very similar position at the University Pierre and Marie Curie. At the beginning of his career, he was a specialist in homogenization, multi-scaled analysis. He was at the base of one of the most celebrated methods in periodic homogenization, the two-scale convergence method. And today he is also a specialist in shape and optimal structure optimization. And the title of his talk conference will be Shape Optimization with Imperfect Interfaces. So, Greg, you can go ahead.
Okay, thank you very much for the introduction, and thank you also for inviting me. It's a great pleasure. Can you see my slides? Good, excellent. And I hope you can hear me well. So it's a great pleasure to participate to this birthday of Enrique, a long friend. So indeed, I'm going to talk about a topic in shape and topology optimization. And I choose this topic because I did it with a Chilean postdoc, Matthias Godoy, that some of you know, and also together with my colleague, assistant professor here at Polytechnique, Benjamin Bogosel. So the content of my talk is following. I will first discuss the motivation of this work, which has something to do with so-called additive manufacturing, and more precisely the question of supports in additive manufacturing. Then I will first discuss the case of a two-phase design, optimal design problem in thermal conduction, because things are a little bit simpler. And then I will go in a third section to the case of the elasticity, linearized elasticity system for supports. And then I will finish with some conclusion. Let me add that this work has been funded by a project which is called the SOFIA project, which is a project funded by the French government, which has many partners. So the CNRS for the academic side, but then some companies like Adobe, Michelin, Safran, and some other ones. Good. So what is additive manufacturing? You all heard probably about this. This is a way of building structure layer by layer. Here I'm talking mostly about metallic additive manufacturing. And one of the main interests of this new way of building a structure is that you can have very complicated shape and topology. So here, I don't know if you see my mouse. I don't know if the mouse can be seen. Anyway, at the bottom of the slide, you can see two structures with very complicated topologies that have been built by additive manufacturing, and that will be very hard to build with other techniques like molding or milling. Okay, so here is a principle of powder bed metallic additive manufacturing. Typically, you have a build platform. On this build platform, at every layer, there is a roller that put one layer of metallic powder, and then you have a laser beam that travel above this layer of metallic powder, and that will melt this powder where you want to build something, and will not melt the rest of the powder. And once you have melted one layer, you put another layer of powder, and so on and so forth. So it is a process that takes some time, but in the end, so you see here a picture where the dark gray is the metallic powder which has been already melted. You clearly see the spot of the laser beam, and the light gray is still the powder. And at the end of the process, you just remove the powder and you have your structure which pops up. Okay, good. So also, it is very convenient, and many industries are interested in using it. There are still some constraints. In particular, if you want to build, for example, an horizontal beam, this horizontal beam will be carried by powder, and powder is, is very fragile. So the beam will be probably a little bit bended when you melt it. So it's very hard to build a structure which have so-called enverang surfaces, so which have surfaces which are almost horizontal, because they will, kind of dig into the powder when you melt it. Then, of course, when you melt it, you bring a lot of heat, and then in the melted part, what remains after the passage of the laser beam is some thermal residual stresses, and so the structure will be deformed by cooling down, because you have some thermal residual stresses that stay inside. In particular, you can have an upper bending of the structure that will probably stop the roller that put a new layer of powder if it has bent too much. Okay, so to accommodate those constraints, there is a trick of using so-called supports, and the role of the support is to support inclined surfaces, horizontal surfaces, if you want, and then also to fix the shape that you want to build to the base plate at the bottom layer, which is fixed at the machine, and so the support can fix the structure, and so it will not deform too much under the effect of thermal residual stresses. So here you have a picture of one structure, and you see below the structure which is inclined, you see supports which are built in metal, with the same metal, and the role of those supports is just to support the structure. At the end, when you have built your structure with the supports, you remove the supports. So of course, because you remove the supports, this is some metallic powder which is lost. So you want to have some support, but the minimal amount of it, because building takes some time and costs some money. So you want to use support if necessary, but in a minimal amount. So here are two examples of support. Here, this is a picture of my PhD student, Martin Beer, who is doing his PhD at Safran. And so he has built a small, this is a very small sample, something like 5 centimeters long, MBB beam. And you can see on the right, supports which are not very well designed, by the way. And actually the supports, the goal of this picture is to show you that these supports are very thin and, they are in some sense pre-cut. You have some kind of a collection of holes close to the connection with the structure so that it will be easy to remove. Okay. Another example of supports is here. That's a picture that I've taken on the webpage of Magix. Magix is a software that allows you to design supports. And you see that the support have a kind of a tree or branching structure when they connect to the structure. You see, because you want to remove them. So you want to have very thin bars in the support so that you can cut them very easily with any kind of tools, so you can remove the support easily. So the purpose of those two examples, the example 1 here and the example 2, is just to show you that the interface between the support and the structure that you want to build is very complicated. It's made on purpose. Either you have a tree structure or you have a dotted line of small holes for easing the separation of the support from the structure. So if you want to predict the effect of supports by doing some finite element simulation, it will require a very fine mesh, but you don't care about all the details. So what you want to do is, in some sense, do some kind of homogenization purposes, some kind of homogenization process, because you want to go very quickly in the simulation of those supports. So actually, what we are going to do is to model this kind of detailed interface between the support and the structure by a model of imperfect interface. Okay, so I'm not doing any homogenization here. I assume that the details of the small branching of the supports close to the structure will be represented by an imperfect interface. And I will explain this model of imperfect interface first in the case of thermal diffusion and then later on in the case of mechanical system. Good. So now let me forget about the motivation for the moment and let me consider a domain where you have two phases which are occupying two subdomains, omega 1 and omega 2. And those two subdomains are separated by an interface gamma. So there are two possible configurations. The first and simple one is when omega 1 is an island inside omega 2. And then gamma, the interface, is a closed surface, okay, or a closed line in the plane. And the second configuration, which is actually more relevant, but a little bit more complicated, is when the total domain, which is a union on omega 1 and omega 2, is cut in two pieces or several pieces by the interface gamma. So that means that the interface gamma is not a closed surface, but the interface gamma touches the boundary of the exterior boundary of the total domain. Okay. So now the model will be that this interface gamma is imperfect, meaning that the temperature in this thermal conduction model will be discontinuous through the interface gamma. But the normal heat flux, of course, is continuous by conservation of energy. And this normal heat flux will be proportional to the jump of temperature, like a Fourier boundary condition, if you want. So the complete model is here. So the temperature will be called U. Okay, it is made of two functions, U1 in omega 1 and U2 in omega 2. And I introduce the characteristic function chi1 for omega 1. So it's 1 in omega 1 and 0 outside, and chi2, which is 1 inside omega 2 and 0 outside. Okay, and so the temperature is made of two functions which are not continuous at the interface gamma. So in every subdomain omega I, you solve the heat equation with some constant thermal conductivity AI, with a given source term F. So the source term F is globally defined over the union of omega 1 and omega 2. And at the interface gamma between the two subdomains, you have continuity of the heat flux, normal heat flux. And then this normal heat flux is proportional with a constant of proportionality that I call alpha to the jump U2 minus U1. Okay, and alpha is positive because I choose the orientation U1 outside from omega 1, and so the jump is U2 minus U1. So the convention of the jump between U2 and U1 and the normal U1 is the right one, so that you get alpha that can be interpreted as a conductance of the interface. The inverse of alpha is a resistance, a thermal resistance of the interface. And then usual boundary condition on the exterior boundary of the domain that I call capital D, which is omega 1 union omega 2. Of course, when alpha is plus infinity, that will force U2 to be equal to U1 on the interface, and then you recover the classical transmission condition at an interface. But then if alpha has a finite value, this is an imperfect interface, the temperature is not continuous, and you have some resistance, thermal resistance, which is the inverse of alpha at the interface. Good. So of course, this is a very standard model. You can find it in many places in the literature. And then you have a standard variational formulation, which is the sum of the two variational formulation in omega 1 and omega 2. Then at the interface gamma, you have a bilinear form that involves the product of the jump of the unknown u and the jump of the test function. And both the unknown u and the test function v belongs to a space H1b, B for broken. That means that this is a set of function u in L2 of the global domain capital D, and the restriction to omega 1 belongs to H1 of omega 1. The restriction to omega 2 belongs to H1 of omega 2, but there is no continuity of the function u1 and u2 at the interface gamma. So existence of uniqueness is really very classical for this model. Good. And then, of course, the goal is to do some optimization. So the shape is not the variable of optimization. The shape, the interface gamma is the variable of optimization. So actually, I will denote by j of gamma an objective function, which generally speaking could be an integral over the complete domain capital D of j, small j of u, the solution of the state equation, plus an integral carried by the Neumann boundary condition of another function k of u. Small j and small k are smooth functions with some growth at infinity, so that this is well defined. And the problem is to minimize this objective function among all admissible interfaces. Gamma belongs to a set of admissible interfaces with a volume constraint, let's say on one of the phase, let's say omega 1. Okay, good. So it's a very classical optimization problem. And what we want to do is, I don't want to say anything about existence nor uniqueness of solution. I just want to devise a numerical method to do some optimization. And the first goal is to compute a shape derivative, a derivative with respect to the position of the interface. So in the setting of Hadamard, you introduce a displacement vector theta, and you look at perturbation gamma index theta, which are obtained by applying the map identity plus theta, meaning that every point x in gamma is displaced to a new position x plus theta of x, and differentiating in the sense of Hadamard is differentiating with respect to this displacement vector field theta. Okay, so you said that the function j of gamma is shape differentiable. Actually, if j of gamma index theta is differentiable with respect to theta. What does that mean, Fresher differentiable? Well, you build this first order Taylor expansion where the remainder term is small with respect to theta in the W1 infinity norm. So very classical setting. Good. So when we compute this shape derivative or derivative with respect to the position of the interface, we need an adjoint state, and the adjoint state is very classical. I call it P. It satisfies the same type of equation, except that you replace the source term by the derivative of the integrand of the objective function, so minus j prime of ui. You still have the continuity of the normal heat flux. You have the same interface, imperfect interface boundary condition for the adjoint. So the normal heat flux is proportional to the jump of the temperature. And again, because I had one part of the objective function which was carried by gamma n, you have a non-homogeneous, non-band boundary condition on gamma n that depends on k prime of u. So in the sequel, I will always implicitly assume that gamma is smooth enough and that U1, P1, and U2, P2 belongs to H2 in each subdomain. Of course, they are not in H2 globally because they are discontinuous at the interface, but in each subdomain, they belong to H2 so that everything has a meaning when I will compute the shape derivative. And then I have a theorem that gives you the shape derivative. Please don't look at the formula. The formula is absolutely awful. It has absolutely no interest except that I needed to use it in a numerical algorithm. But I just want to tell you that also this formula is awful. To prove it is not very hard, actually. The formula involves jump through the interface, okay? So you have 3 terms in this formula. The first term is carried by the interface. So that's a classical term that you will expect, okay? And it depends only on the normal component. Nu is a normal to this interface gamma. It depends only on the normal component of the displacement vector. So that's the usual part. And then you have 2 additional parts which do not exist if gamma is a closed surface. So if gamma is a closed surface, you only have the first term. But now if gamma touches the boundary of the domain capital D, then when gamma moves, you move also the touching point on the boundary. And so you need to take into account that. And then you have 2 terms, one where you see the tangent vector tau, and another one where you see another tangent vector t, which is not tau. Okay, so tau is tangent to gamma, to the surface gamma, and it's also normal to this boundary of this surface gamma, which is not closed. Okay, now t is different. T is tangent to the boundary of the domain capital D, and it is normal to the boundary of gamma, but it's not tangent to gamma. Okay, so it's a little bit complicated. If I come back to my picture of this setting here, you have one which is tau, which is tangent to the surface gamma or to the line gamma, if you want here. On T is a tangent to the boundary of the global domain capital D. Okay, so that's two different integral terms if gamma is not a closed surface. Good. So the proof, the formula is awful, but the proof is very simple because actually, in the case of the perfect interface, the proof will be more delicate because you have the transmission condition to take into account. Here, the transmission condition, you have no transmission condition because the temperature has a jump. So actually, there is no transmission boundary condition. You just write the variational formulation, you add the objective function, and you just use the standard method proposed by Sea to differentiate this Lagrangian to find the shape derivative. So actually, the proof is really simple. And the fact that on the boundary terms, you get 2 different unit vectors is that because you get 2 different terms which are differentiated on the boundary, one which comes because you differentiate an integral which is in the fixed boundary gamma n, and another one that comes because you differentiate something which is on the integral of gamma, and when gamma moves, you have a component at the endpoint of gamma. Okay, so I don't want to enter into the details, but actually the proof is simpler than in the case of a standard interface condition. Okay, so now we have a shape derivative. So we can do, we can devise an algorithm to do optimization, shape optimization, and there will be 4 ingredients in my algorithmic implementation of this optimization algorithm. First, because I'm moving an interface, I need to, have a method for that. I'm using, no surprise, the level set method for halving the interface. Now, in my motivation, what happened at the interface is really very important. So I'm going to require that the interface is exactly mesh, so my computation will be very precise. In particular, I have something which is discontinuous at the interface, so I want really to compute exactly what happened at the interface. So I'm going to remesh at every iteration of my optimization algorithm. I will remesh the entire domain so that the interface is exactly captured by the mesh. And for that, I'm using a free software, which is called MMG. It was developed by the team of Pascal Frey in Jussieu, and my former PhD student, Charles Daponi. Then there is a small trick for the finite element computation that I will explain, and the finite element computation are done with fruitful++, also developed at Jussieu. And then for the optimization, I use an augmented Lagrangian algorithm because I remember there is a constraint on the volume, so this constraint is taken into account by an augmented Lagrangian algorithm. Excellent. So the level set method, I guess you know that. Here is a picture. The interface is this difference between the light gray and the dark gray. And by definition, the level set is 0 on the interface, negative, let's say, in omega 1, and positive in omega 2. And if the interface moves with normal velocity capital V, a scalar function, the equation for psi is simply d psi over dt plus v modulus of nabla psi equal to 0. But how do you guess this velocity v? Well, you use the shape gradient that you have just computed. And so there is two cases. When gamma is a closed surface not touching the boundary of the domain capital D, then that's easy because the derivative that I have computed is something like an integral over gamma of theta dot n, the normal component of my vector field, n is a normal vector to gamma, times some integrand j that depends on the state u, on the adjoint p that I have introduced. And so you see that if you want to choose theta such that this integral is negative, that means I will go in a direction that minimizes a function capital J. One simple choice will be simply to say that the normal velocity v is exactly theta dot n, and you choose theta dot n to be equal to minus j, which guarantees that the derivatives, the directional derivative, will be negative. Okay. Then it's a little bit more delicate when gamma touch the boundary of the global domain capital D, because in the shape derivative you have terms which are not carried by an integral on gamma, but which are carried, if we are in 3D, on a line, which is the intersection of gamma with the boundary. So then, you know, not only the normal velocity plays a role, you have a normal velocity, but you also have a tangential velocity. And even more than that, you have two different tangential velocities because there were two different tangent vectors. So what we do is instead we compute a vectorial velocity, vec v, you see a v with a small arrow here, and I use a scalar product for some Hilbert space. So in theory, I should choose an Hilbert space, for example, H2, okay, for which I'm sure that in 3D, I have a notion of trace on surfaces and on lines, right? But actually, in numerical practice, I just use a scalar product of H1, and I'm cheating a little bit. So, you know, I'm saying that I have a trace on the line, which is not true for the continuous space, but you can always do that in finite elements. But in some sense, you need to use a small trick to extend your velocity, because your velocity is not only a normal velocity, but also a tangential velocity. I do not go to the details, but you can imagine there are some technical details at this point here. Now, what about the finite implementation? I mean, usually people use standard continuous finite elements, right? And here on the interface, the temperature is discontinuous. So either you go to Galerkin discontinuous finite element, but you know, if you are using a usual package, maybe you don't have discontinuous finite elements. So if you use continuous finite element, here is a small trick. Actually, you introduce two fields, u tilde 1 and u tilde 2, okay, that are computed everywhere in capital D. So usually u1 is restricted to omega 1 and u2 is restricted to omega 2, but here you compute them everywhere. So I wrote the variational formulation where I replace u1 by u tilde 1 and u2 by u tilde 2, right? And the same for the test function. But of course, u1 and u2 appears only in omega 1 and omega 2. And if you want to have a rigidity matrix coming from the finite element, which is invertible, you need to extend it. But no need to extend the bilinear form with a derivative. You just add for example, u tilde v tilde 2 in omega 1, u tilde 1 v tilde 1 in omega 2, and you put a small parameter epsilon. Epsilon does not need to be very small. 10 to the minus 5 typically will do the job. And then you reconstruct the temperature U by taking U tilde 1 in omega 1, U tilde 2 in omega 2. You're making an error of size epsilon, but epsilon is small enough, and you see it's enough. And of course, there is no continuity of U tilde 1 and U tilde 2 at gamma. So for sure, you don't have continuity. Well, if you were using standard finite element, you will have the continuity built in. So you cannot do that. So that's a way of doing it with standard finite elements. Okay, so let me show you some examples. And let me start with a very classical example, which is a so-called radiator. So it's a square domain here. You have a unit heat flux on the upper boundary here. At the two lower corners, you see the dashed line here. You have a cold end, that is a Dirichlet, homogeneous Dirichlet boundary condition. All other boundaries are adiabatic, that is homogeneous Neumann boundary condition, and there is no source term inside. So more or less, you're putting temperature, heat flux, if you want, at the top, and the heat can be extracted by the two lower corners, and you mix a good conductor, A2, which has conductivity 1, and a bad conductor, A1, which has conductivity 0.01. And what you want to minimize is so-called thermal compliance, so that the integral on the top boundary gamma n of the heat flux that you impose, which is 1, multiplied by the temperature. Okay, so that's equivalent to the thermal store energy inside your square domain D. And you want to minimize this with a volume constraint of 50% for each conductor. So you want to get, in some sense, the best arrangement of the two phases so that you dissipate thermal energy as much as possible. So here is the solution that you obtain with a perfect interface. So I have an initialization. The good conductor is the white phase. The dark phase is the bad conductor. And you see that starting from this initialization, what you get is some kind of fibers of the good conductors that comes from the top and brings the heat to the two lower corners where the heat can escape. Okay, so that's the optimal radiator in some sense. So this was done with a perfect interface, so continuity of the temperature. Now, what do you obtain? Just to tell you how well it converges. You see, because I started with a configuration which has not the right volume, it takes some time that you convert to the right volume, and the cost, that is the thermal compliance, is minimized in the end. But of course, it first increase because you first reach the correct volume, and so when you have more good conductor, the thermal compliance will be smaller. So everything is smooth in the convergence. That's what is important to see. Now let's see what you get with an imperfect interface. The perfect interface is still on the left, and on the right you see the imperfect interface with a conductance of 1. But actually, if I had put any other value of alpha, you will get almost the same topology, the same shape. Okay, so this is a very deceiving example. Just want to show you one case where changing the value of alpha, going from a perfect interface to an imperfect interface, does not change the design. But of course, all the coming result will show you that in the other cases, there will be a difference between a perfect and an imperfect interface. So let me come to another very classical test case, which is a so-called heat extraction test case. Again, my domain is a unit square. I have a bulk source term F equal to 10 everywhere. All boundaries are adiabatic, that is homogeneous Neumann, except a very small part of the bottom boundary at the bottom where you have a homogeneous Dirichlet boundary condition. So again, you mix two conductors, A1, which is a good conductor, A2, which is a bad conductor. And so you want to minimize the so-called thermal compliance, because I have a constant source term. So this function J of gamma is exactly the equivalent of the thermal compliance or the thermal store energy in the domain. You want to minimize it. That is, you want to find the best configuration of the two phases so that heat is extracted as much as possible. Again, this is a self-adjoint problem, and I have a volume constraint, so I have only 20% of the good conductor and 80% of the bad conductor. So here are three optimal design obtained with our algorithm. On the left, it's alpha equal to plus infinity, meaning perfect interface. In the middle, alpha equal to 1, and in the right, alpha equal to 0.1. So that means that going from left to right, the interface is more and more imperfect. The resistance of the interface is bigger and bigger. And so you see that the designs are different. And actually, you see that when the resistance of the interface is large, you want to have an interface which is with a smaller area. And actually, if you compute the length, because we are in 2D of the interface, on the left, the length is 12. In the middle, it's something like 6. And on the right, it's a little bit less than 6. So the length of the interface is decreasing because you pay a cost of the interface resistance when you minimize the thermal compliance. So increasing the resistance of the interface means that you want to decrease the length of the interface, but still, you still want to have, kind of branches, because a good conductor, which is a white one here, carries away the heat produced by the source term up to the exit, the cold end, which is a small Dirichlet boundary condition at the bottom. So you see a very important role of the imperfect interface in the optimal design if you change the value of alpha. So now that I have explained all the details in the thermal case, let me go to the mechanical case, and let me slightly change the setting, right? Because in the mechanical setting, my two faces are actually two different structure. Omega is a structure that you want to build. In my picture, it's a red structure. You recognize a cantilever structure, which is a classical test case in topology optimization. So I want to build this red structure. And then the other phase is a so-called support that I call S, like support, which are in blue. And those supports are supposed to support the parts of this red structure, which are almost horizontal, because remember, I told you that in additive manufacturing, it's hard to build things which are close to horizontal. So you see that those blue supports support more or less the almost horizontal part of my red structure. So what are the slight change? Before, in the thermal case, I was optimizing the interface. But actually here, I don't want to touch to the red structure. Omega is fixed. Okay, so omega is fixed, meaning that the interface is sliding or moving tangentially on the boundary of my fixed structure, small omega. Okay, so actually the optimization variable is rather S than gamma. Gamma, if you want, is the intersection of the boundary of S and the boundary of small omega. But gamma is must be carried by d omega by definition, because the support omega. So actually, I'm not moving normally gamma. I'm just moving tangentially. So it's a bit different. And then in the previous case, I showed you an example where the thermal conduction was different in the two subdomains. Here, I'm building the support with the same type of material. So actually, the material parameters are the same between omega and S. I will not play with different material parameters. I could, but I'm not going to do that for practical reasons. So omega and S are made with the same material. Okay. But still, there are some ideas. In particular, I still have a model with an imperfect interface. So I'm solving minus divergence sigma of u. Sigma of u is a stress tensor equal to F some applied load in both small omega and S separately. Sigma of u is a usual stress tensor, so it's computed from the strain tensor E of u. E of u is a symmetrized gradient. U is a vector valued unknown, which is a displacement. And I have the Lamé parameters mu and lambda as usual. Then on some part of the structure gamma d, on the boundary of the structure gamma d, the structure is clamped, so u is equal to 0. Typically, that will be at the bottom of my structure because I have the base plate and I'm building vertically my structure. On the other boundaries of the global domain, I have a Neumann homogeneous boundary condition. And then on the interface between the support and the structure, I have continuity of the normal stress tensor. So the jump of sigma u times nu, the normal vector, is 0. But I have a jump in the displacement vector. And so the the jump in the displacement vector is equal to some matrix capital R times the vector, which is obtained by sigma u times nu, the normal. Okay, and this matrix R is a compliance or the inverse of the rigidity of the interface, and it is characterized by two coefficients, alpha and beta. You have beta, which is compliance in the normal direction, mu is a normal vector, and you have alpha, which is the compliance in the tangential direction. So, of course, it's isotropic in the tangential direction. There is no reason to have something anisotropic, but it could be not isotropic between normal direction and tangential direction. So I have two numbers, alpha and beta, which are like inverse Lamé tensor, if you want, Lamé coefficient, sorry. So the inverse of alpha and beta are rigidities associated to the interface. Okay, so again, imperfect interfaces on the boundary. So again, this is a standard model of imperfect interfaces in mechanics. So I'm going to minimize the compliance. So I'm not looking at any objective function. That's the compliance that I'm looking at, right? And I'm minimizing for supports that belongs to a fixed box capital D, where of course you have the structure small omega, which is there. So the support cannot overlap on the structure. So the support must belong to D minus small omega. And I have a volume constraint on the support because I don't want to use too much material to build my support. So remember, that gamma, the interface in some sense, is constrained to belong to the boundary of my structure. So actually, it does not move freely. So in some sense, the real design variable is capital S. It's not really the interface gamma. So again, you can compute a shape derivative. I skip all details because you've seen some details in the thermal case. And what is really important is that now there is, in some sense, a third phase. I didn't say that. There is a kind of a third phase, this white phase here, which is void. You have the capital D is my rectangle, small omega is the red part, the support S is the blue, and then you have voids among what remains, which is not support outside from the structure small omega. So actually, when you move the support, when you deform the support, you still have on the boundary of the support, but not on the boundary of the structure, a normal component of my vector field theta, and then you have something, okay, which is a derivative of the compliance objective function. And of course, at the endpoints, in 2D or at the line, which are the boundary of the interface between the supports and the structure, so it's a line in 3D, it's points in 2D, you have some terms that come from the imperfect interface term. And so you see that that's a tangential component of the vector theta that plays a role, where tau, again, is a tangent vector to the boundary of omega, but also normal to the line, which is the boundary of my interface gamma. Okay, so a little bit delicate. You move away from the structure, you move the support in the normal direction, but when the support touch the structure, you move it tangentially, not normally. Good. So let me show you some example, and that's a very classical standard test case, which is called the so-called M structure. So this is a light blue. That's my structure. That's an M. So why is it a standard test case? Because you have this corner here, which is for sure an overhang part. I mean, you have this corner. I mean, if you want to build it, you do it layer by layer, and when you have a layer that touch it, you will have to create an island of solid metal that will only touch the border behind. So it will, like a metallic stone, it will in water, it will go deep inside the sea of powder, and so you will not be able to build this structure if you build it layer by layer starting from the bottom. So of course it's a test case because it is impossible to build these small corners, reentrant corner, if you do not have support. So I have my light blue structure, which is fixed, and then I have my initialization of support in dark blue with some holes inside, and I want to build the support that minimize the compliance for which load? Well, for gravity load, because actually that's exactly what happens. I mean, the gravity is applied to my melted structure, and it will go down inside the powder because of gravity load. So I'm minimizing compliance for gravity load, and I'm trying to optimize the support to minimize this with a volume constraint on the support, which is 1. So something you will see on the structure how it goes. So here are the support that I obtained for this M structure. So on the left, I take very small value of alpha and beta, which mean very large rigidity of my interface. So what does that mean? That means it's almost a perfect interface. Okay, that's the limit case of a perfect interface, if you want, on the left. And you see that the supports are more or less vertical bars supporting the M, but those vertical bars are very thick, close to the reentrant corner of the M. Now, if you decrease the rigidity of the interface, so alpha equal to beta equal to 20 in the middle and 50 on the right, you see that you need more and more support, because the contact between the support and the structure is not good. So you need to thicken the support, and the support get closer, if you want, to the lower corner here. So no big surprise in some sense. But what is really interesting is then when you vary the rigidity in the tangential and the vertical direction. So here, on the left, you still have the perfect interface case. In the right, I choose values of alpha which are larger than beta. So that means that the rigidity in the tangential direction is weaker. So that means that, in some sense, the support is sliding along the structure. And what you see in the extreme case on the right, where alpha is 5 times larger than beta, so that means that really the support works only in the normal direction. It's very weak in the tangential direction. Well, the supports have a tendency to be normal to the structure, to be efficient. Okay, so that's exactly the kind of thing that we would like to see. And of course, if you do the reverse case, which is to have a normally weak interface, what you see on the right, which is an extreme case when the interface is very weak in the normal direction, but very strong in the tangential direction, you see that the support acts more or less tangentially. So they do what we want them to do in some sense. And then it's very interesting to see, because if you take a different structure, let's take a triangle, right? So that my light blue is a structure that I want to build. That's a triangle. If you do the perfect interface case, you see that, of course, because you want to build layer by layer, horizontal layer in the vertical direction, you see that the support are mostly vertical. But then if you have a weak interface, then you see, by the way, here the support can be attached to the bottom side, but also to the lateral side, but not to the upper side. And then you see that if you have a weak interface, then it becomes advantageous to have supports that are also coming from the lateral side. And that's something which is used by engineers, by the way. Even if you build layer by layer from the bottom side, sometimes they build a vertical layer, and then they have support starting from this vertical layer. So we were very happy to see by our optimization algorithm that indeed it is a good strategy if you can build a vertical layer to have supports which are attached to the lateral boundaries and not only to the bottom boundaries. Okay, so a very complicated structure which is not intuitive, and of course with a topology which is completely different with the topology that you could get with a perfect interface. So of course it works in 3D, and because time is running out, I'm just going to show you one example. Again, it's a classical test case. You see only here on the left 1/4 of the test case. It's a table, it's a circular table with just one pillar at the bottom, and you want to build supports for it because of course it's an overhang, it's an horizontal structure on most part of it. And so you see the type of support which are non-conventional in the sense that, of course, the support comes from the base plate and the support from behind, but there's also support from above because the interface is not perfect. So it's better not only to put support from below, but also to have some support from above. And so we have a very complicated structure of support in this case. And if I use supports which are normally weak, so they are strong in the tangential direction, but weak in the normal direction, we see something kind of strange. You see, it tries to clump the table at the boundary of the table in order to act in some sense horizontally, so that is tangentially rather than vertically. So we have a very different support if the interface is perfect according to the different rigidities in the different direction. So conclusion, what we wanted to prove is that if we take into account the fact that those supports are pre-cut, in some sense, you have dotted holes close to the interface with the structure. If you take that into account, maybe the topology and the shape of the support will be very different, and that we have been able to prove. What we should do is actually to have maybe some kind of a different rigidity if you are in traction or compression. You could expect that probably it's very stiff under compression, but not very stiff under traction. And actually, traction can happen because here I showed you examples with only gravity loads, but actually you can compute so-called equivalent thermal forces that come from the thermal residual stress. So you simulate the fabrication process where you have a thermal and elastic model, so a thermoelastic model. You compute the deformations, the thermal residual stresses, you deduce from them equivalent thermal forces, and then you do the optimization for those forces rather than for the gravity forces. And they typically give you more traction loads rather than compression loads. Of course, you could do multiple loads or multiple states because, if you say, well, why do you use thermal forces rather than gravity forces? Well, you could do both, actually, and that could be explored. And then, of course, in the end, you've seen that I've shown you some pictures. I'm working with people that are doing experiments, so we should do real experiment to see if those supports for imperfect interface do perform better than the classical ones. And let me conclude by wishing a very happy birthday to Enrique.
So many thanks, Gregoire, for this very interesting talk. And okay, so now we can hear some questions, comment, and start discussions on this subject. So the microphones are opened and the written chat, it is also open.
So Carlos, can I ask some?
Yes, yes, of course.
So merci, Greg. So thank you, Greg. Is in the problems you consider the right-hand side F was always fixed and given?
Yes.
Yeah. So. Yes.
And typically, yeah, it was continuous through the interface. Now if you were, for example, when I talking about gravity loads, gravity is the same for everybody, right? But the force will be the material density times the gravity. And so here, in the case of metallic additive manufacturing, we are lucky that the material parameters are the same. So that means that the gravity forces are the same in the structure and the support, and so there will be no change in the force when you move the interface. Where you could look at least from a mathematical point of view, to a case when the force will be discontinuous. You will have one force in one domain and another force in the other domain, and then there will be another term in the derivative.
Yeah, but so it would not be natural to also consider the case where, other than, for instance, the gravity force, you add a force applied by some other, I don't know, for instance, an object you are posing on the surface of the table?
Yes. So that's exactly what I call equivalent thermal forces. So actually, I'm doing this with because I mean gravity forces is good because they prevent. Or they have a tendency to produce support to support the horizontal part of the structure. But actually, when you have horizontal parts, not only you have this problem that when you build it, it will be supported by nothing, you don't have support, but also when you build it after, after the end of the process, the amount of heat that you have released to melt it leads to thermal residual stresses, and then you have bending because of those thermal residual stresses. So in the end, when you remove the powder, your structure is not flat, but it's bended by those thermal residual stresses. So you want also to avoid this. And so you could have supports to avoid this. And then you need to avoid this to put not gravity forces, but those equivalent thermal forces, which have been pre-computed by your computation of the building process for your structure without any support. So yes, there are various recipes in some sense of different forces to have the right supports for your structure.
Mm-hmm. Thank you.
Thank you. So, Greg, I also have a question in the same line as Enrique. Your target seems to be always the minimization of the compliance, okay? Or you can change your force by these equivalent thermal forces. But what about the eigenvalue associated to the structure? For example, to minimize the first eigenvalue.
Okay, so very good question. Let me ask the first part of the question. Let me answer the first part of the question, which was, I'm using compliance. And indeed, in my talk here, there was only compliance. But in real life, we are using other objective function. So there are two other objective functions which are very classical. First one is you want to minimize those famous thermal residual stresses. So you have a measure, for example, of the L2 norm of the stress, and you want to minimize this L2 norm of the stress. Another one is you want to avoid deformation, so you minimize the vertical displacement, so that in the end, your structure will not be deformed thanks to the action of the support. Okay, good. So that's used, and then you need to use an adjoint, and I didn't show any computation with that, but that's something that we do classically. Now you talk about eigenvalue and eigenfunction, and here that's something that you could use to optimize your structure, because, for example, your structure could be submitted to vibration, and you want to minimize or to maximize rather its fundamental frequency. So that's a standard optimal objective function for the final use of the structure. But during the building process, and that's during the building process that you need the support, I don't know of any eigenvalue problem which is relevant.
Okay.
You see, eigenvalue and eigenfunction are okay for the final structure, but during the building process, I've never seen any objective function linked to the eigenvalue of the eigenvectors.
Okay, I understand. We have two hand raised, Martin Lasert and Giuseppe Butazzo. So we can start by Martin.
Okay. Hello, Greg. Thanks for the nice talk. I have a follow-up question. So usually when someone deals with optimal design of two materials, the problem is not well posed and you have to relax it, in the sense that you allow for regions consisting of fine mixture of two materials, rather than just have two separate regions, each one consisting just of one material. So is that case in your problem as well, or you don't need any kind of relaxation?
You are absolutely right. I said I would not say anything about existence and uniqueness, but you're right. You would expect a relaxation phenomena by mixing two phases, right? The relaxation will be a bit more delicate because I have an interfacial term. And so you don't expect to have very fine mixtures, because if you have very fine mixture, the term in the variational formulation, which involves the interfacial energy in some sense, will blow up. I mean, if you have very small inclusion, maybe the total volume is bounded, but the interfacial energy may blow up. So, it's not clear how you will relax this term. I suspect still we will have an homogenization phenomena, but it's a little bit more complicated than the standard homogenization phenomena that we know. So if you want to avoid this, I said that the interface must belong to some set of admissible interfaces. Let me just add a uniform bound, for example, on the curvature of my interface. Something in the spirit of the work of Denise Chenet. So if I have some uniform bound on the mean curvature, for example, you have some compactness, and then you have no relaxation phenomena. But of course, if you forget this bound, you have a relaxation phenomena and probably an homogenization result.
Okay, but does the functional you consider attains its infimum or not?
No, that I don't know. That I don't know. Very good question. I don't know.
Okay.
There was some work. There was some work by Rob Lipton on this, maybe Lipton and also Bogdan Vernescu, that were looking at a property of composite materials with imperfect interfaces. And I don't remember exactly what were their final result on this. That's a good point.
Okay, thank you.
Okay, thanks, Martin. So, Giuseppe, you can ask your questions.
Hi, Grégoire.
Hello,
so, concerning the comment you did in the last slide about different rigidities for traction and compression, one could expect that very thin bars could produce a lot of buckling. So do you think reasonable to impose an extra constraint about the thickness? So you only allow bars which have a certain minimal thickness.
Very good question. Thank you. Of course, this is linearized elasticity, so no buckling is taken into account, and that's a default. I agree. Now, my point here, I'm replacing a precise description of the small details of the support close to the interface by a very rough model of a weak interface. So I'm not going to go, with this very rough model to a very precise mechanical model, because that will make no sense. I mean, I'm making a very large, very big assumption by replacing the details of the geometry by my imperfect interface condition. So if now I go to a very precise mechanical model, that doesn't make any sense. But you're right that instead of taking into account a buckling constraint, I could put a thickness constraint, and that I know how to do that in previous work that I did. And that's a classical issue. You could have a constraint on the minimal thickness for the support. And then you could expect that this minimal thickness could be tuned so that it will not buckle. That's possible, yes.
Okay, thanks.
Okay, so thank you very much again, Greg, for this very nice talk. And we can thank him again. And now let's go to a brief break, a coffee break. So you can have your coffee at home or at the office. And we will stop for, I don't know, some 10 or 12 minutes. And we'll come back in here in Chile at 11:40. And in Europe, 4 hours plus. So 15:40. Okay?
Good.
Okay, so
thank you.
You can
see you. Thank you.
See you in 12 minutes. Okay, so we can come back and restart our meeting. Our next speaker will be Eduardo Serpa. He's a young Chilean researcher who received his PhD in 1989 from the University of Paris Sud. He is a former student of Jean-Michel Coron. He's today a full professor at the Catholic University of Chile. But before that, he was also a professor at the University Santa Maria in Valparaiso. He has received very important prizes at the international level. In particular, the USA SIAM Activity Group honored him with the Control and System Theory Prize. The title of his talk will be Stabilization for the KDB Equation, from Zuazua's result to the most recent ones. So, Eduardo, you can start your conference.
Thank you, Carlos, for the introduction. First of all, Enrique, I really hope you have had a nice year of celebration. Okay, feliz cumpleaños. Well, just to start, in the first attempt, I thought of putting the title from Enrique's result, but there are two relevant Enrique's in our community, so just I put Zuazua, which is kind of called, but it wasn't the intention, Enrique. And of course, we're starting from one paper with two other co-authors, so Brazilian guys, Perla Mensala and Vasconcelos, so also the recognition for them. Well, in fact, it was making memory. The first time I saw Enrique was in Caldo's office when I was undergraduate student in Chile. So since then, Enrique has been always very kind with me and with other young researchers at that time. So I really appreciate that, because it's very important when you are starting, feeling that you are part of something. And so Enrique was always there, also always there to write a number of recommendation letters and organizing and inviting me to conference. I remember one of the nicest conference I went, because the ambience was in Castro Urdiales. It was a very nice place near Bilbao. So I have also Benasque. I have very good memories. All the effort of led by Enrique, organizing all kind of events, was very important to make our community stronger and very nice to make our career. So thank you for all that, Enrique. Just to start, well, I will work with I will talk to you about my favorite equation. This is the KDB one, okay? That Jean-Michel this morning, or very early in the afternoon for you in Europe, talk about this. Okay, it's the model for water wave. Okay, this is at the bottom. We have a nonlinear equation when it's right on the whole line. Okay, so then when you want to study this equation on a bounded domain, you have to add a first order term, ux. What is very important to some problem, as Jean-Michel told us this morning, because if you remove that term, there is no critical length or all that stuff. So thanks to that term, we have written a lot of papers, so it's important, okay? And of course, because of the modeling, it's very important to include it. So in this talk, we're talking about stability and stabilization properties for this KDB equation here, okay, which is a nonlinear third order space derivative on a bounded interval 0L. For the boundary condition, we're putting homogeneous Dirichlet boundary conditions on the left and on the right, and homogeneous Neumann boundary condition on the right. Okay. Of course, we have to add an initial data, and if this initial data is L2 in a space, well, the solution is proven to be in continuous in L2, okay, with other hidden regularities which are very useful to deal with the nonlinearities. So we're interested during this talk. In fact, I was like looking for a topic connecting me with Enrique, okay, and I realized that that paper that I will show you soon has created a huge amount of paper, a huge flow of papers, of works, of method, generalizing or extending the result in that paper. So I found this is very important. This is just an example because Enrique has made that in other directions with other equations, but it's a really nice example of how that first paper create a mass of works around it, okay? So we're interested in the energy. So here we call the energy just the L2 norm because of the regularity we're working at, okay? The energy is just the L2 norm of the solution. And we wonder if we have or not an exponential, well, a decay and an exponential decay of the energy, okay, as you can see here in the middle. So the first step is linearizing the equation. So we have the same equation as before. We just drop the nonlinear term ux, okay, we have the same system. And so we start playing with that equation. So here in blue is the linear part, okay, this is 0 because the equation is equal to 0. And we get that in that case, we have that the derivative of the energy is given by this boundary trace, okay, the ux at x equal to 0, okay. So it's not positive, so good news, but is it strictly decreasing the energy? So that's the question, okay. So in addition to that, we're looking for exponential decay, if any. So what happens? Well, as it is very connected to the Jean-Michel talk, so the energy is not always decreasing, okay? So there are solutions with constant energy, okay? So for instance, here, if L is equal to 2 pi, so you are studying the equation in 0 to pi, okay? You have this initial condition, y minus cosinus x, okay? Such that the solution of the linear KdV equation here in red is stationary and is just 1 minus cosinus x. So the energy is conserved, okay? So the derivative of the energy is equal to 0 because we have exactly that this trace at 0 is 0. So you don't have any decay of the energy. And of course, this is not the only case. L equal to 2 pi, there is a set of what is called critical lengths. Okay, here, well, denoted by the letter N, sorry. So we have that for all this L, there are this kind of solution conserving the L2 norm of the solution, okay? And of course, this phenomenon is linked to the controllability of the linear KdV equation that Jean-Michel mentioned this previously, okay? So that's important to just understand what we're saying later. So the set of initial data for which there are solutions conserving the L2 norm, okay, is a finite dimensional space in L2, and we denote it by M. Okay, it's the same set M as in the talk by Jean-Michel, so that's very easy to me. I can just skip some explanation. And here there is this is a summary of Jean-Michel talk. Okay, so thanks for doing all the explanation. So in '97, Leonard Rossier proved that they studied the controllability, and then we proved that we use the nonlinearity in order to get the local exact controllability. And recently, Jean-Michel with Armand Koenig and Huang Nguyen does this very nice result. So here, in fact, I never asked Enrique. So this is a picture of the Lionel paper, okay, in '97. And he thanks Enrique for pointing to him techniques permitting to drop useless assumptions. So I never asked Enrique or Lionel what kind of condition were those. So I don't know if Enrique remembered that or not. Maybe Lionel maybe sometime told me that at the first time he just made some multiplier computation and he got very restrictive condition on the L, on the domain L. I don't know if Enrique pushed that a little bit to look for this critical length. Maybe that is my, that's what I thought. I'm not sure about it, okay? So again, in this very seminal paper by Lionel, Enrique was playing an important role, okay? So that's very, very, very nice to see that, I don't know, or almost 24 years later. And so for the stabilization, so we know that there are some solutions conserving delta norm, okay? So we have here the nonlinear equation. We consider here a source term, capital F. We can show it as a feedback load. So we can address this problem from a control viewpoint, saying, can we find a damping mechanism in order to add a damping in the solution, making the energy to decrease? Okay, and so that's exactly the case. So we put here a term minus A of X times U, and this A is a L infinity function being positive, okay? Being positive in a, well, being always not negative, but being strictly positive on a subset O, okay? So that term brings, as we will see, the decreasing of the energy to the set. So the closed loop system, finally, to study now is this in the bottom here in the box, okay? So we have add this damping term in order to see what happened with the energy. So a natural strategy again is to linearize, okay? We linearize the equation, we get one, okay? And this is the first result in that in the paper that I mentioned before by the Perlamensala, Vasconcelos, and Zuazua. In fact, I saw by the first time Vasconcelos last year in a webinar in Brazil. It was very nice. I talked to him a little bit. And Gustavo, I met him when I was in Paris. So very, very nice guy, Gustavo Perlamensala. So the result was, if A is as before, effectively A brings some damping mechanism to the equation. And for the linear system, we can get the exponential decay of the energy, okay, for any initial condition U dot in L20L. That result can be extended to the nonlinear one, first in a local manner, okay, just by a perturbative argument, okay. Here in 2, we have now the nonlinear equation with this damping additional term, okay. Using, of course, with this local result, we have to add an initial condition on the initial data, have to be small enough in order to recover that exponential decay for the nonlinear system. This is also a paper, this is also a result in the previous paper, but that was improved because of a condition on the damping term, A of X, okay. This result, improved result, is by Ademir Pasotto in 2005, okay. So they prove what we call a semi-global result, okay. So for any initial condition, we can find constant C and omega here, but depending on R. And R is a bound for the norm of the initial data, okay. So for any initial data, you look at the norm and you will find constant depending on that norm, such that you recover this exponential decay. So what's called semi-global result, okay. And so, and here in blue, okay, we have the condition. This is a condition in the paper by Perlamensala, Vasconcelos, Enrique, okay. Yeah, and it was used in order to, at some point, we have to apply a unique continuation property for the KdV equation. And at that time, that condition ensures that you get at some time with an U, which is 0 near the boundaries, and then you can extend to the whole line, and then you can apply a unique continuation property on the real line, okay? And Ademir realized that you can prove, you can use another result by Jean-Claude Zot in order to get the unique continuation for a nonlinear version of the equation, okay, without extending to the whole line, okay? So here, let me move a little bit here. Yeah. So what happened for what is what's an idea of the proof, okay? An idea of the proof. So here I will talk about the case with no damping and with a non-critical case. When the domain L is not critical, you don't really need the damping term A, okay? And the proof is very easy. So here, this is what is called observability inequality, and this is the condition giving you the controllability, okay, of the linear KDV equation from with a control on the Dirichlet, on the Neumann boundary condition on the right, okay? So you make this computation as before, okay, and you get this trace, and it's exactly what you have in the observability. You can use the observability in order to get here at the last line a decrease of the energy if the time goes from 0 to 1, okay, for instance, okay? And with a constant here in blue, which is strictly less than 1. That's very important, okay? So the observability gives you exactly that, okay? Sorry. So you can do the same between t and t plus 1, okay? With this constant c, the same constant c squared minus 1 over c squared, which is less than 1, okay? And by using that kind of semi-group argument, okay, you can recover a constant gamma, gamma, gamma for each unit of time, okay? And you can recover here on the left, you have the energy, and on the right, you can write what you obtain in an exponential way, okay? And you get, so when you have the observability inequality, so when you are not in this set of critical length, you get the decrease of the energy without any damping term, okay? So when you are in a critical case, here you need for the linear system, you really need the decay, brought by the damping term. Here is the same as before, but because of this term A here, you obtain this extra term here, okay, for the derivative in time of the energy, which is still less than 0, non-positive, okay, but you have to work a little bit in order to obtain the exponential decay of the energy. And here you can do it, okay, that's where just making some computation as before, where there's some explanation that I can skip a little bit, saying that in fact what you need is the last inequality here, okay, at the bottom, which is kind of observability inequality with an extra term, okay? So if you remove this A, of course, this is not true if L is critical, but if you put it, you can prove it that this is in fact true. And the proof of that, this is all this proof was made in Enrique's result in 2002. Okay, you made some computation, okay, some multiplier, and you get some stuff. Let me skip a little bit that. Okay, and finally you have to prove this. This is the last line. So you have to prove this, and you apply a contradiction argument. Okay, here you apply a contradiction argument. So for every k, blah, 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 this is writing here, for every k, there exists a solution such that the inequality you are looking for is not true, okay? And you use this for any k with k equals to 1 over n, and which is important. That's why you are able to build a sequence of solution of your linear KDV equation satisfying this, okay? 1 over n bigger than all that stuff. So here at the limit, if you're able to pass to the limit, and some station work hard in order to pass to the limit with other non-linearities, I will mention that soon. So you end up with the sequence such that not only the trace of the derivative at 0 goes to 0, but also a times un, the whole solution, but multiplied by a. So that gives you information about un, or the limit u, when a is not 0. Okay, so we can pass to the limit, okay, and you end up with a linear equation, okay, for u here, but with the additional condition, as I mentioned before, a times u equals to 0. Okay, and so that gives you the condition that u is 0 for every x in this subset O. So because the equation is linear here, you can apply Holmgren's theorem in order to get that the solution has to be 0 everywhere, and also you get a contradiction because you rescale at some moment, so the norm of u is 1. So that's more or less how this argument by contradiction ran. Okay, so doing that, you get this result for the linear equation. Okay, so you don't need the A term when you are not critical, and you really need it when you are critical. Just to mention very quickly, when you want to pass to the nonlinear equation, if you are looking for a local result, you can just do a perturbative argument as usual. So here you have the system nonlinear, the nonlinear system U. You split in U1 and U2. In U1 you put the initial condition, so you know that U1 is decreasing because what you just proved. And U2, you pass to U2 0 and null initial condition, but you pass all the nonlinearity. Okay, so here you get for U1, U is bounded by U1 plus U2. For U1, you get this gamma is strictly less than 1, and you really need some nonlinear estimate in order to it. Okay, with this kind of perturbative argument, all the garbage coming from the nonlinear. Okay, so this is the more or less the kind of inequality. So at some point you really need a nonlinear estimate. Okay, you can do it here, but I just skipping the details. Okay, and at the end of the day you obtain something like this, and here you can get something like this when U0 is small enough. So you can, this is here you have all the terms that you have to manage in order to get some result like that. Okay, and after this point, then the proof is as before when you get this inequality, this estimate for the energy. Okay, so that's the way you prove the local version of this exponential decay. Okay, and in blue here I'm just putting that well, the semi-global results. Okay, the semi-global result by Enrique and improved by Ademir Pasotto requires you to work with all the time with the nonlinear system. Okay, so making the contradiction argument and the continuation unique property with the nonlinear system. Doing that, well, you can do it, you can manage, and you end up with what we call a semi-global result. Okay, so here I would like to mention some extensions. Starting from this paper by Parlamentara Vasconcelos and Zuazua. Okay, so some of the first extension when you change a little bit the nonlinearity. Okay, and this paper are plenty of technical difficulties that they were able to do. Okay, so when p is less than 4 or P equals to 4, okay, that paper by Lionel and Binju Sang, Felipe Linares and Ademir Pasotto. Okay, here I don't know if people know a lot of this result, but there is some numerical version. In fact, they semi-discretize the system, discretize in space, with very particular numerical schemes in order to conserve some nonlinearity quantities. Okay, they are very, very precise and very tricky numerical scheme in order to recover lambda properties for semi-discretized system. Okay, so we have this by Pasotto, Sepúlveda, and Vera, and by Sepúlveda. Sepúlveda works in Concepción in Chile, and he is very strong in numerical analysis. And other kind of extensions. Okay, so first paper by Mazzarolo, Perla-Mensala, and Ademir Pasotto. Change the damping term. Say maybe putting the A times U. Well, that's when it's enough, but maybe it's too much. So they put weaker damping mechanism. Okay, using here the inverse of the Laplacian, for instance. And then recently, Roberto Capestrano Filho also used another damping term. Okay, there are other extensions. Here there is an extension on the delay. Well, it's very important because the delay is also present in application, and the behavior of the system with delay can be very bad. Okay, for instance, here the very simple system with x is a real number, x dot equal to minus x with solution exponential minus t. Okay, if you put a delay d, okay, which is bigger than p over 2, you manage to find solutions that are not converging to 0. Okay, so that's very, of course, here you need a delay large enough, but we know for PDEs, especially for hyperbolic systems, okay, that even sometimes there are very small delay, as small as you want, that destroy the stability of your feedback loop, okay, of the stability of your system when you consider the delay. Also here we found a paper by Julie Balin this year. So here they put two damping terms, one without delay, another one with delay, okay. Well, under some condition on saying that the more or less we can rephrase that, saying that the damping without delay is stronger than the term with delay, okay, but you can manage to do more or less the same kind of argument as in the first paper by Enrique, okay, with this delay. So there are also works in that direction. And here with Saint-Mars, Vincent Andrew, and Christophe Prior in France, we consider the case with saturation. So we put here what is saturation, okay, putting here in the graph is simpler to see. We have in the dot line is the cosinus function, okay. In blue is the more famous saturation function, cutting at some level by here in 0.5 and minus 0.5, okay. But you can also consider a saturation, a non-local saturation. You can say like that, saying that behavior on the whole line. So you saturate or not depending on the norm of the function in the whole domain, okay. And that gives you the function here in red, which is okay, smoother. So sometimes you can do more precise result using that kind of saturation than just cutting using what we call here the saturation, the local saturation. Okay. So here again, it's very important to look what happened with saturation, because we have very simple examples. For instance, here, where you have a feedback control system, choosing U in this way give you that the system goes asymptotically to 0. Okay, this is a system of ODE. And if you cut with the saturation at level 5, for instance, okay, you get a solution. Here's a numerical simulation. You get solutions that are not converging to C. So again, here the saturation can destroy what the performance of your feedback loop. Okay. What we do here is a quick summary of kind of result I found for this, starting from this initial point by this paper. So for any of this saturation, we were able to prove the semi-global version of the stability. Okay, well, of course, the linear, but also the semi-global. And here, the difficulties, the ideas are the same that in the initial paper, but you have to take care of this new nonlinear part of the system, because the saturation you have to deal with it as a nonlinearity in the system. Okay, so this is a paper in 2017. In that paper, we run some simulations. Here we were able to say something more precise when, well, not very interesting maybe, but when you put the damping term everywhere, okay, and you saturate with the L2 norm, okay, well, these are some simulations showing that it works more or less well. Here's the decay of the energy here on the right at the bottom, okay, the numerical saturated energy in blue, okay, which is go faster to 0 than the theoretical predicted energy, okay, but worse than the energy without saturation, okay. And in the case where you put the damping term active between L/3 and 2L/3, okay, you again here you saturate with the log, you just cut at some level, which is 0.5, Okay, yeah, here the notation was good. U0 is where you got. Okay, and here we have also some simulation showing that the control works good. And here the control, you see that is really cut at 0.5. Okay. Other extension, well, just for couplet system, there are a lot of papers. Okay, trying to do this same approach for couplet system, and recently some effort to consider, well, a special case of couplet system, but network. Okay, so different KdV equations posed on different domain, but coupled. Okay, with different topologies. Just to make the link with what Jean-Michel explained this morning, just briefly, what happened with when you are not allowed to add damping? Okay, so you know that the linear system has some solution conserving itself to norm, but you can wonder if the nonlinearity, as for the controllability part, if the nonlinearity brings some decay of the energy. And that was effectively the case. Okay, it's in a series of 3 papers, but there are still some open doors to do some research, but there are very few. There are very few room, maybe, but it's still interesting. Okay, to close that and be able to say something working for every critical domain. First, when the system is not controllable because the space M of non-controllable state has dimension 1, so it was the first paper by Xu, Corona, and Shank. Okay, using infinite dimensional version of center manifold theory. Okay, in order to study. That's very important here because the space where you have this conservation of energy, let's say like that, for the linear system is finite dimension. So you can adapt many things from finite dimension to this infinite dimension case. Okay, and then when for the second paper works, as I remember, just for one case, for a particular case for which the dimension of M is 2. The kind of tools are similar to the previous one, and recently Huamin and Guyen got a very nice result. Okay, which is working for many critical length, but not all of them. Okay, and he used power series expansion and very fine estimation of all to see really what's happening on the part of the finite dimensional part where the energy is conserved for the linear system. So that's more or less result trying to get the same kind of result for the controllability, in the sense that the linear part has a behavior and the nonlinear part, the nonlinear equation, has a different behavior. Okay, well, here the decay, the system is asymptotically stable with decay 1 over the square root of t. And all these results are local because I forgot to put, there is a paper by Gleb Doronin and Matteo Favalli, okay, showing that there exists some other solution conserving there to norm. Okay, so they are all locally around C. And just to, I have 9 minutes. Okay, I just want to show you about a last result that we continue in related to that, but it's not exactly the same. Okay, but related to that is a KdV system. Okay, where we managed to design an output feedback control. Okay, so just let me spell you here. We consider the system 5 here. Okay, so we have a cascade system. We have V1, V2, and V3. All of them are KdV equations. Okay, they are coupled in a cascade way. And here I put in red this minus V3 because of the minus. This is a term adding energy in the system. Okay, so here you expect that the equation V3 is unstable. Okay, that instability can even propagate to V2 or V1 because of the structure of the system. For V1 and V2, we consider homogeneous boundary condition, the same as before. Okay, here in 6, For V3, we consider a control acting on the Dirichlet condition at the left, here in red, okay? So when, as I mentioned, you expect the system to be unstable when no control is applied, okay? So we wonder if can we avoid that instability making a control, okay? And even better, can we make that control depending only on V1? So the control is acting on V3 through a boundary condition and depends only on V1. So you can only measure the solution V1. You can measure everywhere, okay, but you can just measure V1. So that's the reason we call an output feedback control, because you can measure just a part of the state, V1, and the control is additionally acting on far from that equation, so in V3. Classic strategy, so in order to make the full state feedback, no, you look at control U in the form U equal to Kx, okay, for linear system classical like here. So doing that, you have to look at for a matrix K such that the matrix A plus BK is perfect. So all the eigenvalues has a real part strictly negative. Okay. When you look for what we call what is called a static output feedback, so the same kind of solution, but U not in the here in red, not in the form Kx but Ky, where Y is a part of the state, is the measurement, is the observation. So you can look first for a control such that A plus BKC, okay, is Hurwitz, but it's very easy to build up some example as this one, okay, showing that there is no hope to do that even for matrices, okay, for system of ODEs. So here you have to change the static part, and we're looking for dynamic output feedback, okay? So in the way that, next slide, in the way that here, the first step is going to be to build what we call an what is called an observer. So here denoted by X hat, which is an auxiliary system converging to the real X. And so then you look for a control more or less as before, but not depending on X, because we see that there is no hope that that work, but depending on X hat, so on the observer, okay? So finally, that in finite dimension, that give you that, well, you have to first find a K such that A plus BK is Hurwitz, and also find a matrix L such that A plus LC is Hurwitz, okay? So we apply this to the system that we were considering, okay? Here I will accelerate a little bit. So the system, well, I present you with only 3 equations, but it can be n equations, okay? So this is in 9, you can see the structure of the system, which is a cascade system with the last equation can be unstable, okay? All the conditions are homogeneous for the first n-1 equation, and for the last one you have a control, okay? And for the output is you can measure the first component of the system. Okay, so you can see that if you control U depends on the solution Vn, you can just solve your problem by a backstepping method, for instance, and the result that we have with Jean-Michel in 2013. Okay, so that works, but we were looking for a control depending on V1. Okay, so the idea is first, here in blue, first to be that an observer, sorry, and then the control U define it by using the same structure as for the backstepping method, but not depending on the real state, but depending on the observer. Okay. So here, in the PhD thesis of Constantino Kitsos, made under the direction of Besançon and Prieur in Grenoble, they have worked and they have built some what is called high gain observer for different equations. So we applied that for this KDB system, and we started when Constantino visited us in Chile for a month. Okay, so just accelerate a little bit. So here we have the system, and we build an observer here with a a matrix O, which is diagonal with some parameter theta. So we have to choose theta big enough later on in order to do all that works. And our result, I will skip the proof, but our result is that first of all, we have the convergence of the observer. So V hat converge to V in an exponential way. Here we have the explicit dependence on the parameter theta. Okay, just to show you here a numerical simulation showing that when you increase the theta, okay, the convergence is faster and faster, and where there are even values of theta for which the convergence is not true. Okay, so we have a theoretical estimate of what you need. Okay, but you numerically you reach the convergence with a much less value. So our final result is that, in fact, not only the observer converges, but also the full system converges to zero. So you are adding a stability. You are with your control feedback, you convert an unstable system into an stable system. Okay. This is sketch of the proof. I will just skip it. Okay. And just to mention that when we change a little bit the boundary conditions, well, in the literature there are many papers dealing with boundary conditions. Here we have some troubles. We really need some point Lyapunov function depending on a function on a solution of a ODE. Here called pi. So with other boundary condition, in some case we have a result working only with two equations, or for any number of equations, but with a very small domain. So just to finish, well, I already thank Enrique for support to my career, and also to the community in Chile. I know that story started many years before, but at least since I'm in Chile, Enrique has come many times, a couple of important conferences, bringing his student, his postdoc, and being always available to be here. And for us was very, very important. So thank you to all of you, especially Enrique.
Thank you to you, Eduardo, for this very nice talk. So questions are open for everybody who is raising the hand. In particular, Jean-Michel. So I see here Jean-Michel, Enrique. So Jean-Michel, you can start.
Oh, okay, very good. Yes, thank you very much, Eduardo, for this very nice talk. I was wondering, sometimes you say there exists C star of R, there exists mu star of R. Is it possible to get some estimates on C of R and nu star of R?
Yeah. For the case, for instance, for saturation, well, in fact, just in the simplest case where you have the L2 saturation and the support is acting and the damping is acting everywhere, in that time you can see very clearly what is the dependence of all the parameters of the decay rate. But in the general case, not that easy, because there are, well, contradiction arguments, and so it's not that clear. But in some cases, yeah, you can see it, especially the decay rates and the C.
And in the first part of the talk, you prove the exponential decay rate without giving any Lyapunov function. Is it possible to give a Lyapunov function as you do later on, or it is a V dot such that V dot is less than minus omega V?
Yeah, no. In fact, I haven't been able to show a Lyapunov function giving that result. No.
Okay. Thank you very much.
Okay. So Enrique, you have raised your hand.
Yes. So Eduardo, thank you very much for your talk. Yeah, I remember. My contact with this topic was, I think I was, maybe, do you know if the first paper of Lionel on this was published in Siam Journal of Control?
No, it was COCV.
Or COCV, yeah. So I think I was the editor of, in charge of the paper, and then all independent of the referees, yes, I found it extremely interesting. Yeah, and probably my remark was something like, yeah, I mean, once you have the compact reminder, you can somehow do the argument of, you know, try to reduce that to the very isolated cases where there is a non-trivial eigenfunction, right, for which the boundary dissipation is vanishes or something like this. Yes. So, but in your first slide, I think you have put, you know, the typical you know, experiment where you build this nonlinear wave, right, on a canal, like the nonlinear soliton, right? So this is the typical nonlinear soliton that you get on KDV when you release a substantial amount of water, and then spontaneously this nonlinear pattern arises, right?
Mm-hmm.
So how does your work somehow apply when you are looking to solutions around this soliton?
Yeah, well, in fact, what we have done always is bounded domain. So with this kind of homogeneous boundary condition that kills every soliton as we know in the whole line. So you don't have it when you are working on the bounded domain, at least with the classical boundary conditions. So yeah, in order to see it, you have to consider on the real line. In fact, I also forgot to mention a paper by Claudio Munoz, who worked with Martel and Merle in the propagation of on soliton for KDV, and he wrote a paper in SciCon on the role of this kind of damping terms for soliton propagating on the whole line. But of course, you really need this damping term acting or acting everywhere in the domain. Okay, so when you want to apply this idea to the whole line, you really need a damping term acting almost everywhere, or I don't know, something like that.
So, but you can of course take this soliton and you place it in the interval 0L, right? With suitable, I mean, with the boundary conditions of the soliton that of course are moving, right? So, and then maybe it makes sense to formulate some kind of controllability property or so. I don't know whether the results by Jean-Michel earlier this afternoon will apply in that case, where your goal is to drive the KDV equation from an arbitrary initial state to the profile of the soliton. That will be a kind of potential result. But I agree, this will be maybe open loop control, right? Through the boundary. Okay, thank you.
Thank you, Enrique.
Many thanks, Enrique. So, Chiang, you want to ask a question?
Yeah, of course. So, hello, Professor Serpa. It's a very nice talk, and actually, I'm very happy because during my PhD, I read a lot of your papers. So the question is like more or less related to the talk by Jean-Michel this morning. So, you know that for your first part, you proved the stability using those compactness argument, which is based on energy estimation and the observability inequality. So, but you see that for Jean-Michel, they say that, okay, we don't work on L2 space, but sometimes we work on higher dimensional space. But I probably don't know any result of this kind for stability result. I mean, for stability in H1 or H2 space, but it's also based on some compactness argument for KDV. Do you think this is possible, or like? We are working on L2, which is fine, which is perfect, but just asking some technical problems. So,
yeah, no, I think that the decay can be proved to other solid spaces instead of L2. Or yeah, I don't have clear the reference, but if there's something made, I don't remember very well. But yeah, no. Well, I will take a look at that closely. See if I can find some reference.
Yeah, probably it's not a very good question, but
okay. You know, there are a lot of papers looking for the right correspondence between the regularity of the boundary condition to the regularity of the solution. Normally they get a global existing solution. It's an important topic, of course, sir.
Yeah, Yeah. For well postness, I think it's well studied, and for stability, I just think, okay, probably I haven't seen something, but maybe you know. So okay, thank you.
Thank you, Chan. So, Mahamadi, do you
Yeah,
have
yeah.
a question?
Yeah, I have a question. My question is that, in what will be the effect in the controllability result if you add an even part of the derivative? Because what you have is the derivative in time, in space, all derivative. You have the third one in the first one. Suppose you have the second one. What will be the effect in the controllability result if you have a second derivative in x in the space one?
Yeah, well, I never made the computation, but I think that there will still be some non-controllable solutions. Well, the form, in many papers, the form, they really use the explicit form of the eigenfunctions that are not observable, well, the state that are not controllable and all that stuff. With other low-order terms, maybe there are, will be some modification, but there will still be present in the system, I think.
Well, from first order to third order, you have a very small perturbation, like very, very small. Okay. But if you have a third order, you put the second order, you have to be, I don't know, in terms of semi-Wuppertal thing, you have to be careful how you have this from third to first is really going very low, Okay. But if you have a second order, if you put a second order there, I don't know what will be. I really wonder, maybe while the specialists know, I'm not a specialist in control, but how will be the effect of this second order?
Well, for instance, we have some paper adding and there are other papers adding the Laplacian in the equation. Okay, so but not looking for the non-controllable part, but putting the control, for instance, on the left divisibly boundary condition.
On the left. Okay.
Okay, and you can add this kind of system with a second order term specifically.
Okay, thank you.
Okay, thank you to you, Mahamadi. If there is no more questions, we can thank again Eduardo for his very interesting talk. Thanks. Many thanks, Eduardo. So we will go now to a longer break. We will stop for approximately 1 hour. People in Latin America can use this to have a light lunch. We will come back in 1 hour. People in other locations, they can use this freely to have maybe a 5 o'clock tea. I don't know. You can do whatever you want. Feel free to rest a little bit. And okay, so we will stop and return back in 1 hour at 13:30 in Chile, 17:30 in Europe. Okay? So see you later. Huh? Ciao. Hello? Hello?
La luz.
¿Aló?
Ya. Ahora sí.
Y a Miguel, ¿no? También ábreselo.
Sí.
So I think it's time to start again. So thank you everybody to be here. I have the pleasure to present Miguel Escobedo. Miguel works at the Department of Mathematics at the University of the Basque Country, and he works in the study of nonlinear partial differential equations, existence and uniqueness of solutions and their qualitative behavior using tools of classical calculus and functional analysis. He has been more involved recently in kinetic equations and strongly motivated by physical phenomena. So he's going to talk about instability of some equilibria in a homogeneous Boltzmann equation for radiation. Thank you, Miguel.
Thank you very much for the invitation, for the presentation. Can you see the?
Yes, the slides, yes.
The slides, okay. So the first thing is, all right. So it's a pleasure and a privilege to participate in this conference in honor of Enrique. Of course, almost everything has been said about Enrique, but anyway, can't. I can't. Okay. Okay. So I don't know if you still hear me, but I had some.
We hear you, but we don't see the slides move. It's
yeah. So I had a small problem, but I think it's working. So I was saying that essentially, well, a lot of nice things have been said about Enrique, but I would just like to emphasize the fact that Enrique's generation came after a brilliant Spanish generation of mathematicians who, as I say, started a new time for mathematics in Spain after a difficult period. And that sometimes is difficult, okay? But Enrique, as we all know, always did very well, always did as well as people before, and quite often he did much better. So that's something I would like to emphasize. And of course, Enrique is also a wonderful and generous colleague who enjoys tough discussions, not only on mathematics, but on other subjects. So for all this, I want to thank Enrique, wish him a happy 60th birthday and tell him sorry, Onak. So I would like to describe some recent and still partial results on a very simple, at least simply looking kinetic equation that some people call the Compton-Boltzmann equation. So it comes from a Boltzmann equation in three-dimensional variable, but after some reductions, it is simplified to this very simple situation. So U describes the density of particles called photons. It depends on T.
Slide, Miguel, sorry, we don't see the slide. You are at the beginning.
Can you see it when I
Only
move it?
the first slide. At least I don't see it moving.
Are you sharing your screen?
No, just one.
This is what you have to do.
Here it is. So here you have the Compton-Boltzmann equation.
Let's see if okay, I don't understand what is happening, but anyway. So that's the equation I wanted to talk about. As I was saying, U is a density of
particles, and depends on t, the time. X is not a space variable, it's a momentum, an energy variable, and it will be non-negative. W is a function I will describe later, and small q of u is this quadratic form in u, or this nonlinear term in u, strange mixture that looks like something like in the Boltzmann equation. Okay. It was first written by Campanese in 56, and then it has been derived by many other people. It is described, or it was introduced to describe what is called the Compton scattering between electrons and photons, that are the particles whose density is u. And it is of great interest in many, many applications, plasma physics, cosmology, but also biomedical imaging, and in a lot of places where you have you need to describe radiation interacting with some kind of matter. And as it often happens with these equations, there's no rigorous mathematical deduction of the equation from the beginning. So I don't know if you see the new slide.
Yes, yes.
Okay. So this Boltzmann equation actually is mostly used in the applications because it has an extremely well-known approximation that is called the Campanese equation, which is a diffusion, a kind of Fokker-Planck or convection diffusion equation that I wrote here, that was also derived by Campanese. And it's the basis of what I call here the basis of the mathematical description of the Sunyaev-Seldovich effect in the cosmic microwave background. So it's a widespread model in all astrophysical books. You can find 1 or 2 pages about this Campanese equation. Now, just from the mathematical point of view, the equation as one delicate point is how do you derive it from the Boltzmann equation? Okay, because essentially the idea is to expand the solution of the Boltzmann equation using a kind of Taylor expansion. And for that, you need the solution of the Boltzmann equation to have some kind of regularity. So you need to avoid strong gradients in the solution of the Boltzmann equation. So one of the first motivation is it always true that you can find regular solutions for the Boltzmann equation? Of course, a second problem of the Campanese equation is that you can always find situations where you cannot use the approximation and you have to go back to the original Boltzmann equation. Okay. Now, about the function W. The function W is not trivial because the geometry of the collisions is not trivial. The photons are necessarily relativistic quantum particles, and the electrons, in order to get the simplest possible equation, are supposed to be classical, non-quantum, non-relativistic particles. So you are mixing things, and so the collision is not completely trivial. So W is like that, where omega is this integral depending on the angular variable of the scattering. And it has a delicate behavior at the origin. When X or when Y goes to 0, it is singular at the origin in X. And if X and Y go to 0, you get that kind of behavior. Okay, so omega it's not very singular, but it is singular. And that will be the source of some problems. Now, some general properties of the equation that are shared by almost all the Boltzmann or all the kinetic type of equations is the total number of particles, which is represented by this integral, the integral from 0 to infinity of x squared times u, is conserved in time. So when you multiply when you integrate the equation for all the values of x, you get something that is constant in time. The energy is not conserved. It's different from the classical Boltzmann equation because we are not describing the electrons. The electrons are not taken into account in the equation. Only the photons are described. So when the photon, in each collision, say the photon is transferring energy to the electrons. And the equation has a set of equilibria, a whole family of equilibria, one parameter family that are given by these nice and explicit functions. Now here again we have two problems. The first problem that is perhaps the main motivation of our result is again related with the regularity of the solutions. In order to give sense to the nonlinear equation, we need to define the duality product of the integral collision with test functions. And in order to do that, we need to apply some Fubini argument. And here again, the regularity of U near the zero values of x is important. Moreover, taking into account that omega itself is not very regular. So we need to know, or we would like to know, what is the behavior of U when x goes to zero in order to check that the weak formulation of the nonlinear problems makes sense. The second problem is more related, well, it's perhaps more related with the model, but it comes from the very striking observation is that all these initial data that I wrote before are all of them bounded from above by the equilibrium for a equal to 0. So by the total number of particles that you can put in the equilibrium for any a is bounded from above by this number and naught, which is the integral of this a. So in this model, a gas in equilibrium may only contain up to n naught particles. So what happens if my initial data, or if my gas initially has more particles than n naught? So do I have solutions? And if I have solutions, what happens to them when T evolves? So the case where the initial data is below one of these equilibria is more clear, because in that case, you have an equilibria to converge to. And at least the existence of solutions was proved by Ferrari and Nuri some time ago. But imagine that you are below UA for some A for almost every X, but you just have a small peak in your initial data, and the number of your particles is too large. So what happens then? So that's the motivation of the work I wanted to address. Now, what I'm going to do is try to use the simplest arguments. I am going to linearize the equation around the maximal equilibria, which is this one, and look at some small perturbation with a positive number of particles in such a way that I'm in that region where I have no equilibrium anymore, okay? So this situation happens for other equations. For example, if you consider the equation that describes interactions for boson particles with positive mass, because photons have zero mass, so it's a very particular kind of bosons. But if you consider a gas of bosons with positive mass, you get a slightly different equation, more complicated. I don't want to describe it, but you have a similar situation. So there is a kind of maximal equilibria for which you can put a maximum number of particles and you may wonder what happens. But in that case, what happens is that the equation admits another family of equilibria where you can have Dirac measures at the origin. And so you can increase as much as you want the number of particles in your equilibrium. So the model admits singular equilibria, so equilibria with a Dirac mass at the origin, but you have equilibria. But in our case, in our equation, that is not, these kind of distributions are not equilibria in our equations. So even if the situation is not new, because it happens in other cases that you have a kind of maximal regular equilibria, in our case, the problem is that we do not have this singular equilibrium to solve the problem. So let me linearize around this maximal equilibria that I call 1 over exponential of x minus 1. I call it U0. And the linearization is made in this very particular form because it helps to simplify very much the way in which the linear equation is written. Okay, so the linear equation, I write it in that way, where Q of L is this integral, well, it's this linear term. Now I have a multiplication by an explicit function, gamma of x, which is given by this expression. And here inside I've this omega times the exponential of x plus y over 2 times y. This is kind of collision kernel in this simplified linear problem times f of y. So that's the linear problem. And what I would like to see is what happens if I take now an initial data, which is not necessarily positive. So the perturbation will not be necessarily positive, but the total amount of particles in the perturbation is positive in such a way that my perturbation increases the number of particles in the equilibria, and I want to know what happens. So the main result is the following. So I just need the spaces of functions that have some momentum x to the theta for theta positive. So there are kind of L1 spaces with weights, very simple weights. So my initial data will be a continuous function in two of these spaces for some weights alpha and beta. Alpha is going to be taken less than beta, but both of them have to be less than 1. Okay, so alpha is less than beta, so alpha less than beta, beta is less than or equal to 1, so alpha is strictly less than 1. So under these conditions, you can find a local mild solution of the equation for a small amount of time. The time is beta minus alpha, so since beta is already less than 1, this is a quite short interval of time. The function belongs to this kind of L1 weighted spaces. It is continuous in x and t for x strictly positive, and they satisfy a global, well, a bound for all time t less than the critical time, bounded by the norm of the initial data. Okay, so this k naught is a universal constant that doesn't depend on anything. So that's, I have a local solution for a small interval of time of my linear problem. And moreover, and that's the interesting point, you can obtain a lower bound, a lower pointwise bound on the solution f in terms of two non-local problems. So you have something that is that is singular at the origin, t over minus x times log of x. So when x is negative, when x goes to 0, log is negative, this is a positive quantity. You have here two constants depending only on the initial data. And here you have something that depends on the solution itself through the operator R that I will describe in a moment. This is a non-local term in X, and it's integrated in time. Okay, so that's the basic lower bound that you can obtain for X small and T small. Okay. Now, from this estimate, you can deduce the main result or the corollary, which is the following. If you assume, moreover, that your initial data is in L1, so it's not only in these L1 spaces with weights, but it is also in L1. And if you have a kind of condition that the whole integral of the initial data is larger than this weighted integral, so you see, if the initial data is constant, if the initial data is concentrated near the origin, this is always possible, okay? Because here you have the weights x to the alpha, x to the beta, so this will be always possible. So if f I'm worried about the connection anyway. If the initial data satisfies this condition, then the solution that we have obtained cannot be integrable in time and space in any small interval of space and time. Okay, so can you tell me if I'm still connected or if you look?
Yes.
Okay, very well. So if the initial data is in L1, essentially, and if I have this condition, meaning that the initial data is rather concentrated near the origin, then my solution cannot be in L1. So I claim that this is a kind of instability for the linear problem. Why that? Because no matter how regular and small is the initial data around the origin, if it satisfies these conditions, the perturbation, which is u naught times 1 plus u naught times f, cannot remain a small perturbation for times in 0 time, because this function, when x goes to 0, behaves like this function, taking into account the behavior of u naught and hyperbolic sinus, and this function is much, much larger than u naught because f is not bounded near the origin. F is not integrable, so f is very large near the origin. So the perturbation becomes much larger than u naught instantaneously in a small interval of time. So I cannot maintain a small perturbation for any small interval of time in my linear problem. So this is also not very good for the nonlinear problem, because for the nonlinear problem, in terms of the physical model, a natural condition of the perturbation is that this quantity contains a finite number of particles, because this is exactly the amount of particles I'm adding. If I want that to be finite, I know by a previous result by Ferrari and Nouri in 2006 that this condition will imply this condition, where I dropped 1 power of x. I go from x squared to x. But this condition implies that f is integrable near the origin. So if I want a finite number of particles in my perturbation, this implies that f has to be L1 integrable near the origin. So of course, I only have the result for the moment for the linear problem, but I strongly believe that this will imply that there is no L1 solution for the nonlinear problem, and that will mean that I cannot build a solution of my nonlinear problem containing a finite number of particles. So I will not be able to build a solution of the nonlinear problem respecting, say, the physical model. Okay, so that's the main result and the remarks I wanted to do. So what is the, how can you prove something like that? How do you obtain something like that? The idea is, oh my goodness. ¿Qué cojones pasa? No. Okay. So the proof has 3 steps. I think I will only have time to give 1 step, and 2 approximation. I think I will have time for 1 approximation, which is the main step. So the main idea is to approximate this function omega, which is complicated. Okay, the function of x and y is too complicated to solve it directly. So the idea of the approximation is to notice that if I drop the cosinus here, which is something made by physicists sometimes, then the remaining integral can be computed almost explicitly. So you can integrate this function. You get a kernel K for which you can know the behavior for r near 0 and r going to infinity. And you can also find very easily the behavior of the function gamma x that is in the linearized problem. So you may approximate the linear problem in that way, that I q tilde L, where I replaced omega by this function h, and where I replace gamma by this gamma naught. So h is a kind of Frankenstein approximation of omega. You see, it's 1 over r for r bigger than 1, so it's extremely simple. And for r small, I get something which only depends on y. So r will be x over y. Okay, so that's just a notation. So this is the kind of approximation I do for h. So what's the advantage? The very big advantage of this approximation is that you can solve it explicitly. This linear problem is the kind of skeleton of your problem, and you can linearize. You can solve it explicitly using Fourier methods, or in that case, Mellins transform method. So I Mellin transform the equation. I call it f hat with some abuse of notation. And I get this equation for f hat. It's a kind of linear hyperbolic equation, but non-local. So it's a kind of, well, but you can build an explicit solution, at least one. So S now is in the complex plane, but the real part of S is well chosen in order for this function to be analytic in some strip, and then you can take the Mellin, you can inverse the Mellin transform of this function G, and you get something which is horrible, but it's explicit or more or less explicit. Okay, so that's what I call capital phi. So you have 2 terms. One term still contains a Dirac measure. So that's a fundamental solution with a Dirac measure at y. At time 0, the Dirac measure is at y. So you still have a Dirac measure at y, but it's modulated, it decays in time, and you have this extra power of y. It's a kind of regularization, well, slightly regularization of. And then you have a function g, which is given in terms of some hypergeometric functions and binomial coefficients you don't want to know, and h is the Heaviside function. So you have 2 parts, one for x large. So capital X is small x over y. So you have one for small x large and one for small x small. Okay, so and this is the one which is dangerous because that's the behavior I'm interested in. What happens when capital X goes to 0? So when x goes to 0, you can give the asymptotic behavior of this function phi when capital X goes to 0 or goes to infinity. They are explicit, they are very simple to obtain. And the important point is that when X goes to 0, you get a 1 over capital X here, plus a logarithm. Okay, so it is not very bad, but it's not very good. In particular, it will not be integrable. Okay, so the function phi has a singularity. For X large, it's not bad. Okay, for X large, you get something that decreases, and as far as t is not too large, this will be integrable at infinity. But for X small, here you have a singularity. So now once you have the fundamental solution, you can solve the Cauchy problem. You can solve the Cauchy problem for a class of initial data that are still in that kind of spaces. You get a local solution, of course. You can define a kind of local in time semigroup, and you can obtain the behavior of the solution F in terms of the solution of the initial data. Well, I think I will have no time to give that. The second step, you start to add things to your kind of Frankenstein equation in order to get something more similar to the real equation. So the first step is to consider the function gamma instead of the function gamma naught. And so you get a second type of equation that you can also solve using classical fixed point arguments, and that you solve as a perturbation of the first semigroup. Okay, so when you add gamma instead of gamma naught, you get, for your first semigroup, you have an extra perturbation that you can solve in the equation. And using the explicit behavior of the first semigroup, you can find the behavior of this equation when X goes to 0 and for small values of t. Okay. You write your equation as a perturbation of the equation for the first semigroup, and then you can give the description of the behavior of this solution when t goes to 0 and X goes to 0 in terms of your initial data, plus the norm. So this is a non-local, but only for the initial data, plus the norm of your initial data, plus something that is arbitrarily small as t goes to 0. And now the last step is to consider the complete equation, okay, with gamma and omega. And again, you consider that as a perturbation of the second equation that you have solved. And so you put H here, and here you put the operator R that appear in the main result, which is just you add omega and you subtract capital H. Okay, so that is the operator R, which is well behaved for the spaces we are working on. So you can obtain estimates on this operator R when acting on these L1 spaces with weight. So you write your equation in terms of the semigroup for the S gamma that I worked just before. This is a new perturbation, and you apply again the Joubel formula. You obtain a solution which is given by the usual fixed point argument, and then you can obtain your existence result from where, if I think I've 2 minutes, 1 minute, from where you can obtain how do you obtain the lower bound estimate? So you have the initial data for which you know exactly the behavior as t goes to 0 and X goes to 0, which is given essentially by these two first terms. And then you get this extra term coming from the perturbation of the operator R. And that is the term that you need to control. Now, that term is non-local. Okay. But if you control the L1 norm of F, and that's the hypothesis you do for the corollary. If you control the L1 norm of F, you will control the L1 norm of this term. Now, if this term is in L1, if this term is in L1, and if you suppose that F is also in L1, you get a contradiction because this guy cannot be in L1 of any small interval. So that's where the contradiction comes from. If you suppose that F is in L1, this quantity here will be in L1. And then this guy, if this is strictly positive, of course, this guy will be in L1, and that's impossible. So that gives you a contradiction. And from there, you deduce the instability result. And I hope that's something I'm still working on, but everything shows that you will not have integral solutions for the nonlinear problem. So thank you very much for your attention. I think it's time to finish now.
Thank you very much, Miguel, for the nice talk. Now it's time for questions or comments. Yes, Enrique, please.
Okay, thank you, Miguel, for the talk and for so many things, right? So many years. So thank you. So finally, the conclusion is what? Is you do a linearization, you get L1 solutions, but then when you go back to the nonlinear, they are not.
You cannot get L1 solutions.
But for the linearized, you do.
No. You get solutions that are in L1 with the weights.
Oh, with the weight.
X alpha times F is integrable, but not F.
Yeah. And then once you have the linearized, you have understood the linearized problem in these weighted L1 spaces. In the nonlinear case, what do you get?
So in the nonlinear case, I'm still finishing it, but I suspect strongly that you will not have L1 solutions. So the impression is that the equation is bad behavior as soon as in the neighborhood of this maximal steady state. Okay? If you perturb this steady state to get something bigger or with a higher number of particles, the equation is bad behaved.
So there is no way of giving a sense to the solution after beyond this
even to define the weak formulation. You see, you need to do some. You need to apply Fubini, just like in the PDs. You need to do some integration by parts.
Right. Maybe there is some renormalized thing or something like this. Yeah. And what do you, if you look in the PD setting, of course, for PD people, the PD looks nicer, although we see these ugly weights, right? X squared, X4, and so on. If you look at the problem in the PD setting, do you see any better? I mean, you understand better?
The PD also has a problem.
Is that what? Is a boundary condition at X equals 0, or what is the?
Yeah. So I don't know how to go back. So let me see if I'm able to go back in this. If one goes back to the PD.
No, you stop sharing your screen, Miguel.
Yeah, this is the strong solution to go back. So
it's a strong solution. So if you go back to the PDE, you see there is a convection term, this du square over dx, that is pushing everything towards the origin. And in finite time, you lose. If you want to look at the PDE, you need some boundary condition. So the natural boundary condition is to put something that preserves the total amount of particles. So the integral of the right-hand side is 0.
Yeah, so some flux condition, right? Yeah.
And this condition is lost in finite time.
Okay.
Because everything is, so you get a very strong gradient near the origin. And so X square times du square over dx is too large, and so not for all the solutions, but a lot of solutions you will lose the boundary conditions. So,
and is this related to being, say, near this maximal steady state, or this is a completely different phenomena? What you are telling now about
it's probably related, because
Yeah.
you also need to be very concentrated. So as the impression is that as soon as you have strong gradients near the origin, your solutions will have, you will have problems. So in the PD, you can solve the problem, because the PDs are much better, of course, as we all know. So you can solve the problem. But in the case of the Boltzmann equation, I don't think that you will be able to solve the problem.
And so the way, so there is a kind of subordination of the PDE to the Boltzmann, but you cannot go back, or you do?
So if you assume the relation is not complete, so it's not very clear. If you suppose that if you regularize the kernel omega that I wrote, that omega function, and you put something that is regular, then you can expand, and then you can prove that the solutions converge to the solution of the PDE. But you need to impose a lot of conditions. In particular, you need to have a regular kernel.
And what kind of technique you use to pass to the limit? Is again some kind of Fourier or
no. In that case, is there is a small parameter in the Boltzmann equation that I didn't wrote because I wanted to simplify. There is a small parameter which depends on the temperature of your gas. So when the parameter goes to infinity, formally your kernel goes to a Dirac measure along the diagonal x equal y in the integral.
Okay.
And so formally you converge to something which is a diffusion equation.
Okay.
So what if you replace the kernel I wrote by something more regular, and if you take a good initial data to have regular solutions, then you can pass to the limit.
But pass, I mean, in the functional sense, right? Not only formally, but in a rigorous setting. Yeah.
But you need to impose a lot of regularity conditions. Okay, so I don't see how you can expect something like that with a real physical. But it's not very surprising, because the equation is you have neglected a lot of phenomena in the physics, and so probably the equation is not robust enough to consider all the possible cases. So if you are below an equilibrium, everything goes well. You have everything is bounded, regular. So the equation is. But if you get something too large somewhere, or then the equation seems to have a problem. So that's my impression.
Okay, thank you, Miguel, again.
Thank you. Are there any more questions or comments? No? Okay, so thank you, Miguel. Thank you again.
Thank you.
And we'll restart in 7 minutes with Rafa Uribe. I think he's there, yes.
Do you listen me?
Maybe we can start. You don't think
You listen me?
so, Carlos? Yes.
Okay. Let's move.
Do you see the presentation?
Yes, very clear. So we give 2 minutes if somebody connects.
Only.
Your talk.
Do you see the next page?
Yes.
Okay, perfect. No problems.
Okay, so we resume now. So it's a pleasure to present Rafael Oribe. Rafael was one of the Enrique's students, so he's my brother, I will say, but also he was a student of Carlos Conca. And so he get his PhD at the Universidad Autónoma de Madrid and at the Universidad of Chile. And he's associate professor in applied mathematics at the Universidad Autónoma de Madrid. He's also a member of the Instituto de Ciencias Matemáticas since its creation in 2007. So he's going to talk about the spectral gaps in planar waveguides. So thank you very much, Rafa. No, your microphone is closed.
You are mute.
Okay. I have a microphone. Yeah. First, it's a pleasure to me to participate in this Congress. I thank to the committee for this invitation to participate. I know Enrique 25 years ago, too much time. He was my professor in the last year in my graduate students in Complutense. I knew this year I met Enrique changed my life. No, I began my students PhD students with him and with Carlos, and all this time was crucial for my career. And I think that also now is colleague, and of course it's a pleasure to me always talk with Enrique. Always I learn something with him, and of course I very thanks with the friendship with him. Okay, well, the talk is about the spectral gradient planar waveguides. Is a problem different of other areas that he worked in, Enrique worked, no? But there are a lot of relations. I told about them. Okay, this work is with Delfina Gómez, María Eugenia Pérez, and Sergei Nazarov. Delfina and María Eugenia was professors in Universidad de Cantabria, and Sergei is professor in University of St. Petersburg. Okay. Let me see. Yes.
well, the weights, I think that Enrique, a lot of the works is about the weights, no? About also about the study of the eigenvalues, the asymptotic behaviors of the eigenvalues, etc. No? A lot of problems of control or asymptotic behavior is related with the eigenvalues and with the eigenfunctions. And this area now of my work is related with this thematic, with the asymptotic behavior of the eigenvalues. Okay, in homogeneous problems, the ways is natural to construct the behavior of the solutions. But in homogeneous media, the propagation of the weights are very difficult, no? Are very difficult to control, to study, because the behavior is quantitatively different than the homogeneous case. The reason is the scattering and interference of the medium is translated to the weights, and the behavior is more difficult. Okay, there are two areas of work about this thematic. The area that I work is in periodic media. In the periodic media, we can find the multiple scattering can manifest to obtain the stop bands or gaps in the frequency. This is very important because these gaps get passing down zones for waves where the waves now translate to other regions or stable solutions. This is to identify to the stopping zones. This is very important because these results is necessary to different engineers, different applications engineers. For example, wide filters, wide dampers. This is very common for metamaterials, etc. Okay. In the disordered media, these problems are related with the Anderson localization. No? The Anderson localization says us that in the random media or disordered media appear exponential localized models, in particular appear gaps in the spectrum. Well, what's happened when the natural is the period media is almost one disordered media, or very near on disordered media, and with the periodic media is we obtain these situations, these gaps in the spectrum in particular. Okay, this area of work is very natural for Nazareth in the last almost 20 years, but there are other people like Baccarat, Borisot, Giuseppe Cardon, Hempel, Peter Kuzmin, Olaf Post, Rasolainen, Taskinen, etc. A lot of people, more of the Russian people, no, war in this area. Well, the problem that I study is easy. No? Well, is not very sophisticated. No? We study we work in some domain. This domain, like this, okay. This domain is a street. Is a street in all the real line, okay, and is bounded in the second direction in the vertical line. It's bounded always with side with size h, and we had a periodic design, one periodic design, that in the vertical lines we had a lot of small holes, okay, only in the points that we translate with the integer numbers, okay. With these regions, we can define the periodicity field only with the domain 1/2 when the length is 1 in the h1 direction, and the length in the second direction is h. And in the center of the domain, we appear all the multiplied holes. All the holes are the similar, are the same design. No? This design is, in general, is a smooth function, is a smooth hole. It's possible to work with more sophisticated holes. Okay. In particular, is the problem, or the natural problem to work here is translate the problem in all the band only in the periodic set. Okay, I saw it in the following problems. Okay, the spectral problem that we are working is the Laplace operator, only the Laplace operator. No, it's necessary to work with the other difficulties, and with two different situations, with Dirichlet problem in the boundary, or with the Neumann problem in the boundary. There, with these conditions, we obtain two behaviors completely different. But the analysis to work in these problems is with the same techniques, and the problem is appear that the results to obtain are completely different. It is necessary different techniques to obtain this. Oh, okay. The first result, well, we know, is the spectrum of these problems is a union or innumerable subsets, the connected boundary segments in R plus. These subsets are the bands. Is now the bands. Okay. What happened with these bands? Well, these bands is possible to intersect or not. In the case when no intersect, it's possible to appear gaps. Is one of the objectives of this problem. We studied what is the limit of what is the limit, what is the behavior when epsilon is small in these problems. In particular, we describe the spectrum when epsilon is small. To obtain the structure of the band structure, it's natural to the classic. It's natural to use the Floquet-Both-Gelfand transformation. Okay, in differential equations is the first author work in this thematic was Floquet. He he worked in the theory of Floquet, and with this he obtained all the discompositions in the spectrum in one-dimensional equations of second order. For PDEs, the result is in the Passigal with Bloch and Delphi. The idea is a very popular idea. I'm sure that Carlos now saw these problems. Is the transform or Bloch transform that what's happening in the Bloch transform is we translate, we construct the solutions that translate by a way. Okay. With this for the function, the functions transform in other problem. This problem always is in the periodic cell. Okay. In this case, the periodic cell, remember, is the domain 0, 1. In the scale, in the variable is 1. And in the second variable is in 0, 8, and with the zeros, with the holes in the vertical line. Okay. In the Dirichlet problem, I had a Dirichlet condition in the boundary, and in the Neumann problem, I had a Neumann condition in the boundary. But in the boundary, that is the intersection with the boundary of the street. Okay. In the other part, the boundary of the cell, we put the quasi-periodic conditions. That is the necessary condition by the transform, the Delphi transform. This saying that we have periodic conditions, but multiply by the way. Also in the derivatives and the derivatives and the functions and the functions. Okay. I use the classical formulation for operators. I need to work in particular space. In particular, I work space A, but the space A is the is one space with boundary conditions Dirichlet in the region of the right of the left, and the other case, in the Neumann case, only is the H1 space, and also in two space is the quasi-periodic conditions in the vertical boundaries. Okay, I define these scalar products. I define the T-epsilon operator to traduce the operator to the problem of the Laplacian problem. And this, I obtain this abstract equation, and the eigenvalues problems is traduced with other spectral parameter that this is 1 divided 1 plus the eigenvalue of the operators, or the Laplacian operator. Okay, with this operator is compact, the spectrum, the essential spectrum is 0. I have other discrete spectrum that correspond with the these eigenvalues where we can get the eigenvalues of the Laplacian operator. With these eigenvalues, I have a sequence, the positive numbers. In particular, for Neumann problems, it's possible that the first eigenvalue with theta is equal to 0 is 0, but when it is positive, it will be known that this is positive, okay? And I have a continuity relation of this function of the eigenvalues is a continuity relation that depends on the parameter eta, and the support of this the image of this function is one of the bands of the spectrum, and this is with this obtain the structure of bands of the spectrum of the Laplacian, also in Neumann problem and the Dirichlet problem. Okay. The problem is now go to 0, epsilon go to 0, what's happened. The problems are completely different if I work in Neumann or in Dirichlet problem. First, I work in Dirichlet problem, and this is very nice. It's not surprise, but the limit of the eigenvalues for any eta of the band, converge always only 1 point in the case of the Dirichlet problem. And these points, these values, these real values, are the eigenvalues of the Laplacian in the rectangle 0,1 by 0,8 with Dirichlet condition in the boundary. Okay, if you observe, you remember the third problem. In the vertical line in 0, I have all the holes. I have Dirichlet conditions in these holes. The solutions are continuities, very near of the holes always is 0, and we can see in the limit that the limits go to 0 in all the vertical line. Okay, this in at the top, at the bottom, always is 0, and we can extend the problem, the solutions by the structure of the transform of block transform. What happened when I translate 1? The problem what happened is 0 and 1, 0 in 0, 0 in 1, 0 at the bottom, and 0 at the top. In total, I have the rectangle with Dirichlet conditions. And the limit, this problem is very well known. The eigenvalues are known, are numerables, and the eigenfunctions are signs in the direction in depend is 1 and signs by depend is 2, normalized by the structure of the rectangle. No, in particular appear divided by a's because the rectangular in the h2 direction is the length h. Okay. Of course, the limit of the problems of the eigenvalues and the eigenvectors, in particular the eigenvalues is obtained, but the eigenvectors are different. No, it's not the solutions of the Dirichlet problem. The eigenfunctions of the domain with the boundary conditions in the vertical lines in 1/2 and -1/2, we have a quasi-periodic conditions. I need to get these quasi-periodic conditions multiplied by this number in one of the region. I can translate multiply with any factor, I have to obtain other formulation for the eigenfunctions. Okay. Also, we can see that the eigenfunctions depend eta. Okay. It's important also this result because I can get a strong stability of the convergence. The convergence, also the eigenfunctions and the eigenvalues can be when epsilon and eta go to epsilon go to 0, eta go to any eta. Okay, and in this case, the limited is the same eigenvalue, but the eigenfunctions depend converge to aquí eta gor, eta ja. Okay. With these results, it's not sufficient to get the Kath structure of the Dirichlet problem. I need to know what is the behavior or the limit for any eta to get this. In general, the eigenvalues there are some when epsilon go to 0, there are problems that eigenvalues disappear, are small but disappear and go to infinity. There are problems with different eigenvalues. It's necessary to get uniform rates to this convergence. Okay, to do this, it's necessary asymptotic analysis. I show now the principal ideas of this asymptotic analysis. We consider an ansatz with the eigenvalue. I think that my eigenvalue first is the homogenized eigenvalue, and also any function depending eta by multiplied by epsilon. Okay. Equivalent, I had other expansion for the eigenfunctions. The first behavior is the homogenized limit, the homogenized limit obtained previously, and other function that multiplied by epsilon, and this function is necessary to see what is in particular this value also. And we are going to do a matching asymptotic, and to get it, we consider other expansion. This expansion is very near. This is the behavior very near of the hosts, and for this I need to construct some auxiliary functions that now I told about them, and there are some functions that depend on the derivative of the homogenized solutions in 0 and 1. That remember, the homogenized solutions go to 0 when x1 go to 0, and go to 0 when h1 go to 1. Okay, and these solutions depend also the way of the periodic boundary conditions in the vertical lines. Okay, well, the WB plus minus are solutions of are harmonic solutions, but are harmonic solutions in some special properties. I need solutions with some behavior in the limit. In the limit when H1, the modulus on H1 go to 0. The behavior of these functions as periodic condition in the direction H2 with these periodic conditions is necessary to work in the periodicity there, and in this case we need that the degree condition in the boundary of the hole. This is the problem is in all the street, okay, in all the for any x1 in R. Okay. The third say us that there are two solutions. Well, the solutions of these problems are combinations of two solutions. These two solutions are WB plus and WB minus, and we can construct the behavior of these solutions. In particular, these solutions, okay, is linear in infinity because one function, WB tilde, is with exponential decay. Also, C1 go to infinity or C1 go to minus infinity. And in infinity, this is the behavior is like the C1 derivative, and is necessary some constant positive or some constants in the direction 1, in the direction positive, and in other constants in the direction negative. In particular, is linear in the one direction, in H1, in H1, in positive H1, and is constant in the behavior is constant in the other in the negative direction, and the other function is the contrary, is linear in the negative edge, and is positive in the is linear in the negative edge and is constant in the positive edge. Okay, and all the solutions are combinations of these functions. For these solutions appear some coefficients. Is now the polarization coefficients is two matrices that the behavior of the constant behavior on the right on the left. Okay, with this these constants are very important to get the size of the gas. Okay, to obtain the estimates, the uniform estimates, we need some classical result. This is the classical lemma of near eigenvalues. This lemma say that you construct some function u epsilon star or u epsilon h, and some value m epsilon to get that I apply to this function to the operator, to the abstract operator, and the difference of these things in the normal or in the norm of the problem is small, and I can estimate this rate. When as a consequence of this, there is some eigenvalue that the distance, the eigenvalue to this value that I construct is the same rate that the estimate with the difference. Okay. Well, the values that I use is the two terms of the asymptotic behavior of the eigenvalue, and the function is a collection of different different functions that the homogenize the solution, the U1 solution, the U1, and the inner functions of the asymptotic analysis. Well, these functions, I obtain this estimate. This is important, but this estimate is for any eta of the domain, any eta of the dual problem, and depend the sum constant and depend for any epsilon sufficiently small to get this estimate for any n. Okay, these constants and these epsilons depend the eigenvalues when I work. But other consequence that we obtain that is not trivial is there are no seeds other eigenvalue that satisfy this. Remember that the lemma say us there exists some eigenvalue, but this eigenvalue is not the unit. But we can obtain that this eigenvalue is the unit. This is for consequence of the strong stability of the convergence that we have for this problem. The value of the function lambda 1 is now and depend of the coefficients of the matrix of polarization. Okay, and also depend the derivatives of the eigenvalue or eigenvector or the homogenized eigenvector. This is natural in general in all the problems of the homogenization, but these coefficients are different than other situations. Okay, I have some relations with the coefficients. I have properties, but it's not important. But it's important to get values to the length of the gap, no? In particular for the structure of the eigenvalues. Okay, remember, yes, because I take some eigenvalue in particular. This eigenvalue depend to values. The n is the respect to the derision h1, q is the depend of the derision h2. With these values, I know what is the eigenfunctions, and I know what is this parameter. This parameter depends the cosine. The cosine, the maximum value is positive, is 1, or the minimum value is -1. Multiplied by this number, we can obtain the maximum value of this. In particular, I obtain that for this eigenvalue, the length of the eigenvalue only depends of the parameter in the one's direction. Okay, and the length of the gap is the other ratio. Similar analysis I can obtain with multiplied eigenvalues, but I must know I'm not told about this. But in particular, I have this picture to show what is the behavior that we obtain. No? In particular, I can obtain that any band is the order epsilon, depend the eigenvalues, of course. They are different, the order one with the other eigenvalues, because always are multiplies on natural numbers, divide the a's. This is also depend the a's. If this a's is very small or very large, the distance of the eigenvalues is more small. But with a's phase also I can construct this Gath structure for the eigenvalues. For the Dirichlet problem, the Gath structure is very easy to obtain. In fact, when the eigenvalues are multiplied, I have estimates and I get estimates for any band. In particular, the sum of the bands is the order epsilon, and we happen the similar case where the problem is this band is possible that there are intersections in these bands. Okay. Well, for the Neumann problem is completely different, because the limit, the homogenization problem, or these eigenvalues is, well, disappear the holes. The holes, we can extend the solutions because it's the Neumann condition, no? And only have the problem with Neumann conditions at the top and at the bottom in the H2 direction, and the quasi-periodic conditions or the periodic conditions in the lateral boundary. Okay, with these conditions, the eigenpairs depend on parameter eta, and we construct a family of parabolas. This is parabolas, and now that's the curves of dispersion, and now to show in the picture now. And the eigenfunctions are with me now, but it depend the weights and depend the eta. Depend the eta with respect to the direction is one. Okay. Well, the dispersion curves, I only work with in the region minus pp. Any parabola is the reflection with the HP and the A's minus P. Okay. This is one parabola, and the second parabola is at the bottom, because remember, the second parabola begin when n is one, and when the first case is eta n equal to 0, and the second case is n equal 1, and is always is positive. Okay, this is for the second. Okay, here the first dispersion curves now depend the H2. The second dispersion curves depend the H2. Okay. Well, its H is sufficiently small, like the eigenvalues are divided by H. This dispersion curve is in the top, and it's more easy to work in this case. When this is the case when H is less than 1/2. The second picture is when the H is about 1/2 and 1, and the second dispersion curve go to the bottom and intersect the first reflections of the dispersion curve, or the first dispersion curve. And when the H is very large, the problem that appears is the dispersion curves are very near one of others. This is the first and the second. Of course, they are the third and too much. No, when I go to the limit, epsilon go to 0. There are the perturbation of the dispersion curves, and the result that I want to obtain in this problem is for when the second dispersion curve is out, is not in the regions that I can work, I can obtain gaps of the spectrum. In particular, I can obtain one gap in p squared, around p squared, another in around 4p squared. This is for A's less than 1/2, and when A's is less than 1, only I have the first gap. It's possible that appear others, because it's possible, for example, that this is go to 0, this is go to the bottom, this is go to top with different values of A's, and appear other in other regions. But this is in a special case. Other possibilities is in the case when A's is very large, when this A's go to very near to the other. I think that when A's is very, very large, it's possible that obtain other gas in this region. But this is problems. This is open problems for continuing to the war. Okay. Well, I don't know what time.
You are running out of time.
Okay.
In fact, so if you can finish, please.
I finish with very fast. I had the limits. I obtained some estimates. The problem what happened is I don't have the problem of the lemma of the near eigenvalues is I don't identify. I know there are one eigenvalue, but it's possible there are other eigenvalues. Here there are a lot of eigenvalues. Is a problem. I need to work in different regions. I get some estimates in these regions. For example, in this box, I say that only I have one eigenvalue. And in the second box here, I have two eigenvalues. If I have one eigenvalue in this region, I can uniform estimates for this region. In the other region, it is necessary work with delta very small to obtain asymptotic analysis. I get asymptotic analysis. Okay, in the asymptotic analysis, I obtain that there are two eigenvalues in this region, and this is separate because I identify these values, and these values are sufficiently large. One of them. Okay. With these estimates, I can obtain the gap for this region. For the second region, I need asymptotic analysis in 4p². And finally, I obtain the result of the picture. No, in some situations I have two gaps. In other situations, I have other gap. When S is very large or more large, is open problem to obtain more general case of gaps. Okay. Thank you very much. Let me see. Thank you for the attention. Congratulations to Enrique for this birthday, 16th birthday. Okay. Thank you.
Thank you very much, Rafa. Are there questions or comments? Please raise your hand. Or...
I have one question only.
Hernan Oscar, okay.
I would like to know about some application, physical application for the problem, for the connection, the classification. The theoretic classification with the physical meaning application. Also, I would like to know if possible to obtain negative eigenvalue for another dimension. I know there are negative eigenvalue in another situation when the study manifold structure. Thank you very much for the aniversario, Enrique Zuazua, Hernán Cortés. Greeting for you.
Gracias, Hernán.
Muchas gracias también, profesor Zuazua.
Thank you, Hernán. Well, for this case, the eigenvalues are always positive. No, it's impossible to get the negative eigenvalues. In other problems, for other operators, you can obtain the situation to. This is this is very natural to, well, very important to get for metamaterials and etc. It's true that I remember some paper with Carlos where we study in the behavior, the values in the homogenized problems. We study the tensor, the fourth tensor. In the fourth tensor, we obtain a negative sign. Do you remember, Carlos?
Yes. Perfectly. Yes.
In particular, this is the Barnett coefficients, no? I remember, no?
Barnett,
and
it's a four-order term. Yes.
Exactly. With this, in this case, for this problems, you can obtain this property, no? But for here, no, because always the bands are positives for the problem. Okay. These techniques to obtain asymptotic analysis is applied for different problems. This is the classical matching techniques, but are very, very complicated and very hard to work with them.
Okay, thank you. But
yes. I have just one very brief comment to thank. I would like to thank Rafael for his very sharp result and strong result. He has been able to highlight new phenomena in the asymptotic behavior of the eigenvalues of homogenization problems. So congratulations, because there is a lot of things that I was not able to grasp in your presentation because I will need some more time, a lot of time, maybe. And congratulations also to Maria Eugenia and Delfina, because they have been working on this asymptotic behavior for a long time. And these results are quite impressive and very sharp. You have been able to measure the gap between these block intervals. This is the first time I see something like that. And the other phenomena that I would like to highlight is the fact that the convergence of continuous spectrum to something which is discrete. So we don't see spurious eigenvalues at the limit.
Yeah.
This is extremely surprising. This is the first time I see something like that.
Well, to get the result is not easy. I assume that this is for very special case, no? Well, also the domain is not homogeneous, no? But it's very symmetric and don't have problems with boundaries or something, no? I remember the results of Gregoire or your problems, no? Where get these disappearing eigenvalues, no, or invisible eigenvalues. So I don't remember
spurious eigenvalues.
Exactly. Well, thank you for comments. Because yes, the one of the principal results of this problem is we study the homogenized limit. Well, the periodicity cell is a homogenized limit. In general, this is not the problem, because in general we work in the periodicity cell. In the periodicity cell is phase. No, here is no phase. Here is a other limit. No, we have double limit in this problem. No, we have one periodicity structure in the line in the horizontal line in periodicity 1, and the other periodicity is the order epsilon in this other periodicity, this other period structure is in the periodicity thing. And we need these auxiliary functions. I put only the auxiliary function that appear the polarization coefficients or in the work, but I need different other functions to make the matching, the correct matching. Is a very hard work. And all these ideas, or one of the principal ideas, are for Nazarro. Nazarro is a very special
the Russian school.
This area. He's surprised that he worked with these functions without problems. It's incredible. It's incredible. And Delfina and Maria Eugenia, yes, fantastic girls, worked very, very well with me. I very happy with work with her. Okay. Okay.
So Rafael, we are looking forward to seeing these two papers published soon, very soon.
Yes, I think.
Okay, thanks again.
Very much. Thank you very much, Rafael.
Can I add something, Lucero? Just a brief question. Okay, so Rafa, thank you for your talk and for how many years you say? 25 of friendship, right? Yeah. So yeah, you were very patient with me and also very courageous, right? Because I recall that you were a student in Complutense, and then there was this opportunity to go to Chile. I don't remember which project it was. And then we were looking for a brave young person to cross the ocean and go to Chile. And you said yes in real time, right? So as if you were born in my town, Eibar, right? So I see that in Burgos also there is some influence of yeah. Okay, so thank you for all these years of friendship and hard and excellent work. Just one question, Rafa, a bit stupid maybe. Of course, I understand the problem from a mathematical perspective, but my question was, so why an engineer would like to put holes on a waveguide? Is this something that is really done, or this is more a mathematical model? So I understand that, I mean, you will use perforations in many devices and designs, and in particular, to take advantage of the topology. But for waveguides, it looks like strange to put perforations, because this will probably end up trapping waves, right?
Mm-hmm. Well, in the applications to the engineers, I don't see the perforations. No, well, there are different materials that appear this structure. No, but I don't know if it's used to get the results. But there are other problems or similar problems, like for example in materials, I see that the electric materials with periodic conditions or with periodic behaviors in the line, with a very small structure in some special regions. No, it's not the same, but it's similar. And this is important, these materials, to get the interesting properties to the wave propagation, in particular to get the invisibility or something similar. Well, this problem isn't very nice, because the name, no, the street stands, no, because for the design of the problem, no, and always we work with the derivative of Neumann. The natural problem is Neumann, because the propagation is more natural to get Neumann conditions to continue the propagation than the Dirichlet conditions. No, the Dirichlet condition is very, very, very strong, but also it's possible to get not Dirichlet but almost Dirichlet. No, with mass concentrates FTC, then there are a lot of words, the Maria Eugenia and Delfina, for example. No, well, the this structure of the almost periodicity is very natural in different applications. No? Do you remember that these people in Valencia, no, that have a lot of structures to reduce the noise in the autoroutes, etc. No, there are a lot of applications. What happened? The engineers made the design. So the results of the reduce of the noise or the property that the people see, and it's okay. No, go out and patented this material is okay, and this is a mathematical problem, of course, and always in the mathematics. In a lot of cases now we are more slowly than the engineers, etc. No? This estimates this rates is not necessary for the engineers. No, have experiment, extend the designs and get the results. No, okay. Thank you, Enrique, for these years. I wait to visit to Germany, or I wait to visit here in Spain, because we are colleagues here. But I don't see 2 years for more time.
Yeah. I will see you soon, definitely. Thank you, Rafa.
See you.
Gunther has a question, but we are running
I just want to add to the discussion. So we were also working with Sergei Nazarov and Yari Taskinen on these bandgap structures. And in fact, with engineers, we talk in Erlangen. And when you come to Erlangen, you may want to discuss. I mean, you can also use elastic inclusions or even piezoelectric inclusions, and to produce these kind of bandgaps in real material. So there's good hope that this can actually be used.
True. It's true. Thank you, Lenny.
Okay, thank you, Rafa, again. So we continue with Alessio Porretta. Alessio is a full professor at the University of Rome Tor Vergata. His research activities mainly focus on convection diffusion equations, control, and Milford game theory. He has awarded the Miranda Prize for Young Researchers and the Fiquera Prize. He has given lectures in more than 20 countries in the world, including courses on Milford games held in Paris, Chicago, and ETH Zurich. His research papers collect more than 1,500 citations in math journals. He's going to talk about time decay of Fokker-Planck equations with confining drift. Thank you, Alessio. Can you share? Yes. No, I think I have to activate your microphone. Okay.
Okay, so I think everything should be fine with the, okay, so maybe I can hide here. Okay, so can you hear me and can you see the slides?
Yes.
Okay, great. Okay, so first of all, let me thank the organizers for this invitation. I'm very happy, and also I'm honored to be here to celebrate Enrique's birthday. And this gives me the opportunity to say how much I enjoyed actually my collaboration with Enrique. This was extremely stimulating for me, and really a big pleasure. And I only regret I don't have enough time to push all projects and all things that we could do together, but still we have time to do, of course, something together. And when I met Enrique, actually, I was much younger, and I also must say, as many other young people, how incredible aptitude that Enrique has with young researchers. And it's very rare, I think, for for someone of the quality of the outstanding rate as Enrique, to find someone like him who is always available to young people to discuss math. And then all our collaborations, I enjoyed them very, very much, and I learned a lot, and I'm still looking forward for other projects, of course. Okay, so okay, I must say that the topic today is actually a classical topic, but I must say where my interest comes from, and this is actually a sort of control problem. So this is a model coming from this mean field game theory. And okay, mean field game theory is a theory, I mean, suggested and developed around 2006 by Jean-Michel Lasry and Pierre-Louis Lyons, essentially to describe Nash equilibria in large populations dynamics. And so typically there is, I mean, the evolution of the population is described by a Fokker-Planck equation, where L is a diffusion process. It can be, I mean, just a Brownian motion with a drift term. It can be a non-local operator coming from a jump process. So it can be I mean, any kind of diffusion, I mean, process for the single agents, which describes the individual's dynamics. But the point is that this individual dynamics is then driven by the decisions, by the strategies taken by people, which in the simplest case is described by vector field, which means that typically at least I repeat, in the simplest model, one can say that this population is driven by a vector field, which comes from the strategy taken by individuals to achieve some goal. Okay, so and this means that typically there is a Hamilton-Jacobi equation for the value function of the single agents, and as is customary in optimization, I mean, the strategy is typically described by the derivative of the Hamiltonian function with respect to the gradient, say, of the solution. Okay. And so typically here H is a convex function, and F might be some coupling cost depending on the population. So okay, so the typical mean field game system appears as a coupled system where you do have a Fokker-Planck equation where the drift term is coming, say, from the equation of the strategy of individuals, which of course contains also the adjoint operator L and the Hamiltonian term, and this is related to the cost the cost functional to the goals that individuals want to achieve. Okay, I'm not entering here into really the mean field game theory because okay, I lecture many other times also in front of Enrique, and so I mean I will stick to a particular issue which is very close to also to one of my collaboration with Enrique, which is the long-time behavior of this kind of systems. Okay, in general, what you expect in this setting is that if the coupling term here, if this cost is anti-aggregative and is smoothing, so which means essentially that people would rather be where the density is not big, the density, I mean, of the other agents, then it is expected that in long time you might have this property, which is a sort of stabilization, which is a turnpike property, which might take this form that the solution U and M in time t are exponentially close to some stationary strategy, du bar, and some stationary, I mean, distribution of the population. And this, of course, does not occur at initial and final time, but it occurs essentially in a long intermediate time. So this is a property which is called turnpike property, and it was essentially one of the topics that I worked with Enrique, and actually the min-fill game long time behavior was exactly one of the goals and one of the one of the motivations for our collaboration, to discuss this property for general control systems. Okay, so we discovered many things with Enrique around this turnpike property. Many other people worked later. Also, somehow I can say that this notion was a little bit revitalized, maybe by our work, and then there are many discussions later. But today, I would like to focus on a particular issue here, is that when you want to show this kind of property, you see that this min-fill game system, in the audience, you might not know anything about min-fill games, but certainly you will recognize here the structure of an optimality systems, okay? So you typically can recognize this system as a typical structure of, say, a state equation and an adjoint backward state equation. So if you want to describe long-time convergence, typically you need an interplay here between the long-time convergence of the Fokker-Planck equation and somehow the backward stabilization of the Hamilton-Jacobi. And in order to prove this kind of result, you definitely need some quantitative decay estimates. For example, this is just an example, you may need for a Fokker-Planck equation some kind of semigroup kind of decay. This is sort of coming from Duhamel formula, or you may need some global in time LP estimate, where you see those constant C is independent of the time horizon. Okay. So this led me essentially to go back to the problem of the long-time stabilization of Fokker-Planck equation, which is the heart of this talk. And there is one crucial point here, is that in general, in this kind of situation, as is often the case in optimal control problems, you need very robust estimates. So, for example, you may need this kind of estimates for drifts which are time dependent, and you may not know, you may not have very much information on the drift B because it comes from the other equation. Of course, there may be some information that you may get here, but in general, you do not have explicit forms of drift. And this means that you really need a robust study of this decay of Fokker-Planck equation, or say decay. When I say decay, I mean long-time stabilization. So this is, I think that, all people who have worked in optimal control problems know very well that at some moment you need those properties of the state, maybe equation, or of course, or the adjoint state. And you need very robust kind of estimates that if you look for in the literature, maybe you are not able to find anything exactly in the way you need it. And so I think this is a very common motivation to go back and revisit even classical issues. So now I will so somehow extrapolate this problem. How do we prove, and what do we know about this stabilization of Fokker-Planck equations, so the trend to equilibrium? So this is a very classical problem. If you take a diffusion process and perturbed by a drift, and then you want to show that your solution, which is a probability density in RD, converts towards a stationary state. Okay, so this is not for free, first of all. And it is well known, this is related, first of all, to the ergodicity property of the process behind. Okay, ergodicity takes this form here, for example, is that the observation that you can take along the evolution of the process, which is the generator of this diffusion L. If you take the time average of these observations, then in long time, this average converges towards some observation, which can be just described by this stationary measure. Okay, this is a typical, it might be a definition of ergodicity, for example. And the mode, of course, this is not for free. If you consider the Brownian motion in RD, well, of course, this is, I mean, you need some property that enhance ergodicity, and in particular, this leads you very naturally to situations where you have not just a pure Brownian motion, but for example, an Austen-Uhlenbeck process, which means a Brownian motion plus a confining drift. Okay, so this is quite well known, of course. So a typical situation where you may expect this kind of stabilization in the whole space. Of course, I mean, you may consider results in a compact situation, but this is, I mean, this is less difficult and is induced essentially by compactness of the state space. Whereas when you are in a non-compact situation, like in RD, in the whole space, you need some property of the diffusion process behind, and in particular in this diffusion process L, or eventually in explicit form in the drift, you may need some confining property which says that the process does not escape to infinity. Okay, so this is all well known for the Brownian motion in particular, and it's convenient for my purposes to rephrase this problem in the sense of time decay for zero average distributions. Okay, what you do in linear problems, typically you have the existence of a stationary measure, and then you subtract, of course, the evolution and the stationary problem, and then you look for the stabilization of the semigroup for zero average distributions. Okay, so in this form, you may afford, for example, here in this kind of context, you now may discuss this decay properties even if the drift is time dependent. Okay, so now I'm trying to summarize what is known, for example, for the Brownian motion case, and what is known is that you have an exponential decay for zero average, say, distributions, for zero average solutions. So here, of course, this property is preserved, I mean, after integration by parts. And then, for example, for the Austen-Uhlenbeck semigroup, this is when the drift is sufficiently confining at infinity, you have this exponential decay. But if the confining property is a bit less strong, so typically this is for sublinear growth at infinity of the drift, then you might have a subgeometrical rate of convergence and, for example, polynomial decay. And I just want to mention the space X in which you are proving this kind of exponential decay is typically an L1 weighted space. This is very natural. We have seen something also similar in Miguel Escobedo's talk. When you are in this non-compact situation, well, there might be quantities which naturally enter into the game. And for example, a natural choice here will be some L1 weighted space, and the weights might be a power of X, which, okay, I'm using this slightly, I mean, modification of the power just to say that all the point here is at infinity, or the point of the weight here is at infinity. Okay, so this of course implies the decay in L1 norm if this power is positive, as it will always be the case, but as a price, and the price is that the initial distribution needs to have some finite moments, okay? Okay, so there is, I must say that there is a very huge literature on the stabilization of Fokker-Planck equation, and I will try to give my viewpoint on this literature. I actually learned a lot when I had to look at the literature, even if I could not find exactly what I needed, and so somehow I decided to go a little bit more deeply into this, the way things are proved. But okay, so starting from the classics, I would say, there is a very typical approach, which is a sort of energy and entropy methods, I would say, which most often applies to the case where the drift is the gradient of a potential. So this is related to variational methods. And it starts, I mean, since some celebrated results by Gross and then by Liggett and many others later in semigroup theory. So starting from the exploitation of the spectral gap in weighted L2 spaces. And this is related to the logarithmic Sobolev inequality. And this was essentially the proof given by Gross of the exponential decay of the Orsten-Uhlenbeck semigroup. But then those methods had a sort of, upgrade or update, if you want, in the early thousands, in the early years of this century. And in particular, I mean, rather than discussing somehow the decay in weighted L2 norms, it was pointed out how natural it was to discuss the decay of the entropy or relative entropy of the measure of the solution M, relative again to some weight. And you see how, again, in both approaches, it's a very natural way to have weighted estimates. Very natural to have weighted estimates. Okay, so this kind of entropy dissipation methods were in particular developed by Giuseppe Toscani and by Villani, and they became very, very popular after the works by Villani, who was a wonderful, he popularized this method as usual in his wonderful way. And of course, there were many contributions, in particular by Markovic, and Carrillo used that a lot as well. Okay, so of course, this relies on functional inequalities like Poincaré inequality and logarithmic Sobolev inequality, and there's many connections with other important structural conditions like the Bakry-Emery conditions on manifolds. So it's very elegant approach, but there is maybe a drawback in my viewpoint, is that it's hard, first of all, to be generalized to very general diffusions, including non-local diffusions. So there are extensions to fractional Laplacians, but they already need quite precise forms of the drift. And so, I mean, even if those methods are very elegant, I would say that there is some drawback to have results in very large generality for the drift, in particular for time-dependent drifts, and somehow also for non-local diffusions. Then there is another approach by probabilistic methods, essentially, and I learned that from papers by Martin Ivern and Mattingly, but of course this dates back to much earlier works, in particular by Mine and Tweedy. And the typical idea of these methods is that if you look at the semigroup generated by, say, the Fokker-Planck plus the drift, then there are two properties which imply the exponential decay. So those two properties are the existence of a Lyapunov function for the adjoint operator A star. And you see, it does not need to be a global strict Lyapunov function, but just say a Lyapunov function outside a compact set. This is the spirit of this condition. Of course, I didn't mention there is a phi which is a Lyapunov function. So essentially, it goes to infinity at infinity. So it's a typical Lyapunov function, and it is a strict Lyapunov function outside a compact set. But then you also require the property that your semigroup enhance positivity in compact sets, like a sort of Harnack inequality, and that your measure is strictly sort of diffusivity property, you see, in compact sets. And those two properties give the exponential decay of the semigroup. And again, very natural space X is a L1 weighted space. In this case, the weight depends on the Lyapunov function. I must say that I like this approach very much. And then there are many developments later, in particular after this very deep work by Bakri, Catio, and Guillen in 2008. And many authors also mixed somehow the methods of the energy and entropy dissipation with this kind of approach by Lyapunov functions. And in particular, Michler worked a lot on that, and there are many contributions with many other colleagues. And these methods were also extended quite recently to non-local operators by Laflèche. Okay, so even if, of course, I mean, many ideas are already there, I am trying to suggest sort of a new approach, which is a sort of analytic. My opinion, it's more natural from the analytic viewpoint, so from the PDE viewpoint, rather than some of the ideas which here were taken essentially with probabilistic methods or with analytic but quite difficult argument. So I'm suggesting a simplification and a generalization at the same time of some of these ideas. So first of all, the point is that if you look back at this approach from the probabilistic viewpoint, you see that it combines two properties. One is a property of the adjoint operator, so it's the existence of a Lyapunov function, and the other is a property of the operator itself, which is a sort of preservation of positivity. When you are in applications, it might be difficult to check this latter condition, because somehow it requires you to prove itself a new Arnack inequality. So it's clear that from this approach that those two ideas lead to the exponential decay. But when you, for example, need this for your specific problem, for example, in my case, I had this Minfield game system, and then I looked at my Fokker-Planck equation, and okay, I am not exactly in this framework. I must try to understand whether I do have this kind of property for my semigroup. It's not so straightforward. So I was looking for something which was somehow more readable and more user-friendly when you need something. And the first point is that my first remark, this is essentially more a remark, is that the decay of the Fokker-Planck equation can be entirely deduced by the dissipation estimates of the adjoint equations, so of drift diffusion equations. And what are this kind of dissipation estimates? Those are weighted oscillation estimates for the adjoint problem. So in this adjoint problem, so I have put it in the forward form. Of course, you can rephrase that in the backward form if you prefer. Of course, you do have the adjoint of your operator L, and you have your drift now acting, in non-conservative form. And in this case, it's out of question that you have global estimates for the function u, but the ergodicity is observed in oscillation estimates. So the oscillation of u could be globally estimated once you do have an ergodic phenomena behind. And so I am introducing here a semi-norm for u, which is a weighted oscillation, and this weight is typically the Lyapunov function. And okay, you may just limit yourself, to this case when you have a Lyapunov function of power type. And the typical result that I will prove in this case is, I just have here taken a sample case of the fractional Laplacian, which is a way to show you that this method applies to both local and non-local diffusion. And of course, the prototype is the whole range of fractional Laplacian, but does not need to be the fractional Laplacian. I'm not using at any level Fourier transform. This is can be extended to jump processes, which are not necessarily, the Poisson process or fractional, pure fractional Laplacian. Okay, and so what is the typical estimate I have in mind, and I can prove is sort of theorem A is that, okay, you assume that your drift is sufficiently confining at infinity, and you have some other dissipative condition. I mean, this may depend whether you have a bit more of diffusion in the operator or a bit less diffusion in the operator, okay? And those conditions, so for example, if you take here the case of alpha above 1, this is the diffusive case for fractional Laplacian, and of course it includes the Brownian motion, the Laplacian case. Well, this is not very hard to check this condition, because essentially it says that your drift B can be just locally bounded in compact sets, and at infinity it is a bit dissipative. But this kind of dissipation is very much also, in general, in agreement with the property you already have required on B. Okay, and then the conclusion is that there exists an exponential decay for this semi-norm. Okay, an immediate consequence is the sort of corollary theorem B is that under the same assumption, the Fokker-Planck equation decays exponentially, of course, for zero average distributions. Okay, so I am not, now I will skip here some comment, but I will just give you the proof, which is, of course, a duality proof of the corollary B, just to stress one point. Okay, of course, I mean, I want to deduce the estimates for the Fokker-Planck from the adjoint operator. So it's clear that I am evaluating my Fokker-Planck equation along a backward, say, solution of the adjoint operator. And then this is the only, say, the basic remark here is that, of course, since you are with zero average distribution, you are free to add any constant to the adjoint state. And here you just use your, say, your L1, L infinity weighted duality. And then you simply remark here, and this is something I learned from already one of those approaches by probabilist, is that it's very convenient. Of course, this is, once you think of that, this is, of course, an exercise, but it's convenient to remark that if you take just the infimum among all constants of this L infinity norm, then you just get the semi-norm that I introduced above. Okay, so this means that I can just minimize over C this inequality 1, and once I minimize over C, I estimate the L1 norm of the Fokker-Planck just in terms of the semi-norm of the adjoint operator. Okay, so okay, I must say I'm a bit confused with time, because since we started with delay, so can I ask how much time I do have?
5 minutes, if you want.
Okay, 5 minutes. Okay, because we started very late, so I mean this confused me very, very much. Okay.
It's not like 5 minutes late, and okay, so.
Okay, I thought. Okay, I'm okay. Okay, I will try to shorten a little bit. Okay, of course, there are similar results for the slowly confining case, which means that the drift is a little bit less strong than the Ornstein-Uhlenbeck. And for example, and in this case, you with the same method, you deduce a polynomial decay. For example, this is I mean, a situation where if you use functional inequalities and so on, you have really to strongly modify the approach to go from say the logarithmic Sobolev inequality. You have to prove every kind of weak Poincaré inequalities to go from the, say, strongly confining to the slowly confining, while in this kind of approach, I mean, this is exactly, I mean, you don't need to change anything in the approach, except you just observe the different quantification in this method. Okay, so the main novelty, as I was saying, is that the decay of Fokker-Planck equation is entirely deduced by the decay of weighted semi-norms for drift diffusion equations. And if you rephrase this, so I'm trying to give you now a little bit more hints on the method, because you see this kind of estimate can be rephrased just by, okay, so this is equivalent to property 3, just rewriting the semi-norm, which is here. Of course, the weight now has been put in the right-hand side, so this is equivalent. But the main point here is that rather than proving directly 3, it's okay if we prove, I mean, the inequality for any bounded function psi of the difference of x minus y, of course, the distance between x minus y. Of course, if psi is bounded, this will be dominated by the Lyapunov function, so 4 implies 3. But the true inequality which you should observe in this kind of equation is inequality 4, for a reason which is probably clear if you reason in terms of interaction of your process starting from, say, x and y, because essentially this term psi takes care of the small range interactions. And while, of course, the long range interactions can only happen at infinity, and they are dominated by the Lyapunov function. So you see that in a single estimate, I am taking both properties that were required by the method developed by probabilists, in particular by Heirer and Mattingly. They were requiring that somehow you had this Lyapunov out of a compact set, and you had this preservation of positivity for the semigroup. But here, both properties are contained in a single estimate, because essentially when the difference between x and y is small, you have some diffusivity property which appears in this term, and you use the Lyapunov function for outside compact sets. So, so essentially, all the method that I am suggesting relies in proving this kind of estimates for general drift diffusion equations. And this estimate is in particular an evidence of ergodicity. It was also known somehow in the probabilistic literature with, of course, totally different methods. And if you want improving this kind of estimate with a purely analytic proof, this is also an extension of what was known to probabilists. And the key point, but here I'm really running out of time, is that essentially to show this kind of estimates, the key point is to give analytic versions of what I mean in probability is known as the coupling method. And this is something I had developed partially already with Enrique Priola in 2012, in particular for local diffusions, that essentially we had explained in our joint work that there was a sort of parallel, and it was a perfect translation between probabilistic coupling methods and the double invariables PDE methods. And revisiting these ideas and extending them to no local diffusions, somehow you can also prove this kind of estimates in much more generality. Okay, so I will, of course, I mean, I had, I mean, this is just, I don't know if I have time, this is for people, of course, who never heard about coupling method. I can describe it very roughly, and the picture is maybe the simplest way. This is a reflection of the Brownian motion. So the coupling method is used in probability to say, if you want to estimate the expectation of the process starting from x and the expectation of the process starting of y, one of the tools they use is to reflect essentially this process and to build a new, what is called the coupling, so a new process in the product space, and to try to build this new process in the product space in the way to optimize the heating time of the diagonal. Because a coupling for probabilist is a process in the product space xy, so that when two processes, when I mean the marginals should be the same, and then when this process in the product space hits the diagonal, then of course it remains there. Okay, so of course I can say more, but I see that I don't have enough time, so I'm just skipping to conclusions. Is that okay, I'm suggesting a new strategy for proving the long time decay rates of Fokker-Planck equations in much generality, so for local and non-local diffusions and for time-dependent drifts. And this is a way to recover and often extend, I must say, many results obtained with many different methods. So it's a sort of also unifying approach. And as a byproduct, this gives an analytical approach of many results which were only known, proved by probabilistic methods in this coupling method literature of probabilities. And of course, this was motivated by my joint work with Espen Jacobsen on mean-field games. Unfortunately or fortunately, I don't know, this is a byproduct of the lockdown period. We had not the opportunity. We were a little bit stuck with some of these estimates with Espen, and then I decided to go more deeply in the literature, and then I developed somehow this approach, and then of course this was very important for us to complete then our joint project on the turnpike property of mean-field games in many cases, including non-local operators, which had not been done before. Okay, so that's all. I thank you for the attention, and happy birthday again to Enrique.
Thank you very much, Alessio. So are there questions or comments? Enrique, please.
Yeah, so thank you, Alessio, for this beautiful talk. So what is the regularity you need on B finally?
Well, for B, you just can take a B which is L infinity in the diffusive case, and a little bit more in the say non-diffusive, or if you want, so you see, let me just take the, okay, so you see here, right, just take as a prototype the fractional Laplacian. So when you have enough diffusion, so alpha is bigger than 1, you need two properties that can be formulated even for bounded drift. Of course, bounded at infinity must be coercive, must be confining, but the regularity, the local regularity, can be just L infinity, because I'm never using
kind of a one-sided Lipschitz condition or something like this, right?
Yes. If you want, there is some dissipativity on some part of the gradient of B, if you want. But you don't need, of course, the regularity to formulate this assumption. While you need a little bit more regularity here you need some regularity. Because this guy is bigger than 1, and this is because you lack a little bit of diffusion when alpha is below 1.
So actually, I'm asking you this because recently I was looking to references, but I didn't find much. Of course, there is a lot of works done for solving transport equations with non-smooth vector fields B, right?
Yeah.
The Bernard-Lyons and then many others after, right? But then when you look to the vanishing viscosity to understand how, of course, when the velocity field is smooth, it's very easy to understand what the vanishing viscosity does, right? It's basically you have transport and diffusion, right? This is what you say. But when the vector field is not smooth, I'm not sure there are results explaining how solutions behave as epsilon goes to 0 on the diffusion, right? Yeah. In a precise manner. Okay, so this is, but we can talk about this later. And then the final question, Alessio, was in this norm you have taken in which there is ux minus uy in the numerator and then x to some power plus y to some power in the denominator.
Yeah.
This space has a name, or where is this? This is not.
This is just. This is just a weighted semi-norm, if you want. And of course, I mean, if you have k equals 0 here, this is just the oscillation of u.
Right.
Okay, and then this is just a way of the weight enters at infinity. What is interesting, and as I said, I mean, I must say that when I found that, and then I realized, okay, that's true. I mean, you can prove this as an exercise, but it's important to notice here that this semi-norm is exactly the same as the infimum of u plus c in L infinity.
Mm-hmm. In L infinity, weighted.
Well, in this case, weighted because there is a weight here, but of course you can take the same for k equals 0.
And then in practice, what is easier is to deal with this differential quotient to the right, or rather with u plus c?
Yeah, okay, that's a good point, because I tried to show that it's very natural to get estimates in this semi-norm, and this is exactly what probabilists also were doing by this coupling method. So this is very natural for the estimates. But when you look at your adjoint argument for the Fokker-Planck, what you really need is this one. So the bridge, so it's, you see, because when you estimate the Fokker-Planck by duality, you essentially take profit of the fact that M0 is 0 average. And then what you see is that you have this 1 degree of freedom to add constants to the adjoint state.
Right.
So by duality, you would like to estimate that. But on the adjoint equation, the estimates come very naturally in this semi-norm. And then it's true that those two things are equal. And this is where there is a nice bridge. And or the argument, of course, is very, I would say, is very clear.
So do these semi-norms have a Fourier interpretation, or?
Wow, that's a good question.
Okay, but we can
I
talk
don't
about
know.
this. Yeah, but probably there is something, right? Yeah.
Yeah, sure. Because, okay, of course, to be honest, if things were smoother, like if the U were smoother, if the drift was smoother, similar estimates can be obtained just by weighted gradient estimates.
Well, actually, in the case where B is just X, then
yes,
you
for
have
example,
explicit,
if B is X, yes.
Yeah, Dermite polynomials with Gaussians. I mean, you have a complete spectral decomposition, right?
Exactly. If you are in a smooth situation, you can find similar estimates just by looking at the gradient of U and looking at weighted estimates for the gradient. Okay?
Yeah, but then in that case, there is a clear, say, Fourier representation of the problem too. Yeah.
Yes, exactly. So this is maybe the link you were thinking of.
Yeah, definitely. Okay. Thank you, Alessio. Great talk. Thank you. Bye-bye. Ciao.
Thank you. Please, Carlos.
Yes, thank you very much, Alessio, for your very nice talk. I have only a very simple question, because I'm not a specialist in this subject, but there is something which is not familiar for me in this identity of a norm, which depends on two variables, x and y. So this is a non-local term. For each value of x, you can see that y can varies all over Rd. And on the left-hand side, you have something which is local.
Yes. Okay, but yeah.
So on the right-hand side, you have something like what Enrique said, that it is some kind of Fourier norm, like in the space HS with fractional s.
Yes.
But on the left-hand side, you have something which is of a different nature.
Well,
of course, what you have on the right-hand side is must have plenty of advantage.
Yeah, of course, be careful that, of course, in the right-hand side, you don't have exactly, of course, say, an HS, because you see that you are not quotienting with the distance between X and Y.
Yes, of course, yes. It's
so this
different.
is, of course,
You have
this makes
X
it,
to the power K plus.
yeah, exactly. So this makes somehow it possible. In my viewpoint, of course, I was looking at that by saying, this is the translation of view that you see the C is here, okay?
Mm-hmm.
So somehow, I mean, I'd not this, maybe you have a different viewpoint, as Enrique was saying, by thinking in Fourier, but okay, my understanding was, okay, I have the problem that, because in these problems, what we know already is that typically the gradient of U is, the oscillation is controlled, but U is not. So this means that you have this problem that your solution U can be translated here and there. And okay, so this is a way of saying that if you can somehow optimize among all those translation of U, and what you get in this optimization is a control, the best oscillation. Of course, this is an infimum. So you optimize among all this possible, say, translation of U, and this amounts at catching the best oscillation of U. So this is my viewpoint, but maybe it's different to your feeling. I don't know.
Thank you very much for your explanation. Yes.
Something more?
Okay, I will stop sharing. Okay.
Okay, thank you very much. So we start with, we thank you again. So we start with the next talk. So it's the other Enrique Fernandez Cara, who is professor at Universidad de Sevilla. He has a doctorate from this university and also from Paris 6. And his main areas of interest are the theoretical and numerical analysis and control of PDEs, with a special emphasis in nonlinear PDEs from physics, biology, etc. He's going to talk about controlling some PDEs with non-local in space terms. Thank you very much, Enrique.
Good afternoon, good morning, evening, good night. I don't know. I don't know if everything is all right. You see my slide? Do you hear me?
Yes.
Okay. Well, first of all, I want to thank the organizers for having invited me to this meeting. It's an honor for me to participate. And I want to thank deeply the invitation and the chance I have to speak a little bit about our common works with Enrique Zuazua and some other things. I know him since the 80s, and I have had the chance to meet him. I think that first in Paris, and then in Madrid and Sevilla, etc., in the old times. And it is. I'm going to say maybe things that you have already heard today, so it's not new. But I'd like to insist in two qualities that I have always appreciated in him. First, his ability to interact with everybody, and not exclusively on the mathematics he makes, but also in other areas of mathematics, and also, and overall, I dare say, his ability to make good maths in realistic problems. I think that this is a quality that he has maybe since he was collaborating with Jacques Williams. And I think that it's remarkable to insist in the fact that it is possible to have an applied viewpoint of mathematics without renouncing to quality in analysis and quality in mathematics in overall. So I have the feeling to have been very lucky to work with him, and very grateful. He's more than a colleague for me, he's a friend. And I have only one regret, and the regret is that we have not been all the time close enough, geographically close enough to have worked more. But maybe there will be time to continue some of our projects in common. Okay, this is an old photograph. I will come back to some old photographs later. And I will now try to speak about some of his contributions, and some of them with me, but many others of her own, and on the control of PDs. Let me make a small selection of, this is maybe a question of taste, some selection of his contributions that I think that still can lead to some new works. I will begin with an old work in collaboration with Juan Luis Vázquez, related to simple one-dimensional models of fluid-particle interaction, where they introduced an interesting idea that is written here. The idea is to use the lack of collision to ensure global existence, the lack of collision as a tool to ensure global existence of a non-linear problem. I think that this is still something to be extended to higher dimensions. There is something there, in my opinion, that should give something for more realistic problems, in the sense that we can consider either two-dimensional or three-dimensional models of interaction of a fluid and structure. Anyway, I know that this idea has already been used in the world of controllability. In 2005, together with Ana Dubova, we were able to deduce control results of these models. And later, many other colleagues have continued in these directions. There is a work by Liu, Takahashi, and Tuxnack, in which, using an interesting idea, they were able to control these systems acting from one side. Later, there have been works by Muriel Bulakia, Axel Sess, and Muriel Bulaca, later with Sergio Guerrero, in which some things have been made in 2 or 3 dimensions, etc. Let me also enhance something that maybe has not been considered today, is the explanations and remedies that he introduces for the numerical ill-posedness of control waves, of controlling waves. As you know, when you try to discretize, to approximate the control problem for a wave equation, you have to be very careful in the choice of spaces, of approximation spaces. And I think that there is still something to do at the level of reinterpretation of these ideas. Maybe combining these explanations with the INFSUB conditioned by Bresci and maybe regularization processes for the numerical problem. And as a third selected contribution, let me speak a little bit about the sharp estimates we got on the cost of controlling heat partial differential equations in 2000s. It's written there, for general heat equations, we deduced a cost of the order of the exponential of C multiplied by 1 over epsilon. And for the classical heat equation, we were able to go a little longer and to see that the cost is of the order of exponential of A over the square root of epsilon, in some sense an optimal result. And something that has been in the mind and in the work of several contributors since then has been to find the best constant A and to give an explanation of the geometrical characteristics that has to have such a constant in such a problem. As you see, there are still many open questions connected to the control of partial differential equations, and some of them are apparently elementary, but I like very much to present some examples of apparently easy or elementary problems that are not, in order to illustrate the situation. For example, we can ask a simple question: is it preferable to use cheap or expensive controls when you are trying to reach an objective? Let us look at a very simple situation, relatively simple situation, in which you have a finite dimensional system, an ordinary differential system of this kind, which is controlled by you. And let us try to do optimal control with a system of this kind. If you choose a functional like this one, in which P is symmetric and positive definite matrix, then implicitly you are deciding to use expensive controls, because you are trying to minimize the function in which the control, the size of the control, you don't care the size of the control. Contrarily, if you choose this other another function of this kind, in which you have added a term, epsilon multiplied by an integral in which U is explicit, R is another symmetric and positive definite matrix, then you're supposed to be trying to use cheaper controls. You care, you pay attention to the size of the control you are using. So the question is, what is better? To use J, and try to choose an optimal control for the system, or to use J epsilon or small epsilon? Evidently, you always have J of U less or equal than J epsilon of U. So you are going to get, from the viewpoint of the objective, a better result with J. But this is going to cost a little bit more energy. You will have to use a larger U to control, in this case, the system. So the good question is whether you have or not that the optimal value for the first optimal control problem is the limit, as epsilon goes to 0, of the second value of the infimum of J epsilon with respect to U. And this is an open question, in fact. in general, this is an open question. The answer is yes, if the system is linear in X, but in general, it is unknown whether or not this quality is satisfied. It is an interesting question also from the application viewpoint, because in the case of autonomous car driving, these are the kinds of systems you find. So in the autonomous car driving process, the control is a direction system and the acceleration system. So what do you prefer? To have very expensive systems and to get good results, or are you happy if you only use cheap systems and you get more or less the same results? Okay, this is to illustrate the kind of problems that we are going to consider now. I'm going to pass to the main subject of the talk, in which I will try to present some results concerning non-local in space partial differential equations of the parabolic and also the hyperbolic kind. The motivation of this kind of problems is the fact that many times you find non-local chemical effects on the temperature in a heat process, or non-local behavior of flux in the flow of the fluid, or non-local effects of the market in finance system, in finance model. And a typical kind of non-local term that you find is this one, an integral in space of a kernel K, usually depending on X and also psi, multiplied by the state Y. So the system to control in this part of the talk is this one. And I ask whether or not we are able to get null controllability. I mean, starting from an arbitrary y naught at time t equal to 0, with a control V, of course, supported by a small set little omega. Are we able or not to drive the solution of the system y exactly to 0 at capital T? As many of you know, probably all of you, this is equivalent to the observability of an adjoint. I mean, to prove this property, null controllability of the system is equivalent to prove an inequality that is written here for the solutions phi of a system of the same kind that is backwards in time and starts from an arbitrary phi t at capital T. So what we have to prove is an inequality, as usual, an inequality in which we are able to observe the whole phi, looking at the behavior of phi exclusively on little omega times 0t. Usually, when you are trying to do this for a heat equation or something like this, you use Kalman estimates. We use Kalman estimates for phi. And from the Kalman estimates for phi, we are able usually to deduce the observability. The Kalman estimates for phi say that the weighted integral of phi on the whole Q, on the whole set Q, is bounded by a quantity like this one, maybe weighted with an appropriate function rho. But here, Kalman estimates cannot be used, at least directly. If you try to apply a Kalman estimate for
if you try to apply the usual argument to deduce a Kalman estimate for an equation like this one, what you get is something like this. You get a global weighted integral of phi bounded by what you want. That is a local integral of phi, also a weighted integral. But you cannot avoid to find something like this. Something like this that comes, of course, of the term that is here that sees all the behavior of phi in the whole omega. And it is not easy to deduce from an inequality like this one what you want, the observability estimate. So you have to do otherwise. In a result, in 2016, in collaboration with Enrique Zuazua and Q. Lee, we have been able to deduce the observability inequality under some particular hypothesis assumptions on the kernel K. Essentially, what we have asked to K is to satisfy this property. Once you write K as an expansion using the eigenfunctions of the Laplacian, the Dirichlet Laplacian on omega, you need these coefficients, K and J, to be small enough as M and J go to infinity. Small enough in an appropriate sense. Let me say that this smallness of the coefficients implies, in particular, that capital K has to be analytic. It's an analytic function with respect to x and xi. Under this assumption, we were able to prove the observability inequality that I have presented before. And I'm going to give now the idea of the proof. It is the unique proof that I'm going to detail, but I think that it is deserves to be presented because it is interesting to see why we have observability in this case. So we prove, in fact, that phi at time t equal to 0 is smaller than a local integral of p, where p is some part of phi, and this is still smaller than a local integral of phi. And what is p? P is the part of phi that satisfies the heat equation. I mean, I have written here phi equal to p plus zeta, and have imposed to p to be a solution of the heat equation and to satisfy the same final condition at phi. Okay. So this is the inequalities. These are the inequalities that I have to prove. For the inequality in the left, what we have done is to write that phi is the sum of p and zeta at 0, at t equal to 0. T equal to 0 is the final time here, in fact, because this is a system that is going, it's backwards in time. So this is the final time here. And I have written the composition of t equal to 0. And here, what we use is the energy estimates and the observability, the classical observability of P that are satisfied because P is the solution of the heat equation, to deduce that this term is less or equal than this local integral of P. And then we have used the energy estimates of zeta and again the energy estimates of observability of P to deduce that zeta at t equal to 0 is also less or equal than a constant that depends on k, the kernel k, multiplied by the local integral of P. Okay, so this gives this first inequality. The second inequality, which is the harder one, the second inequality is proved by contradiction. So let us assume that this is not satisfied. That we find a sequence of functions, Pn and phi n, for which we have these kind of inequalities. This is much greater than these other local integrals, so this is not satisfied. Then what we prove in that case is that zeta n, which is the difference of phi n and pi n, goes to 0 strongly in L2 of Q. This is the difficult point. The difficult point is to prove that if you have these inequalities, then the difference zeta n between phi n and pn necessarily goes to 0 as n goes to infinity. And here the key point is an inequality, an estimate that we got in 2000, a paper that we published a long time ago, that gives an estimate of the final values of the solution of the heat equation, of the backwards heat equation of this kind. In fact, this is an estimate that we got looking for other objectives, and it's an estimate that gives, if you look at it attentively, it gives the exact controllability of the heat equation in space that is larger, much larger than the image of the semigroup. In fact, the exact controllability of the heat equation in space that it's characterized by the finiteness of the sum that is here. So using this inequality, using the assumptions on K that have been imposed and the unique continuation of phi, which is the solution of this equation, I will come back to this in a moment. Using these three properties, we are able to prove that zeta n goes to 0. But if zeta n goes to 0, then again by the triangular inequality, Pn also goes to 0. And if Pn goes to 0, this is an absurd because we have assumed that these integrals were all them equal to 1. Okay. So the second inequality is also proved, and we have observability of phi. We have used this recently in a paper with Juan Limaco, Dani Nina, and Miguel Núñez to prove the local exact controllability of time t to a regular free solution of the system in the case in which we consider this heat equation with the coefficient, diffusion coefficient that depends globally on y. Before we had proved some time ago the null controllability, the local null controllability of problems of this kind, but now with the result that we have obtained in 2016, we have suddenly noticed that it was possible to prove also the exact controllability to any free solution, provided it is sufficiently regular and provided we start from a point why not, which is sufficiently near. And the argument is not too difficult. What we have to do is to reduce the exact controllability to y bar to a null controllability problem for a system of this kind, and then to adapt the previous result and to prove that it is possible to find a control that drives z to 0, provided we start from a sufficiently small z0. It is also possible to adapt this result to Stokes-like systems. It is not too difficult to do this. In fact, the argument is more or less the same. And it is connected to another argument that appeared in a recent work by Sergio Guerrero and Takeo Takahashi, in which the null controllability of systems of this kind is also proved by another method. And let me also remind that in the same paper in 2016, we have also been able to prove a similar result for the wave equation. The argument is more or less the same, even an easier argument works. And so it is a result that says that this equation is exact controllable. In fact, you can go from Z0, Z1 to any other W0 and W1 appropriate spaces with a control V localized at little omega, provided the geometrical control condition is satisfied for little omega and capital T. Let me make some comments and let me present some questions, some apparently simple but open questions for related to these results. First, let me mention some recent results by Miku, Takahashi, Pierlisi and Zuazua, Bicari, and Victor Hernandez Santa Maria, etc., where similar results have been proved. For example, in the case of the first of these works, the Burger's equation has been considered. Lisi Zuazua considered systems, non-scalar systems, and they proved a similar result about when the non-local terms appear, etc. Two questions. What happens when K is non-analytic? It's not analytic in X and Xi, in Xi. I said before that I was coming back to uniqueness. In fact, one of the ingredients of the proof that I have presented uses the uniqueness, the unique continuation of this equation. This can be asserted because K, essentially because K is analytic, as I said. A related question is for a kernel K symmetric and not necessarily analytic, whether we have or not the unique continuation for the eigenvalues, for the eigenfunctions of this problem. To my knowledge, this is an open question. Which are the minimal conditions on K to get uniqueness here? Another related question concerns this system. This is what is called the Burger's alpha system. This is an approximation of the Burger's equation, in which you have some kind of regularization of the velocity z. Z is the solution of a Poisson equation regularized through a parameter alpha. So it can be used as a regularization of U, and it is known that the Burger's alpha system is globally null controllable for any alpha. So it is a natural question to ask whether or not we have also exact controllability to the trajectories for any alpha, or at least local exact controllability to the trajectories for this system. In fact, you see that this can be written in a similar way as before, because Z is the solution of a Poisson equation that can be written as an integral of the kernel multiplied by U. And if you replace here the value of Z, you find again a non-local, non-linear in this case, non-local parabolic system for equation for you. Okay, so this is another related question. To my knowledge, still unknown. I'm going to finish my talk with some considerations on non-local in time partial terms. I mean, I'm going to consider now a particular system that is related to viscoelasticity, in which instead of non-local in space term, we have a non-local in time term that is, of course, caused by memory, by the presence of memory. This is the system. This is a very complicated system, the Aldrich system, in which you have a sort of generalization of the Navier-Stokes equation with an additional term, the divergence of tau. And tau is tensor, is what is called the extra stress elastic tensor. That is also the solution of an equation. It's a solution of a non-scalar equation that is hyperbolic and nonlinear. It's hyperbolic of first order. You don't have diffusion for tau. And it's nonlinear. There is a term here, G of gradient of U tau, that has this structure in which W of U is the antisymmetric part of the gradient of U, and D of U, as usual, is the symmetric part of the gradient of U. So it is nonlinear in the first special derivatives of U and tau. And of course, this is the source of all problems, of all theoretical and numerical problems for the solution of this system. This is very difficult, so I'm going to linearize the system at 0. And if we linearize at 0 the system, we find something like this. After substitution of the variables, we find something in which you recognize the usual terms of the Stokes problem, divergence of U is equal to 0, together with the memory term in which you have the second derivatives of U inside an integral in time. So the question is whether or not we are able to get boundary control results for a system like this, at least for the linearized system, 0, at least in this case. This is the scheme of the geometric domain in which you are trying to control the behavior of the fluid acting on a part of the boundary, gamma. And these are the results that we have. First, if we ask for a null controllability result for this system, the answer is no. It is not possible to control, to drive to 0 exactly all initial data U0 with a control F on gamma. It is not possible to do this. In fact, a result of this kind was already obtained some time ago by Sergio Guerrero and Danguillo for a somewhat simpler system. But if we ask for approximate controllability, then the answer is yes. For any epsilon, it is possible to control epsilon such that at capital T, the final value of U is distance less or equal than U1. Okay. It is interesting to know, to take into account that if one of the V is equal to 0, then we do get, in that case, we do get if B equals 0, of course, we have the Stokes system, and we know that this is null controllable. And the same is true also, at least under the geometric control condition, if nu is equal to 0. Because in this case, if nu is equal to 0, if you look at this system the good way, you recognize something like a wave equation with the pressure, something like, and this was obtained some time ago in collaboration with the Jose Luis Boldrini and others, and it's known that the result is also positive. Okay. Well, the proofs, of course, rely on classical arguments. It's again equivalent to observability, and it is proof that observability does not hold. So no null controllability of the system. And contrarily, approximate controllability is equivalent to unique continuation of the adjoint. It proves that the unique continuation holds using the analyticity of the solutions and some particular arguments. And I'm going to finish with mentioning other results very briefly, and final remarks and works that have still to do, some open questions. First, let me remind you that the world of viscoelasticity, there is since several years also another strategy that relies on moving controls. Moving controls have been used by Felipe Chavez Silva, Jose Enrique Zuazua, and others to give a positive answer to the control of systems in which you find something of the same kind that we have seen. Something like a parabolic equation coupled to an ordinary differential equation or similar. It would be interesting if it is possible to extend these results to linear or to non-linear, to the original non-linear Oldroyd systems. Of course, there are many things to do still. In the numerical results, for example, to my knowledge, have not been explored for a moment. For moving controls or for approximate controls, it would be interesting to know what can be done. In the case of approximate control, it must be a difficult problem because notice that as epsilon goes to 0, it is expectable to have that the norm of the control goes to infinity, because in general we don't have no control. So this is a delicate problem from the numerical viewpoint, and in my opinion, this deserves some work. And I'm going to finish with a question that is pertinent, in my opinion. Said, in fact, for the original non-linear system. Remember that there is a work by Jean-Michel Coron and in which it is proved that the Navier-Stokes equation is controllable, is locally controllable with one component, something that is not true for the linearized system. So it is not desperate to think that the non-linearities that we find here and overall in the equation for tau and make it possible to control, at least locally, this system. This may be a complicated question, but it is not clear whether or not non-linearity, non-linear systems are appropriate to controllable, at least locally. Okay, thank you very much. Muchas gracias por la atención y felicidades a Enrique por su cumpleaños. I'm going to finish with a picture in 2007, and I'm going really to finish with some words of a very beautiful song by Simon and Garfunkel, old friends, bookends, says something like this. Long ago, it must be, have a photograph, preserve your memories, they are all that's left you. Thank you very much.
Thank you, Enrique. So are there questions or comments from Michelle?
Yes, thank you, Enrique, for this very nice talk. I'm not expert in this case where there is this kernel, but there are counterexamples to the fact that it may be not controllable for some k with a yt minus Laplacian world is integral from an omega k of xy and so on. Is there a counterexample or?
Sorry, I didn't hear. Can you repeat, please?
Yes, I was wondering if there are at least counterexample, let's say for k C1 or C2, to the controllability, to the null controllability. For the when there is a
in the case of the
yes, the integral of k.
You mean for the
non-local equation with the kernel
A? Excuse me, I didn't hear. Can you repeat again?
You have this result that if the k satisfies some condition with which implies analytic.
Okay. See, yeah. No, I don't know. I don't know any counterexample. I don't know.
What happens if k depends on time?
What happens if k depends on time?
Okay. Well, k depends on time. You you have to be able to control the non-local term anyway. I mean, if k depends on time, then you can give you can use usual estimates in order to control the integral. The problem is k depends on time and x in a mixed way. In that case, I don't know what to do.
Okay.
I don't know if you have k equal to something that depends on time, and that can be outside the integral, then you can use it as a coefficient, and there is no problem to work with it. This is the argument used, in fact, for the controllability of the nonlinear system. In the case of the nonlinear system, you have something that depends on time, but it's outside the integral. The problem is that how can I say, if the dependence is more complicated than this, it's mixed, then you have a problem.
Thank you very much. Thank you.
In that case, it's not easy to speak. Okay. Thank you.
Enrique Zuazua.
So can you go back, Enrique, please, to the slide where you were talking about cheap controls and expensive controls, the limit as epsilon goes to 0 of j epsilon. So you said that that you know the answer when g is linear, right?
Sorry. Yes.
But okay, so even if u enters as a multiplicative control, right?
Yes.
Even if u enters as a multiplicative control, so if g is linear, you know how to do it. But if g is non-linear, you say this is not known.
This is
okay.
Point. This is in fact, this is a result. It is in the there's a book by Blondel, and one which has a list of open questions for controls, and there you can find the result. The result is by our law, and it is very well explained there. Counterexamples in control. Yeah. I think that this is the title. Counterexample.
Okay. It's very nice. It's a very nice problem, actually. It looks like very simple, so it's nice to look at. Good, excellent. So thank you, Enrique, for so many years of collaboration and friendship, and the great talk. And thank you all for being there so late, and the excellent journey. I mean, it was an excellent series of lectures, definitely. Yeah.
Okay, thank you. Do you have any other question or comment? Oh, I have a question, Enrique. You said that you have this non-controllability problem is not possible for the Oldroyd equation or something like that. And I may ask if maybe it is approximate controllable, but not non-controllable. So maybe is there a minimal time of controllability or something? You don't know.
Good question, in fact. It's a good question. I don't know. I haven't looked at this. I haven't looked at this. And I'm going to, yes, it's here.
I don't see it, but
I don't know. I don't know, but I'm not sure, because in fact, the argument that we have used in order to prove that this is not null controllable is that it is not possible to have observability. And if I remember well, we don't use here the size of t. I mean, if I remember well, for any capital T, we prove that it is impossible to have observability here. So I think that it is not a problem of minimal, of having time large enough. I think that well, I have to see with detail, but I think that for the moment, I think that it is not the problem with the size of T, but it is a good question.
Okay. Well, thank you very much. So if there is not any other question, let's thank all the speakers of today and see you tomorrow.
Thank you. Hasta mañana. Chao.
Hasta mañana.
Good night.
Mañana,
En la madrugada para mí, ¿eh? They
bueno,
are
un abrazo a todos,
making me to wake up very early. So have a nice day, afternoon. Bye-bye.
Good evening.